disappeared a couple of weeks ago.
I see. Okay. Now I'm going to announce your talk right now in my group so that they will pin down their schedule. Oh, by the way, so Robert, I think I get Ziwei a postdoctoral position in Purple Mountain Observatory.
Yes.
So he told you that, right?
Yeah, he accepted.
Okay. Yeah. Okay. Right.
But you know,
So,
Jiao Hao, your former undergraduate in Jiao Hao.
Yes, Jiao Hao. Yeah,
He's doing extremely well.
Okay, that's
very,
great.
very well.
Okay. And is she also going to graduate soon? Or?
Well, she's now in her first year PhD. She finished her master's.
Okay, that's great.
So no, she has a little bit of time left.
Okay.
At least 2 years.
Right. Good. Yeah. And in recent days, there are a couple of young boys and girls, after this whole pandemic issue, then they gradually come back to visit with me and with the other people in China. Some of them probably will start to look for jobs recently. Okay, great. So I sent your talk information to my group. Yeah, we'll watch how many students to show up. Yeah. Also, just a few days ago, Wang Yi also came back to USTC for visit. Yeah.
Ah, well, okay, I understood. I didn't notice that you also joined me to a group, so now I'm in a group also. You always live in these WeChat groups. I'm already adapting to it, but it's fantastic. Yeah. WeChat replaces here everything.
Okay.
Yeah.
Yes. I'm also sending you the. So I think there are a couple of topics that you might be interested in.
Yeah. Yes. Okay.
Right. So there are 4 different sessions, which will, might be related to. I mean, some not all, but some of the talks will be related to us.
Yeah. I see. That looks interesting. The most simple for me is now to get Chinese visa. I don't need Chinese visa. Very nice. Actually, I have to say you that China is the most efficient bureaucracy which I met before.
Really?
Yeah.
Like in what aspect?
In every aspect, I can tell you.
Okay.
Even getting a visa. It's the first time when I got a so serious visa in matter of 1 week.
Right. Yeah. It depends. I mean, if it were some urgent issue, then they will do the things very fast. it only depends on whether they want to do it or not.
Yeah, but for me, something strange really happened, because when I came to Chinese consulate, to Chinese visa center, they were kind of, how to say this, they were kind of accepting me first like a normal guy, of course. But then they asked me what's the reason I'm going and where do I go. I told them that I go to Shanghai with a high talent application visa. And they immediately opened to me extra doors. They gave me seats. They told me like, they will process documents in a matter of 1 or 2 days. There is no issue about this. And they very apologize that they cannot do it right away so that I'm free immediately. I don't know what exactly has triggered this, but once I said like I'm going to Shanghai, things changed incredibly. I don't know why. My only someone in this consulate was from Shanghai, and he was kind of happy to see me, but it was strange a little bit. No, but even here, all this bureaucracy is very efficient. I didn't go anywhere. I just people in the university did for me everything. Everything was done smooth and nice. Extremely efficient, extremely convenient.
I'm gonna grab a cup of coffee. So that
Yeah.
understand that.
And by the way, just a simple question. If I will go to Hefei, is it difficult or not to get a hotel? Because
It's very easy to.
No,
it's
because
very easy.
someone told me that if you are Chinese, then it's easy, of course. But if you're a foreigner, it may be an issue that some hotels don't serve foreigners. Can this be the case?
Well, yeah. In the past, yes. Many hotels are not authorized to host international people, but at least as far as I know, more and more hotels are, if they get this kind of the right, it's not difficult for them. And at least in Hefei, I would say most of the hotel are able to accommodate you, so you don't need to worry. And just in case you come, you just let me know, and I will book the hotel for you, so you don't worry about that.
No, I think I will do it simpler. Tomorrow I will anyway navigate to secretary to find out how do I do this so that I don't break rules to be reimbursed later. I just have to know. It's will be actually my first time to go somewhere further than Shanghai. So
That'd be great.
So I will find out how it works. No, generically I know how to buy ticket or how to travel in China. Oh, hi, Luca.
Hello, good morning, Alex.
Hi, Luca.
Hello, hi, nice to meet you, guy.
Nice to meet you.
Oh, we still have 4 or 5 minutes, right?
Right, Luca, I would like to negotiate with you for something.
Yes.
Because previously my talk was arranged at 1:15, but now one third, right? But then this talk has been postponed. But I actually have another meeting at 3 o'clock. So I wonder if I could make my talk a little bit quick and finish it by 2:40. Is that okay for you?
No, for me it's okay. I guess also for the organizers it's fine, right?
Yeah, sorry for the
No problem.
No, for me it's okay. I'm already learning this Chinese thing. We cannot influence it. It's it's very often here to announce even very important meeting literally less than half a day in advance.
Right.
Okay.
It's very easy.
Just for me to understand the time, because here in Europe is different. So in Europe, in China meant to start at 2:15. So we will start anyway at 2:15, right?
Right.
And we have to finish by?
So
2:40. That will
practically speaking,
okay.
Practically speaking, we have half an hour, okay?
Yeah,
okay.
half an hour. Exactly.
Okay.
Yes. So we will start very sharp and finish a little bit earlier, also sharp, because I also can be one day in the same situation, because here it's indeed very strange.
Right.
Like you can get in the morning notification that you must present at some meeting 3 o'clock,
Right.
no matter what. And then it's up to you.
Yeah.
And I'm learning this thing already. Actually, Antonina told me, Marziano, that is quite an often thing, like you get in on Thursday or Wednesday notification that Monday is the deadline for some application.
Right. Yeah.
Which you have to prepare like 20 pages or whatever.
Okay, so since we have to be in time, shall we maybe start with the slide sharing? Just to check if everything is fine.
Let me share my screen now.
Yes. Yes, you can.
Okay, very good.
Sharing.
Well, yes, I kind of make some mistake in online. Okay, great.
Very good. Yes, so according to the schedule, we should start in 2 minutes. Shall we wait or shall we start already? Hey, Masahide, good morning.
Hello.
Hello, Masahide.
Nice to meet you.
Yeah, I can hear
Hello,
you.
Ifu.
Yes. Hello.
Good to see you, all of you.
Yeah, it's very good to see you online. And we will see in person next week.
Yeah, sure, yeah.
Finally. Okay.
Okay, so maybe we can start, right? So, okay, good morning, everyone, and welcome to this second day of workshop. And our first speaker for today is Ifu Kai. I hope I pronounced your name correctly. And he's going to tell us about the leaks of nonlinear resonances in the primordial universe. So please, you can start.
Okay. Thank you very much, Luca. It's very nice to see you all online. And this is a talk that I guess some of the audience probably have already heard about some time ago. It's a kind of the introduction to a collection of the works that I have been in collaboration with a number of people. Many of them are very young, talented students used to be in my group. And but because today I kind of have very urgent issue later on, so I'm skipping the introduction to these people. But today I would like to share with you actually from two aspects. One is to introduce a new mechanism, which is called the sound-speed resonance mechanism that was proposed to enrich the cosmological perturbation theory, as well as the production of primordial black holes. And the second part will be inspired by this line. We will see what kind of observational phenomenon that would happen if there is a non-perturbative resonance effect inside the same B window So that is to beat the light bound by a resonant field during inflation. And if depending on the time, I will mention the new physics, the probe of the new physics using the gravitational wave astronomy by virtue of sound speed resonance. So, well, to begin with, I would like to mention, the topic of the primordial black hole recently is very hot, and well, many people considering this aspect for different motivations. Like, the primordial black hole can be a very good candidate for dark matter, and when people report the discovery of gravitational wave events from the black hole binaries, then there is a possibility this kind of the black hole binary could originally arise from the primordial black hole as well. And the normal saying, I remember a couple of years ago, I remember Robert Brandenburg and his collaborators discussed the seeds for the supermassive black hole from cosmological origin. And also, I know this, the Hawking radiation of the primordial black hole, which would have which happens to take place right now in current universe. Then this could be a candidate for the short gamma ray burst. So there are a couple of motivations for people to look at this. So then people look at how to to produce primordial black hole in a very efficient way, and then that touch the early universe models. And well, to be honest, this actually I learned this lesson very late, just a couple of years ago, and there was a very comprehensive review by Mr. Sasaki-san and his collaborators. And I remember that paper was pretty long, and then the number of the models that I just select very randomly and to show here. For example, if you have this running mass inflation with the slope of the potential to change significantly, or you have this so-called inflection point inflation, which allows for a very short range of the usual slow roll inflation, or you introduce some new ingredients like the Coulton field, then you have the chance to enhance the amplitude of the primordial curvature perturbation in a very certain range. However, once you introduce this, you change this inflationary trajectory, or you change the slow roll parameter, or you introduce the new ingredients. In general, there's a the uncertainty for the the parameter choice and the discussion on the new degree of freedom. So with this in mind, so a couple of years ago, like I go back to 2018, my collaborators and we are considering by revisiting the cosmological perturbation theory. So for the standard perturbation, usually we use this Mahanov-Sasaki variable to describe the propagation of the primordial perturbations during inflation. Then, well, if you look at the equation motion here, you'll see we don't have much game to play because basically we only can play the trick on this z parameter actually is a proportion to the square root of 2 epsilon times a over cs. And if you play the trick with the epsilon with the scale factor, then that goes back to the detailed inflation models that just I mentioned. But there's one hope, one chance that we could play the trick, that is to look at the sound speed parameter. And but if you change the sound speed parameter very significantly, this would also bring some trouble. For example, if you go for dBi inflation with a very small number of quantity of sound speed square, then that would lead to the observationally over large primordial non-Gaussianity, which would be very tightly constrained by the same observations. So what we did was to just parameterize. First of to begin with it, we just parameterize the sound speed parameter by hand, and we just write down this the c square, which typically equal to unity, but we introduce a small modulation, the cosine term as a modulation. And so this is the parameterization that is expressed as 1 minus 2 epsilon times 1 minus cosine 2 k star tau. And of course, we have to choose some moment for the beginning of this oscillating modulation, so that this the modulation has only last for very short while during inflation. And with this parameterization and inserted into the equation motion for the perturbation, then you can immediately realize this actually can be reformulated in terms of the Massieu equation. And for Massieu equation, well, you will have this this instability band range by range, and that belongs to the narrow randomness, right? And so well, here I have skipped the detailed calculation, but just give you the expression for the pulse spectrum with this I mean within this mechanism. So this pulse spectrum, you can see the first term is AS times the co-moving wave number divided by K pivot, the pivot scale, to NS minus 1, which is the standard inflationary laminar CDM pulse spectrum case, right? But then there are some other corrections. The other corrections, well, I specifically take out the first correction because that is a definitely dominant part, and that is expressed as some quantity times exponential term. This is e to minus c p star times tau I. This this is because during inflation, the co-moving time is negative, so that minus tau I actually represents for how long time this redness have lasted for. And so then you can see within this p star times tau I, then that gives you an exponential enhancement for the pulse spectrum that corresponds to a particular scale. And with this in mind, then you can carefully select your characterized oscillating frequency, and so that this enhancement can be free from the observational constraints from the Planck scale and the larger scale structure survey, and then go for the small scales, so that this pulse spectrum is able to generate the primordial black hole very efficiently. And once you have this pulse spectrum, you can translate it to this density parameter, this f PBH. This f PBH is defined as the density parameter for PBH divided by density parameter for dark matter, right? And here I just show this the mass spectrum, and confronting with the various astronomical observational window. So you can see this pulse spectrum actually gives you the multi spikes on small scales, and in the meanwhile it remains scale invariant on larger scales. So this, well, of course, this one is quite an interesting phenomenon. And then a question following is how to realize this mechanism, say within the inflation background. So what we did actually, we tried this this target from two aspects. The first was to look for a very concrete, very specific model to illustrate this mechanism indeed can happen. So then we still play the trick of the DBI inflation model. But this is, well, when we talk about the DBI inflation, we just take this action, okay? But it still belongs to the slow inflation. The warp factor actually is very small, so that the sound speed remain very close to unity. And the second line that we did was developing from the effective field theory. And we just try to look at what kind of operator is able to yield an oscillating sound speed parameter. And then that typically goes back to the two-field inflation model. So in following, I would like to mention this to describe these two stories one by one. So the first was the DPI inflation realization, and because we want to realize this cosine of modulation in CS square, then typically for DPI inflation, CS square equals to 1 minus F phi dot square, and then what we did was to put in the ansatz for this model. Like we put this ansatz, this walk factor has some small modulation for a short range for phi, and then we are able to resolve the equation of motion and to derive, because for the background level, the phi is not sensitive to this oscillation part. The evolution of phi in terms of the co-moving time can be calculated appropriately. So then we can reversely to reconstruct the formula of this F term, and then what we did here in the following, this walk factor actually can be written down as this lambda over phi 4 times 1 minus theta function times this C function, and this C function is the key element to yield the oscillation term. So and we just using one example to illustrate this actually is able to realize this sound speed readiness mechanism. And very recently, there's another work following this line is to look at, once we introduce this unconventional walk factor, does the back reaction significantly affect the background dynamics? And our conclusion is the back reaction actually is totally under control here. Okay, so just right now I mentioned this DPI inflation just as a the illustration to realize this SSR. But as I mentioned, if we go back to the effective field theory, we need to look at what kind of the operator can yield the oscillating modulation for the sound speed square. And then if we embed this framework back to multi-fields, then what kind of the non-perturbative readiness can happen. So we go back to the two field, and here I just mentioned this. There's a one-point model, and this here I show you this the trajectory of the inflationary trajectory along the two fields. In the first period, the inflation happened when the scalar field rolling along with the phi direction, and you will see this bright and shadow range that corresponds to the oscillation along the potential. And for example, this can be realized by so-called the axial monodromy model. But when this field loses the kinetic energy, and then it will automatically turn down along the chi direction, right? And along this chi direction, what we used was the profile of the chi direction potential was derived from the relaxation model. So it's just a linear function. And with this toy model, we can immediately write down the equation of motion for two field fluctuations. And the first equation is the delta chi, and you will see the right hand side of this this equation. Actually, you can see this delta chi is seated by delta phi. But for delta phi perturbation equation, then you will see this equation actually can be reformulated as a Massieu equation. So that means the non-perturbative readiness can happen on delta phi and then reflecting on delta chi. So then we use this two field particular model. We calculate the power spectrum and compare with the SSR, and we will see naively speaking, these two mechanisms are very similar to each other. And also we calculated the induced gravitational wave power spectrum. Okay, so so far what I mentioned is that this readiness is not very single or very particular phenomenon. It can be realized in many cases, right? And then another crazy idea is that, well, I'm saying crazy because typically people wants to make this resonance out of the CMB window, right? But well, reversely speaking, we can think about this idea in a very crazy way. That is, can we realize this resonance effect within the CMB window? And if this happened, what kind of a stupid? I mean, I'm gonna make a joke, not that stupid. Observationally, what kind of the effect can be brought by this resonance? So, in order to look at this question, then we here in the following, I just spent 2 slides to take a look at from the observational aspect what information we care about most. So basically, we are interested in 2 spectrums. One is the pulse spectrum for the scalar fluctuation, which has been discussed previously for a couple of for a while, and the second pulse spectrum is the pulse spectrum for the primordial gravitational wave. So that is the tensor mode. And for these 2 modes, the scalar perturbation has already been measured very well by the temperature anisotropy of the CMB, as well as the E mode polarization. And we know the gravitational wave, primordial gravitational wave, is expected to be measured by the primordial B mode polarization in the CMB map. And so far, and we know this is a very key goal for a lot of the CMB experiments. And but if we make take a close look at this 2 pulse spectrum, then typically we use this tensor to scalar ratio to understand how large or how small this tensor mode would be. And this tensor to scalar ratio, actually, if you put in the equation, the expression into this formula, then you will see actually that equals to the A times the d phi over the enfolding number divided by m Planck square. So that means if the inflation lasts for, let's say, over 60 efforts, and then typically this there's a bound for the variation of the field excursion during inflation. So that is, this delta phi is expected to be larger than r divided by some 0.01 square root of this number. So, and from the observational side, we know the latest constraint on tensor to scalar ratio is that r is smaller than 0.036. That is a combined Planck data as well as the bicep and the KK. But we know if we expect for observable, observationally interest signal for the primordial gravitational wave, then typically the tensor to scalar ratio should be larger than 0.01, and so that the field excursion during inflation would be be super Planckian distance. And there are a lot of in the literature there are a lot of discussions on the troubles with this super Planckian distance for the field excursion during inflation. For example, if you have the variation of field to be larger than m Planck, then you are forced to consider the high order quantum corrections. And if you get involved in high order field corrections, then you are forced to consider even higher, right? So that makes the prediction of inflation cosmology unpredictable, typically. Okay, so then a question is, let's say if we consider the field, the field excursion is very small, let's say much smaller than m Planck. So that is referred as a small field inflation. And typically for the small field inflation models, the tensor to scalar ratio is very low. And if it were that case, then the countries, the governments in the Earth, they shouldn't spend too much money to to build more telescopes to do the CMB experiments, right? Otherwise, it's kind of waste of money. But what we think is, let's say if we are able to beat the light bound, and we still the background model is still small field inflation, and on average, the signal of the primordial gravitational wave remain very small. But let's say if there's a resonance effect during inflation that can significantly enhance the primordial gravitational wave, then when the government makes the investment on the CMB experiment, they would feel this work deserves, right? So this is the goal that we want to do. And again, we take an analog of the toy model that we discussed. We can see the two-field inflation model, and we require that kite to be massless, so it's very light, and basically it controls the curvature perturbation. And there's another field which is quite massive, so delta phi is quite massive. So on average, this is not a scale invariant. So basically, you don't need to worry about that from the global CMB observations. But this delta phi is massive, but it can be resonant, and it couples to delta chi only gravitationally. So this coupling is very weak, and then it makes the control on the S curvature perturbation. So what we did is to write down this action by taking out the elements that the operators that we are interested in. And then we impose three conditions. The first condition is that the resonance has to happen inside the Hubble horizon. So this is limited as a very narrow resonance in a shorter window. And the second condition is that this resonant heavy field must decay at super scale so that it would not affect the curvature perturbation that much. And the third condition is that the resonance field mass needs to be to evolve to a small number right after the Hubble crossing, so that the effects, if we have the resonant effect on the tensor mode, then this tensor mode should be induced non-linearly. Then the effect can be frozen right after the Hubble crossing. So again, we use we consider a toy model here, and you can see we did do the calculation with a very concrete parameter choice, so that it can last for 60-40 number with appropriate convention that can be consistent with the Planck. And you can see the variation for both high field and the phi field. The field excursion is very small, right? It's quite very small number. So yeah, and with this toy model, we find you can see from the left top side of this slide, you can see this that high field evolves just as a normal way. So the curvature perturbation was not affected, but the heavy field, this that phi field, experience a resonance window by and its amplitude can be amplified by a factor of 10 to 4 to 10 to 6, some kind of this factor that can be determined by the parameter you are choosing. And then because this curvature perturbation amplitude is enhanced, and then you are able to use it to induce the gravitational wave nonlinearly by your second order by solving the equation motion at second order. So then there's a nonlinear induced contribution here, and eventually this part of the contribution is able to be translated to the B mode power spectrum, angular power spectrum, that can be read from the right part of this slide. You can see here let me explain a little bit. There's two dash lines. The one dash line corresponds to the current observational bound, that is about 0.07, but actually now it's 0.0636. And then if it were a small field inflation, the consistency relation requires tensor to scalar ratio equals 16 times epsilon, and that is a much lower than any sensitivity curve for experiments. And in the meanwhile, we know from let's say from the SPT, from Paul Bell, from many CMB experiments, we are already able to measure the lensing background for B mode very well, which is can be read by this orange line. And then with the two concrete examples that we considered in previously, then you'll see for either for this this red curve or this black curve, the signal of this half spectrum by considering this is the induced signal, then it can reach the sensitivity curve for some forthcoming CMB experiments. For example, the light bulb. So this is so that means in the near future with the CMB experiments measuring the polarization, they are able to make a probe on the small field inflation by including the resonance effect. Okay, well, actually, there's another story that I want to share with you, but I guess it's a kind of very limited time. But just mention that we played the same game on the sound speed parameter for the gravitational wave, and that is to parameterize the CG square as a unity with combined with a correction, some cosine modulation, and that can be motivated by some modified tensor generic tensor scalar theory. And with this parameterization, we are able to rewrite the equation motion as the Massieu equation as well. And let me skip the detailed formula, but just to show that if we have some modulation arising from modified gravity models, and if this modified gravity happens, for example, at a TV scale, I mean the corresponding operator is at the TV scale, then and it can yield this oscillation for the gravitational wave, then it can lead to the resonant enhancement on the stochastic gravitational wave background. For example, this enhancement can form a peak, a very clear peak, for which the typical frequency is between 10 to -3 to 10 to -2 hertz. And this observational window is exactly within the space-based gravitational wave detectors like LISA. And if we push the modified gravity operator to be even higher in scale, like 10 to 4 TV scale, then the peak will be moved to 100, and that is exactly interesting to the ground-based gravitational wave detector like LIGO and a couple of like a Kagura and some other experiments. Okay, so well, sorry for the change, the plan changes. So I finished my talk in a very quick way, but I still want to take a chance to carry out some points. For one thing, that is if we have this nonlinear, non-perturbative resonance in the early universe, then there are a couple of primordial relics that can be produced, like the primordial black holes. And one mechanism is this so-called sound speed resonance, and that corresponds to the narrow resonance effect. And if we extend this scenario to the window for like the CMB window, then there's one possibility, that is we are able to beat the last bound with this nonlinear correction, and that may leave some observational signal for the forthcoming CMB experiments. And also, I give one example to illustrate using the gravitational wave astronomy by virtue of the sound speed resonance. Then we probably can probe the new physics or falsify this mechanism within the gravitational wave astronomy. Okay, so let me stop over here. Thank you very much.
Thank you very much, Ifu.
Yes.
So I know you have to go. Maybe we can just ask for one quick question if you have time. Sure. So please, if you have any quick question, we can.
It was one in the chat from Robert.
Yeah.
Yes.
So Robert. Yeah, I saw one question.
Yeah, you
how to
answered
get-
it. You answered it before.
Yeah, okay. Okay. Good. Okay.
There is a question from Anna. Maybe quick one.
Hi, Anna.
Hi, thank you very much for the nice talk. I have a question regarding whether the theories which give such strong signals, peaks in the power spectrum, resonances, or whatever other on the perturbative control during, I mean, during the effects considered here.
For example, you are talking about, for example, the back reaction during inflation, something like that, right?
Not only back reaction, actually, because you start from some theory which may be non-renormalizable, and the question is, what is the cutoff of this theory? Whether it's smaller than
right
of the resonances or all these things. Right. I just wonder if it was checked.
Yeah. Okay. This is a very good question. Let me briefly address your answer like this way. And perhaps there are some other, today we have a lot of experts online, and they may answer this question even much better than me. So in general, when we look at the phenomenon brought by the cosmological perturbation theory, we at the moment we are not so caring about the non-renormalizability. For example, as I mentioned, for large field inflation, the field excursion is always larger than Planck scale, right? So as I mentioned, you have to get forced to consider the corrections order by order, and then even that would spoil the predictability of inflationary cosmology. But when people only look at the perturbation theory, then they make the Taylor expansion. So with this to this level, I think the theory is still under control. I'm not saying it's fully renormalizable, but it's under control. So that's why I mentioned for the resonance effect that we care about for very early universe. For one thing, we care about the back reaction because I did the check, okay, and that is totally okay. But I know very recently there are a couple of people talking about the quantum, like the loop corrections, and for the loop corrections, and if it even at the linear for the perturbation mode, which has already involved some non-perturbative effects, then to be honest, the calculation is it involves a large uncertainty theoretically. But if you I don't think the involvement of this theoretical uncertainty would totally destroy the phenomenon. So the phenomenon is still over there. So basically, what I want to say is the calculations that I show here in this talk, it still needs to be improved. Like you have to, as I mentioned, abundant underlying physics of SSR still needs to be explored. And so, for example, you need to carefully calculate this the loop corrections case by case, model by model, right? But I think the phenomenon that I introduced to you today, it is generic. So this is the point that I want to carry out.
Okay, thank you for your reply. It's just maybe it's not a question about loop corrections. It may be too complicated. It's a simpler thing, like the question where the theory breaks down and whether the corresponding energy scales,
Yes.
like frequencies of resonances, whether they are below the unitarity breaking scale.
Sorry, I didn't catch you. Sorry.
Yeah, my comment is just that maybe to decide whether this is under control or not. It's not required to do full loop corrections. Maybe enough just to compare the corresponding energy scales, unitarity breaking scale of the theory you are using for this phenomenon. The frequencies of resonances which you obtain.
Okay, thank you very much.
Okay, thank you.
Okay. Thanks, Anna, for the comment and questions. So I guess Ifo has to go now because meeting very soon. So, but thank you very much again for your interesting talk.
Bye. Thank you. Bye.
And have a nice day.
Thank you.
Yeah, you too.
Okay, we are okay. Of course, still in time, but maybe we can. Yeah, thanks, Masaida, for start sharing. I think organizer. I think we can already start, or you have to wait a couple of minutes.
Maybe just let's wait. People want.
Yeah, we can wait a little bit, like couple of minutes. But I expect if someone wanted to come exactly to the talk by Professor Yamaguchi, these very serious Japanese colleagues, they're usually in time, so they will not be late. So we should not worry.
Okay, you tell me. We can also start now then.
Hello, Suraban.
Hello.
Good to see you.
Great to see you.
Well, basically, Masaida, we finished the previous talk a few minutes before. That's why we are just waiting a couple of minutes.
I cannot use Apple Pencil.
I don't know. Alex?
Oh,
I think you can annotate, Alexei.
I cannot use Apple Pencil.
I think he took a break. We will start when Alexei is back.
No, I sorry, I just unmuted, forgot to unmute microphone.
Okay.
Masahide, you can annotate only on the device from which you share.
I see.
Because there is no other option, unfortunately. Either I forbid it completely, or I allow like this, or I allow to everyone. And then practically everyone can start annotating, which is not great sometimes. We already had this annotation.
Okay. So I just only use the pointer.
Yes.
Because normally, I share the file from a laptop, but I use the Apple Pencil through iPad.
Yes, I understand what you mean, but you see, if I
I understand. Okay, no problem. Okay.
If I allow this, then everyone can annotate in principle. Let's say in a normal discussion, it's okay, but when there are many people, it's not always coming with a good outcome.
Okay, no problem. I will use pointer.
Okay.
Can you see my pointer?
Yes.
Yes.
Then maybe no problem.
Well, then, Luca, it's up to you, but I think we can.
Okay, we can start 5 minutes before that. So we are just 5 minutes schedule. Okay, so we can move to Professor Masaida Yamaguchi, who moved recently to Institute for Basic Science in Korea, as we can see from his first slide. And he's going to entertain us for the next 40-45 minutes with new dynamical degrees of freedom from invertible transformations. So please, Masaida, when you want, you can start.
Yeah, Luca, thank you for introduction. Yeah, I'm very happy to give a talk in this wonderful workshop. And as Luca said, recently I moved to the Institute for Basic Science in Korea. And so, now I'm very busy for setting up my center. But anyway, And today I'm going to talk about new dynamical degree of freedom from invertible transformation. And this is quite simple argument on the transformation, but the result is, at least for me, quite surprising and unexpected. And this work is based on the collaboration with Pavel, Keigo, and Alex. Okay. And the content of my talk is as follows. First, I'm going to give a brief introduction. Yeah, how ubiquitous field transformation or change of the variable in mathematics and physics. And actually, I'm going to discuss appearance of the new dynamics from the invertible transformation. I'm going to define what's the invertible transformation. And normally, yeah, as for the invertible transformation, we have a famous inverse function theorem. And I would like to remind you of the what's the inverse function theorem. And we are going to discuss not only singular, but also the invertible transformation. And I also define what's the singular transformation. And as a application to the physics, I'm going to give the simple example of the so-called magnetic gravity. And finally, I summarize my talk. Okay. So as you know, yeah, field transformation is quite ubiquitous in mathematics and physics. This is very small partial list of the transformation, gauge or global transformation fields, Bogoliov transformation or Fourier Laplace transformation or Galilean-Lorentz general coordinate transformation. And these transformations typically provide better ways to understand various physical phenomena and to advance calculations sometimes, especially to solve the more easily differential equations. So these are quite ubiquitous. And among many transformations, inverse transformation is special. And here we define local invertibility such that there is at least locally one-to-one correspondence between old variable and new variables. For example, if we consider the transformation such as y equals x squared, then you can easily see that except around the origin, x equals 0, there is a locally one-to-one correspondence. For example, around here, we have a one-to-one correspondence. You see, this is my definition of the local invertibility. Then, given the transformation, how to judge such local invertibility? Okay. And before going to address such a criteria, first, we also define regular and singular transformation. And let's consider the transformation y equals xj. This is old variable and this is new variable. And as is usual, we can define the Jacobian matrix like this one. Okay. And we define this transformation is regular at some point when this determinant of the Jacobian matrix, or simply Jacobian, is non-zero, which implies that no eigenvalue vanish for this Jacobian matrix. On the other hand, we define this transformation is singular when this Jacobian vanish, which implies that some eigenvalue vanish. This is very simple definition. Okay. And then famous inverse function theorem says that as long as this transformation is regular at some point, there is a one-to-one correspondence or just a local invertibility around that point. This is a statement of the famous inverse function theorem. And for example, if we consider the y equals x squared, then Jacobian matrix is simply just 2x. So it vanishes, or this transformation is singular at x equals 0, which is nothing but y equals 0 too. So inverse function theorem says, except around the origin, x equals 0, there is a one-to-one correspondence. You see, this is a statement of the famous inverse function theorem. And consequence of this kind of the regular or, you see, invertible transformation. You see. So inverse function theorem says that as long as the transformation is regular at all points, it's invertible, at least locally. And so what's the consequence of this transformation for the dynamical system given by the new variables characterized by the following action? And we consider this kind of transformation, which is regular, that is local invertibility at all points. And the new dynamical system characterized by xi is given by this one. See, this is a new variable, new action. And as you know, at least classically, least action principle give the equation motions. So we have only to take the variation of this new action with respect to x. And this is just a simple convolution rule, you see. So just delta S alt divided by delta y times the Jacobian matrix is delta xj. This is just a chain rule. And by assumption, if we require this Jacobian is regular at all points, it means that this is Jacobian determinant of the Jacobian matrix doesn't vanish. So simply saying that this variation of the new action with respect to xi vanish is completely equivalent to this part vanish because of this Jacobian matrix is regular, okay, or just invertible. So both systems are completely equivalent. This is in some sense physically quite reasonable because as long as this transformation is invertible, which implies that there is a one-to-one correspondence. So just relabeling the dynamical variable. So physically nothing is changed. So both systems are completely equivalent. This is quite natural and standard. Then we are going to move to something interesting transformation, which is singular but invertible. Okay. As I said, as I explained in the previous slide, regular transformation is always at least locally invertible through thanks to the inverse function theorems. And such a regular and invertible transformation gives the physically same dynamics, as is shown in the previous slide, because it is nothing but the relabeling. And also, of course, the same number of the degree of freedom. But please remember that opposite of the inverse function theorem is not necessarily true, or you see, it does not apply. So please remember that our definition regular implies that regularity of the transformation implies that just a Jacobian is non-vanished. And the inverse function theorem says that as long as the transformation is regular or Jacobian is non-vanishing at some points, it's local invertibility. It's guaranteed local invertibility. But opposite is not necessarily true. It means that even if the transformation is singular at some points, it can be still locally invertible. You see, it's not necessarily these are non-invertibles. Okay. Let me give such a simple example. Let's consider the y equals x cubed. You see, and at x equals 0, Jacobian matrix is 3 times x squared. So Jacobian vanish at x equals 0. But from this figure, you can easily see that this transformation is completely invertible everywhere, one-to-one correspondence. You see. So inverse function theorem says that as long as the transformation is regular at some points, it's invertible. But opposite is not necessarily true. Even if the transformation is singular at some points, it can be still invertible at some point. Okay, please remember that. And we are going to discuss consequence of such a singular transformation. Okay? Now we consider the transformation from x to y, and this is an old system given by y, and the new system is given by x. And as is, we can easily get the variation of the new action with respect to x through this chain rule. And as we explained, if this Jacobian or transformation is regular, these two conditions are completely equivalent. It's nothing but the relabelings. No change of the physics, you see. On the other hand, once this transformation is singular, it implies that the Jacobian of this J matrix or Jacobian matrix vanish. It implies that even if for such a singular point, even if this is non-zero, delta S can vanish. you see. So in general, this condition is not necessarily equivalent to this condition. So even if the transformation is invertible, but still singular, not regular, you see. In that case, even if the transformation is invertible, new dynamics can appear because of this feature, or because of delta x vanish for this singular point, not from this vanishment of these variations. Okay. This is a main finding of our paper or this talk. Okay, so let's move on to the simple example of such an appearance of the new dynamical degree of freedom from the singular but invertible transformation. Okay. So let's consider the simple analytical mechanics system with just half of the q dot squared. Okay. This is nothing but a free particle, and from the variation of the action with respect to q, we can get the second derivative q vanish. So we have this simple solution, just initial position and initial velocity. We have two initial conditions. So two phase space degree of freedom, which is nothing but one real space degree of freedoms. Okay. And now let's consider the singular but still invertible transformation of the variable capital Q and the small q. Okay. This is a transformation. Okay. And you can easily see that there is a one-to-one correspondence for small q and capital Q, given the phi dot. Okay. And the Jacobian, as is expected, Jacobian vanish at capital Q equals 0. Okay. But still, this is invertible. And just plug into this relationship to this original actions. You see, just this relationship in this one, original action. And then we can get these two equations for Q, capital Q and phi. And if J is non-zero, which implies that if we choose a regular branch, of course, Q double dot equals 0, which is nothing but the original system of dynamics, completely equivalent, as we explained. But we can also choose singular branch with J equals 0, which is nothing but the Q equals 0. In this case, you see, small q equals phi dot. So just plug into these equations. Equation motion is nothing but the fourth derivative of phi vanish, rather than second derivative q vanish. It implies that we need four initial conditions, four constant, which implies that the four phase space degree of freedom or two real space dynamical degree of freedom. So now new degree of freedom appears in addition to the previous one real dynamical degree of freedom, even though this transformation is invertible. This is, you see, what we found. It's in some sense quite strange. Transformation is invertible, which implies in some sense one-to-one correspondence, but number of the dynamical degree of freedom is increased. Okay, and let's move on to the another example. Sorry, before going to the example, we have discussed what happens through the action level. Okay, to investigate such a future in the action level, first, this is the original action with respect to small q, nothing but half of the q double dot. And plug into this transformation into this actions, we get this one. Okay? And this action can be rewritten by introducing the new parameter theta and lambda. This is just a Lagrange multipliers. So if we take a variation of this new action with respect to lambda, phi dot equal theta. So plug into theta equal phi dot, it recovers the original action. Okay. And this action has a kind of the gauge symmetry. So if we define the gauge invariant quantity q bar like this one, this action is also rewritten like this one. Okay. So even in the action level, you can easily think that if we take a variation of the action with respect to delta q, we have two choices. lambda vanish. This is Lagrange multiplier vanish or capital Q vanish, which is nothing but a Jacobian, you see. Previously just noted, but denoted by J. So if we choose a regular branch with this Lagrange multiplier, plug into this one, nothing but the original action. This is kind of the regular case and completely equivalent to the original action and the dynamics. On the other hand, if we choose a singular branch with k equals 0 or Jacobian, vanishing Jacobian case, just plug into this one, it means that phi dot equal q bar. So this action is nothing but phi double dot squared. You see, originally we have a first order system q double dot squared. So we have one real dynamic degree of freedom. But now if we choose a singular branch, this is nothing but phi double dot squared, which has a 2 degree of freedom. You see, this is the essence of the essence. How number of the degree of freedom is increased, you see, in this system, even though the transformation is invertible. And now we are going to introduce yet another interesting example, which is a singular but invertible transformation. Okay, so in the previous example, we considered only q dot squared. But now we at not only q dot squared, we consider not only q dot squared, but also half of the phi dot squared. So this system equation motion can be easily obtained by variating the action with respect to q and phi. So nothing but q double dot vanish and also phi double dot vanish. So we need to arrange the 4 initial conditions, q naught and v naught and phi naught and u naught. So we have a 2 real number of the degree of freedom. And again, we consider the singular but invertible transformation of the variable. It is essentially the same in the previous one. Small q equal capital Q cube plus phi dot and phi equal phi. And of course, this transformation can be easily seen to be invertible because capital Q equal nothing but the square root, cubic square of the small q minus phi dot. So it's completely invertible. We can explicitly write down. Okay. And let's consider discuss the dynamics from this transformation again. So now original action is this one, not only q double dot, but also we have a phi dot squared and insert this transformation into this action. So we get this one. And by taking the variation of the action with respect to capital Q and phi, so this case, we get not only q double dot, but also this part, you see. And in case of the regular branch, which implies that the capital Q is non-vanishing or Jacobian non-vanishing. In that case, again, we recover the original dynamics. Just the equation motion is q double dot vanish and phi double dot vanish. So we need a 4 initial condition. It implies a 2 real dynamical degree of freedom. So as is expected, for regular branch or regular transformation, if the transformation is regular and invertible, no physics is changed. It's essentially the same. On the other hand, again, if we choose singular branch with q equals 0 or vanishing Jacobians, something interesting again happens. So in this case, again, small q equal phi dot. So plug into this relation into these equations, we get this equation motion. Okay. So this equation motion can be easily solved. This is the analytic solutions. Okay. And still we need to arrange the 4 initial conditions. So it implies that the 2 dynamical degree of freedom. So in this case, number of the dynamical degree of freedoms is still unchanged, still 2, you see. But again, dynamics is new dynamics, completely different new dynamics appears, you see. Original dynamics is 2 free particles. On the other hand, we have now one, you see, accelerated or constrained system in some sense, accelerated systems. So this is number of the degree of freedom remains unchanged, but the dynamics is completely different or changed. So physics is changed. You see. So depending on the given action, even if we consider the same transformation, number of the dynamic degree of freedom can be changed, or dynamics of the physics is changed. You see, this is a quite interesting feature for the singular but invertible transformation. Even though transformation is invertible and there is a one-to-one correspondence. Okay. And now we discuss, up to now we discussed a very
Sorry,
simple.
can I ask a question?
Yes, please.
Okay, so I think it's a good time to ask a question. So about this
Yes.
particular example you allude, I have two issues. First
Yes.
is that in the original field variable space and the new transformed one, you do have a non-local relation in time.
What do you mean the non-local relation? Or just
For example, in the equation in the bottom here, small q. Yes, I'm explaining. Small q is capital Q plus phi dot. So if I want to express phi in terms of small q and capital Q, that involves all the non-local the information of the Q variable and capital Q variable. Right. So you just integrate over time to get the phi at some particular instance t. That it requires all information of Q at the past and future to infinity.
It depends on your definition of the time, because in this case, you see, transformation is simply this one. So given the phi dot or at some point, and Q is given at any point, capital Q is uniquely determined. We don't need such information globally.
No, so let's try to invert the phi, small phi dot, small phi in terms of capital Q. Okay?
But in case of phi, we don't change. Phi is phi.
No, what I'm saying is that so we want to express the phi in terms of the information of capital Q and small q, right?
Yeah, but we don't need such information for transformation from capital Q to small q.
Okay, but anyway, what I'm saying is that the Lagrangian is expressed in terms of the small q and small phi as well, right? So you do need that information. Yeah. What I'm alluding is that
it depends on the definition of the transformation. But as long as we define small q and phi system, and the capital Q and phi system, you see, it's locally invertible.
Locally invertible
given such information,
not in terms of phi. Not in terms of phi. That's what I'm saying. No, it's not.
Of course, phi dot is necessary. Yeah, but phi dot at some particular time is enough.
Yeah, so
we don't need a global information.
You're dealing with the phi, not phi dot. That's why I'm saying you have more degrees of freedom, right?
Well, degree of freedom phi. Yeah, in some sense. Yeah, and this is the essence. Yeah, you are right. Yeah, if we define that transformation is not just a phi dot, if this part is phi, this kind of new feature never appears. I agree with you. This is
that's right. So that's right. So phi and Q relations are non-local in time.
It depends on the definition of the non-local, because we don't say.
I gave a precise definition. The non-local depends on all other moment of the evolution.
But we don't need an evolution because this is a transformation.
Whatever you do, I mean, you're looking at the dynamics. That's what you're after.
But the transformation itself is not dynamics.
No, but why do you do the transformation? After all, the physics is not transformation.
Yeah. So
of
course, we are going to discuss the dynamics, but I just say transformation is not dynamics, and we don't need a global information.
I'm saying that you do need the global information, that transformation itself.
Why?
Okay, so that interferes with dynamics. The second complaint is that this one, even if your original system has a time reversal invariance, this is not. Okay, so this system is
because the dynamics is different. Yeah, because dynamics is different. Yeah, sure.
Okay, so,
By the way,
so that's
Masahiro,
not
may
consistent with the original symmetry of the system, unless you impose additional transformation of the phi field on the time reversal transformation.
Masahiro, I'm sorry, may I interfere and just comment that if the transformation between small q and large q were invertible, in that case, phi dot would be purely a gauge degree of freedom. So we don't need this information at all. Think about this in these terms. So this phi dot, if, for example, the relation where q small is equal q large, let's say plus phi dot, in that case, we don't need to know anything about phi dot because this phi dot would be just purely a gauge degree of freedom. Sorry for interference.
No. Yeah. Thank you very much. Yeah. Thank you for clarification.
No, that's okay. So that's okay. So sequel to that comment, then why the degrees of freedom change then?
Because such a gauge degree of freedom is in some sense enhanced into the dynamical degree of freedom. Yeah.
No, I thought that the comment just said is that by gauge degrees of freedom is a redundant one. It's not an independent degrees of freedom, but it's the equivalence of the dynamics.
No, he said if it were invertible. That was the comment by Vic.
Yeah.
So I think since this discussion is not important, I think for the rest of the talk, maybe we can postpone it to the question session or to the discussion session, and we can let Masaida finish the talk. Okay. So please, Masaida, you can go.
Yes. Okay. Yeah. So just we are going to give some simple example on the more gravity or cosmology community. You see. So we are going to discuss now so-called mimetic gravity. You see, which in which some new dynamical degree of freedom appears as dark matters. So which was originally proposed by these peoples. And the idea is quite simple. Let's consider some seed action or original action given by the metric G and some matter field. Okay? And now they consider some singular transformation with conformal invariance given by some this conformal invariance and characterized by H and phi. Okay? And transform the system is now described by in terms of H and some matter field with new dynamical degree of freedom of phi, okay, which is constrained by the conformal invariance. So through the in the transformed system, we have only to, in order to investigate the dynamics, we have only to take the variation of the action with respect to H and phi, okay? And which gives the gravitational equation, including the new dynamical freedom and its equation motion itself. And as a concrete example, they took this Einstein-Hilbert action as a seed action. You see, just a simple Einstein-Hilbert action plus matter action. And as a transformation, singular transformation, G mu nu is given by this one. Okay. And in this case, transformation is non-invertible, but singular. Okay. And this transformed system is now described by H mu nu and the matter field with this new dynamical degree of freedom phi. So if we take a variation of action with respect to H and phi, we can easily obtain the equation motion for H and phi through these relationships. Okay. So in case of the Einstein-Hilbert action, as a seed action, calculation is quite simple. Just transformation of the action, seed action with respect to G is nothing but a standard Einstein equation motion. But this G is consists of the two parts, delta H and delta phi. So if we take a variation of the action with respect to H and phi, we get the additional term from the not only the original Einstein-Hilbert Einstein equation part, but also this additional part. Okay, so as an additional part, this behavior, if we describe this term in terms of the standard energy momentum tensor, this is nothing but dust. So this is the reason why dust or just a dark matter candidate can appear in this context. Okay? And this is the original idea given by these people let's consider the Einstein-Hilbert action and consider some singular transformations, which is not invertible, but with conformal invariance. Then if we consider the dynamics with respect to H and phi rather than G, in addition to the standard Einstein equations, we get the additional matter which behave like dust or dark matter. Okay. And this transformation has a kind of the trace part of the this equation motion is a trivial satisfied and constrained. And then what's the essence of mimetic gravity? Okay, so why dust-like particle or dark matter candidate appears in this context? You see, and what we found is that the singular behavior of this transformation is crucial. You see, people try to investigate to change the original action or the transformations. And what we found that irrespective of the seed actions, appearance of the feature of the newly degree of freedom is completely fixed by this transformation itself. I'm going to explain step by step. Okay. So now we consider the so-called disformal transformation in general, you see. And to check the invertibility of this transformation, as is usual, we have only to consider the Jacobian and its eigenvalue and eigenvectors. So in this case, Jacobian matrix is given by this one, 10 by 10 matrix. Okay. And in order to investigate the singular behavior or regular behavior of this Jacobian matrix, we have only to investigate the eigenvalue and eigenvector. And in this case, 10 by 10 matrix. So we in generally, including the degeneracy, we can have 10 eigenvalues, you see. And we can easily find that C is this coefficient or conformal factor is an eigenvalue for this matrix through the dynamical calculations. And the eigenvector is given by, characterized by this one, which has just one constraint. So 10 component and one constraint, so we have 9 eigenvalues. Okay. But if we impose that this physical matrix is has an inverse matrix, so it implies that C shouldn't vanish. You see, so from the physical argument or physical requirement, we require that this coefficient, this eigenvalue, should not vanish to guarantee the inverse, to guarantee the presence of the inverse matrix. Okay, and yet another interesting eigenvalue is given by just by through the direct calculation. You can easily verify that this is the eigenvalue for this Jacobian matrix, and the eigenvector is given by this one, and the dual eigenvector defined by this one is also given by this one. Okay, so once we assume that this eigenvalue does not vanish, you see, so singular transformation is characterized by the requirement of the vanishment of this eigenvalues. Okay. Of course, mathematically, this can vanish, but we don't take such an option through the physical, from the physical argument. Okay. So this is a definition of the singular disformal transformation in our context. This eigenvalue vanish. Okay. And the consequence of this kind of the singular transformation again. So original idea of the mimetic gravity is given by this one. Let's consider the seed action, which is described by the original metric G and psi. But now let's consider some disformal transformation through the G to the H and phi. And what's the dynamics for H and phi? So we have only to take a variation with respect to this action. We have only to take a variation of the action with respect to H and phi. And for H, it's given by just this chain rule. Okay. And as we discussed, if this Jacobian matrix is regular or it doesn't have any zero eigenvalues, this two dynamics is completely equivalent. If this vanish, and opposite true. On the other hand, if we consider to take a singular branch, just a Jacobian vanish or some eigenvalue vanish, in that case, in this relationship, we can have always freedom to add this dual eigenvector with vanishing matrix, vanishing eigenvalues. Because even if we add this part through the definition of the this vanishing eigenvector, dual eigenvector, this vanish, you see, through this relationship by definition, because lambda vanish, so this vanish. It implies that the equation motion is modified with this additional part. And exactly in the original mimetic gravity, this eigenvector corresponds to dust, or you see, pressureless matter, and serve as an additional matter. Okay. So you can easily see that given the transformation, and if we can specify the zero eigenvalue and with some dual eigenvector, this dual eigenvector with vanishing eigenvalue completely fix the feature of the additional matter. Okay. And then this is the reason why the mimetic gravity or proposed by these people includes the dust matters. So we can deliver the two important messages. The property of the mimetic matter is completely determined by the dual eigenvector with vanishing eigenvalue of singular transformation. You see, originally, as far as we know, it has been supposed that the non-invertibility of the transformation is essential to realize the mimetic gravity. In some sense, this is true, because at least in the original example, discussed these people, this transformation is non-invertible with conformal invariance. It's true. But non-invertibility is not necessarily, how to say, inevitable or essence. What we found is that the singular behavior is more essential to obtain the additional degree of freedom. Okay. Of course, many cases for singular transformation, it's non-invertible. But this is not always the case. We have already shown, and as we will show, you see. We can consider the singular but invertible transformation. At least, you see, as we have shown in the previous analytical mechanics examples. And in our case, this is again the Jacobian matrix for the generic disformal transformations. And now we require that this eigenvalue vanish, you see, because we have additional 9 eigenvalue with C, but from the physical argument, we require that this conformal factor should not vanish. So only choice we can take is this eigenvalue vanish. And if this eigenvalue always vanish as a function, we can solve this relation for form of the D and C. But for our purpose, we have only to require just this eigenvalue vanish for some configuration phi, which implies that in some sense, this is nothing but just interpreted as a non-trivial equation motion for phi, which may be used to determine the behavior of phi or dynamics. So just we can give the very simple concrete example of the mimetic gravity with invertible transformation. This is still singular transformation, but invertible transformation. We can explicitly give such example. This is a bit complicated. Just using the simple example y equals x cubed in the same in the previous example, we construct some transformation which is singular but invertible transformation. So what we found is that the essence of mimetic gravity, you see, in which the new dynamical degree of freedom appears. And in the original model, of course, the transformation is singular and also non-invertible. But the non-invertibility is not necessarily inevitable. You see, a singular behavior is sufficient to realize such a scenario of the mimetic gravity or to increase the number of the dynamical degree of freedoms. Okay. So let me summarize my talk. As you know, in mathematics and physics, transformation is ubiquitous. And among them, invertible transformation is special because there is at least locally one-to-one correspondence between the old and the new variable. And we classify transformation into the regular and a singular transformation. And the regular transformation, which implies that the Jacobian is non-vanishing at some point. And the famous inverse function theorem guarantees the local invertibility for such a regular transformation. And the two dynamical systems are completely equivalent as long as two systems are connected through such a regular transformation. On the other hand, singular transformation, which has a vanishing Jacobian at some point, can be either invertible or non-invertible. Both cases appear. And we have already shown that singular but invertible transformation can change the number of the dynamical degree of freedoms, as well as the change of the dynamics, even if the number of the dynamic degree of freedom remains unchanged. And we also construct some concrete mimetic example as application with singular but invertible transformation. Thank you very much.
Thank you very much, Masaida. This is very interesting talk. So yeah, there is already a question from Verno. Sergey, please.
Yeah, please.
Thank you for your talk. You change number of degree of freedom. You get some new degree of freedom. They are standard or ghost degree of freedom.
Yeah, but it depends on the you see original action. This case, original action has a healthy degree of freedom, and the new dynamical degree of freedom is a ghost because essentially it's just a phi dot square. But if we, for example, begin with just a q square, not a q dot square. So in case of q squared, original action has no dynamical degree of freedom, just 0. And the new dynamical degree of freedom is nothing but the phi dot square. So it's completely regular or healthy degree of freedom. So healthiness still depends on the action we consider.
Yeah, what in your example about mimetic gravity, what happens?
Mimetic gravity case, this case, as far as I remember, newly degree of freedom is nothing but a dust. Yeah.
Thank you.
Please, any other question? Actually, I have a question, Masaida.
Yes.
It's more a curiosity and to know your opinion. So basically, what you've shown, of course, is how this transformation change. What are the effects of this transformation at the level of the action and just at the classical level? But for instance, if you want to do quantum physics, we should look at not only at how the action transforms, but also, for instance, in a path integral, how the measure transform. Have you already thought about that? How this singular invertible transformation?
Of course, it's a quite subtle problem. And if we try to formulate quantum theory through the path integral, and if we make a change of the variables, we have to take into account the Jacobian as a change of the measure. So in this sense, if we choose a singular point, by definition, Jacobian vanish. It implies a measure vanish.
Yes.
So in the standard formula of the formulation of the quantum physics with path integral, of course, strictly speaking, you see, in Lorentz signature, it's not yet mathematically well defined. But if we take it as it is, you see, standard one, unfortunately, this transformation is a measure there.
Mm-hmm.
So in this sense, you see, still as a classical mechanics, it's interesting, but as a quantum physics, probably it's measure zero and it does not contribute much.
I see.
I'm not sure, you see, as long as before path integral formation is well mathematically defined, I cannot say definitely, but just as, you see, naive argument of the Jacobian or change of the measure,
would
this
be just
transformation is by definition, measure zero, because the Jacobian vanish. So unfortunately, I expect that in the quantum physics or quantum mechanics, this kind of solution with dynamics appears with measure zero, probably.
Okay.
This is my guess.
Okay, thank you. Do you have some more questions, either in the chat or and just pick up on Zoom? Okay, if not, let's thank Masaid again.
Thank you very much.
And we'll meet again for the discussion session.
Yeah.
At the end of this session. So we can move to our third speaker of the day, Alex Wickman. You are muted, Alex.
So hi everybody. So can I share my screen? Let's see. Not yet. I'm still. I don't have a permission to share.
Alexei, can you make Alex
permission
pause?
where? Hi Sasha, by the way. Where do
Hey,
you want me to give you permissions? You are a co-host.
No, he's not.
No, you have to make him co-host.
There are two Wickman things.
There are two Wickmans.
No, one disappeared. One.
Okay, you disappeared.
Okay, yeah.
Why did you disappear?
My phone managed to log out, so it's okay to leave the meeting.
I mean, we're serious here. You disappear means you're gone. I mean.
Yes. Perfect. Okay, let me now see. Okay, perfect. So do you see it now?
Yes, we see it very clearly. Okay, so it's 9:43 here. I think we are perfect in time.
Yeah.
Anyway, so I guess, sorry?
You can wait for 2 minutes if you
No,
want.
no, let's start. I think it's fine. It's better to be always more in time. Yeah, so
we'll get extra 2 minutes if we start now.
Okay, so our first speaker is Sasha Wickman from Seiko, and he's gonna tell us about living maybe living with ghosts is not such a bad thing. And please, the stage is yours.
Okay, guys, it's great to be at this conference, even though that it's on Zoom. It's still great to see you all. And I'm going to tell you about our work, mostly which we published last year, but actually there is some continuation. And you see, it's living with ghosts is kind of sometimes could be unpleasant and could be strange. There could be a lot of surprises. But what I'm going to tell you, it's about actually stable living with ghosts, which is more interesting. So maybe full of surprises, but in a stable fashion. And you see, I got inspired in the title of this talk, which I changed from the program. Sorry for taking this decision. So I got inspired by this paper by Stephen Hawking and Thomas Hertog. And the paper was called Living with Ghosts. And as this conference is about quantum gravity, I think this is kind of appropriate because the paper starts from the following statements. The perturbation theory for gravity in dimensions greater than 2 requires higher derivatives in the free action. Higher derivatives seem to lead to ghost states with negative norm. So what I don't like is states with negative norm, because I'm really in favor of unitarity and proper quasi-classical approximation. So therefore, what I'm going to tell you is about ghosts which are states with negative energy. And therefore, in some sense, it's not that kind of living with ghosts as Stephen Hawking and Thomas Hertog are proposing. But instead, what we are doing is these negative energies. And most of my talk will be based on this paper in PRL published with Cédric Defayer and Shinji Mukayama. And you see the archive number is almost like 1.5 years old now. And stay tuned. I think in next maximum 2 weeks, we will publish a continuation with analysis of a much larger class of systems which are stable. And I will explain stable in which sense and what are the ghosts and everything. And feel free to interrupt me at whatever time, you know, it's okay. Okay, so people are interested in ghosts, so there are some other options on the market, and most of these options are actually less stable than our discussion. So one paper is by Thibaut Damour and Andrei Smilga, and there they were brave enough, so much braver than us, to consider ghosts which are benign. And they denoted benign behavior such that the systems can develop instability, but this instability does not lead to any singularities. So basically, the system for Thibaut Damour and Andrei Smilga is benign if it just evolves, maybe indefinitely in time, let's say even exponential instability, but nevertheless, there is no singularity, there is no pole-like behavior there. Then there is an approach closer to what we are doing. It's this paper on the upper right corner, where people were discussing that systems with ghosts could be metastable. So in a sense, there are some arguments which are based on perturbation theory and on numerics that actually it can take enormous amount of time to develop such an instability. Okay, but it's still never clear, you know, how to properly know whether the instability is still there or not. Another, I think, important comment is regarding this Thibaut Damour and Andrei Smilga paper and Smilga's activity on benign ghosts, because it's not the only paper he published on that, is that, you know, one could think that, well, having some field evolving, like basically constantly growing, let's say, without any bound, is kind of pathological, but we should think about our own universe, which expands, and, well, we don't see any, actually it expands now even with acceleration, and we don't see any limit for that. So in a sense, this is an example of instability itself, or if you want, such a benign instability. Okay, so now let me briefly mention at least my set of thoughts, and probably kind of truly not complete list of thoughts. Why are we interested in ghosts? So first point is very, you know, practical. So these ghosts can give you interesting cosmology. In particular, very practical points, the ghosts can give you phantom dark energy, which is a super accelerated universe with growing Hubble parameter. And this is what is actually still allowed by observations. And I suspect it will be always allowed by observations, especially if the true cause of acceleration is just cosmological constant, because observational window will be just more and more narrow around -1 for equation of state parameter. And of course, there is no way to exclude W less than -1 in that case. Then there is bouncing universes. This is very interesting regarding early universe. You know, they could precede inflation or maybe even be alternative to inflation. And it's very interesting from the point of view of understanding of ensembles and early universe dynamics and initial conditions for our universe. In particular, it's interesting whether we do need quantum gravity to describe early universe or not. Because you see, usually, if you trace inflation back, then there are actually strong statements that there is a singularity, even though recently they were put in doubt. But, you know, if you can have a bounce, then you don't need to go to singularity. And singularity, of course, is a strong coupling for gravitational system. So this is a true quantum regime. Okay. So on the other hand, one could manufacture inflation with blue spectrum and gravitational waves, which could be also interesting for different reasons. So these are like phenomenological reasoning. Then more ideological reasoning is why actually normal equations of dynamics are F equal ma, right, and not m, like some whatever, some lambda, and then parameter which is usually called jerk, like let's say a dot. Okay, so it's a kind of ideological equation, and the point is that high derivative systems have ghosts due to the famous Ostrogradsky theorem. And I'm embarrassed to say that it's a very old theorem, it's 1848. And yeah, so basically this is ideologically interesting why the dynamics is not supposed to be higher order. Or maybe it was, but it is supposed to be, but what to do with this? Then another reasoning is a more mathematical one. Forget about describing true degrees of freedom in some, so to say, mechanical sense. But let's think about more general sense of dynamics. And in particular, in circuits, actually third derivative equations of motion, it's the smallest setup in which you could demonstrate chaotic behavior, okay? Because you need 3 dimensions to induce chaos. And actually, it is realized in electric circuits where you generate basically, where you make random generators, like basically just what is called Chua's circuit. And this is basically higher order equations of motion. Okay. Now the question is if such things really are there, at least in engineering, right? Then maybe this is also interesting to have this analogy. Then for this conference, I think the major point would be renormalization or quantization of gravity. And this is very old result, basically published before I was born, surprisingly, by Kelly Stelle. And the statement is that if you include these higher derivatives, including wild tensor, what is crucial here, and Ricci scalar squared, in that case, gravitational theory becomes renormalizing. Okay. Of course, the problem there, it's done in Euclidean. It's not entirely clear what to do. And as we know from Ostrogradsky theorem, this thing should have ghosts. So basically, it should have states, local states of negative norm. Or better to say exactly what I'm doing, negative energy. Okay. Then the equations related to entropy and thermodynamics, because you see, if you allow kinetic energies unbounded from below, and that's what the ghosts are, as I will show you in a second. Or if you allow negative masses, in that case, the equations related to negative temperatures and so on, and stability of such systems in general. Then, if you allow for negative energies in gravity, localized kind of energies, then it's a question whether it's possible to screen gravity. Especially it is clear, imagine, if you think in terms of normal Newtonian treatment, you take particles with positive masses and particles with negative masses. Particles with negative masses, not imaginary masses, so not negative m squared, but really negative masses, they are ghosts, okay? And then Newtonian gravity would be much closer to normal electrodynamics, where you have positive and negative charges. So now our whole technology, our whole civilization, if you want, is now based on the point that we can screen electromagnetism. Because otherwise the forces there would be enormous. So we use only a very small fraction of electromagnetic force there. So the question is whether it's possible to screen gravity, whether such things exist at all, or at least feasible from the theoretical perspective. And then this is deeply interrelated to the point that where, we have this huge elephant, this cosmological constant problem, which we don't know how to even estimate. And it seems that, having negative energies floating around would help you to screen cosmological constant. Or if you want, screen energy appearing from the quantum vacuum. Interesting to think whether it's true or not, whether it's possible. So therefore, such ghosts could be an interesting contribution there. And last but not least, it's a question related to can gravitons be massive? Because as you know from the old construction, even early, much earlier than I was born, 1972, by Boulevard and Deser, that simple assumptions about massive gravity would lead you to ghosts on nonlinear level. Okay, this was kind of recently avoided by the RGT construction, but it's important that there it's avoided only on Minkowski. And if you go to any other interesting background, like say cosmology and so on, then these ghosts are back. Just you keep the number of degrees of freedom, but just some of them become ghosty. So then it's very interesting. So what to do with them and whether it's relevant or not. Okay. So let me refresh you Ostrogradsky theorem. So first of all, I will tell you what is Ostrogradsky theorem for poor people, modern version. So you take a propagator. Suppose this propagator contains not only p squared but also p to the 4 term. And then the point is that you can expand this propagator, suppress all the indices, all these polarizations, everything. And then in this propagator, you can write it as two propagators, which are just standard one up to this minus sign, okay? And this minus sign, many people try to interpret either as negative energies or negative norms. So if you really want to keep correspondence with quasi-classical physics, so basically think that the equations we should derive through variation of the action have anything to do with your quantum description. And in that case, yeah. Zhao, you want to ask something? There was a raised hand.
Yeah, maybe it was by mistake.
Okay, no problem. So basically, the point is that if you want to keep this correspondence, then the only way to interpret it in terms of normal correspondence between classics and quantum is to say that this minus induces negative energy. Okay. And well, let's see, it's a gentleman who actually derived, of course, a theorem not in this form, but he derived actually in this nice paper. As a true Russian, he was writing everything in French. And what was bad for him, he was writing, everything in French. He was able to read in French, but he didn't know English. And therefore, at this time, he was not aware of works of Hamilton. So actually, in this paper, what my French collaborators are saying, he really basically reinvented without knowing whole Hamiltonian mechanics, but somehow for generality, he decided to do it immediately from high derivative systems, which is quite also an interesting statement. So simple version of what was he doing can be explained in just 3 lines. So suppose you take a Lagrangian, which depends on acceleration, okay? Formally speaking, nobody precludes you from having such a system. So Q2 dot is your acceleration. So now, what is non-standard in this construction? So you choose your first coordinate to be just Q, which is pretty natural and would not face any equations. And as we know from a normal situation, where this Q2 dot term is not present, you think that the conjugated quantity to Q would be related to velocity of Q, namely to Q dot. However, what appears in the Ostrogradsky construction, that the canonically conjugated quantity to this Q is actually P1. And this P1 is basically a function which depends on Q3 dot. So in a sense, Q is not conjugated to Q dot, Q is conjugated to a quantity which is Q3 dot, okay? And then the quantity which used to be conjugated to Q, namely Q dot, is now your second degree of freedom, namely Q2, and this Q2 is logically actually conjugated indeed to its own velocity, namely to P2, which is dl over dq2 dot. So basically, with respect to Q2, there is a normal order of events, so they are properly conjugated, right, to each other, whereas introduction of Q2 dot breaks the conjugacy between Q and Q dot. So now you can still form Hamiltonian in the very same way as usual, so P1 Q dot plus P2 Q2 dot minus Lagrangian. However, now you see what is important. Your Q1 dot is Q2, and Q2 dot you can express in the usual fashion through P2, right? So therefore, what happens? So your whole Hamiltonian is just linear in P1, okay? And because you have this term P1 Q2 plus P2, then acceleration, and this acceleration you solve from inverting relation between P2 and acceleration, and therefore it does not depend on P1. And then in the Lagrangian, because it was Q1, Q2, and then acceleration also is P1 independent. So basically your Hamiltonian becomes linear in P1, and that implies that this Hamiltonian is unbounded from above and from below. Okay, so of course you have more degrees of freedom in these high derivative systems, which is completely fine. That's no problem to have more degrees of freedom. You will need to provide them initial data, that's true. But what is more important is that is necessity, your Hamiltonian becomes unbounded from above and from below. Of course, here one could play different tricks. For example, one could think that this P1 is living, let's say, maybe in compact space. Suppose it's kind of angle, right? In that case, for example, this instability may be not that bad, but usually it's considered to be pretty dead thing. Okay, now let's look at field theory and let's make a mechanical analogy. So let's take normal oscillator, like normal mechanical oscillator, simplest case. So it's given by standard formula. Then let's look at the action, let's say, of cosmological perturbations. So this action would have two free functions, Z and CS squared. So if you go to modes, what we will see is that for each mode, you can write a Hamiltonian because it's a linear system. The modes evolve separately, independently. And you see that this function Z corresponds exactly to the mass for mechanical oscillator, whereas their frequency of the oscillator corresponds to the sound speed squared multiplied with K squared. Okay? So now, if you're equipped with this analogy, I think I'm saying something what you all guys know for a long time, is that there are two types of instability which could appear there. One is a gradient instability when the potential of the oscillator is inverted. And this is quite a bad thing because this causes your perturbations to grow exponentially with the rate of instability proportional to K. It looks completely deadly, in the sense that this appears already in the linear analysis. However, there are ways to kill it if you work on effective field theory grounds and if the sound speed is very small. So basically, for small imaginary sound speed, one could get corrections from dispersion relations, and sometimes in terms of kind of still single field effective field theory, you could kill it, this instability. There are explicit two-field examples how to do it. Basically, UV completions through a complex scalar field, what we worked out with Zhenya Babichev and Sabir Ramazanov, would allow you to see that in some cases, imaginary sound speeds are okay. But it causes you new dispersion relation. Then there is another thing. You see, this gradient instability, you just see literally in linear analysis, you know the rate modulo, basically trying to change your dispersion relation for K higher than something. However, there is another instability, which is actually instability caused by the negative mass or negative Z function. And this you can only see if you bring the system to interactions, right? And the simplest estimation you can do, you are motivated through gravity. Let's suppose that this Z is, roughly speaking, 1 by absolute value. Sound speed is, roughly speaking, 1 by absolute value. And in that case, you can be sure that this R would be actually coupled through gravity to, let's say, photons. Okay? And most naively, the cubic interaction vertices, each of them goes like 1 over m Planck, right? So you can think that they talk to each other, these two energy momentum tensors, through G Newton, right? So therefore, the amplitude goes like 1 over m Planck squared. The real rate, the probability, goes 1 over m Planck to the 4. And now if you ask for the probability per unit time per unit volume, it has to be dimensions 4 in the mass. So therefore, you would need to put some dimensionful parameter, let's say lambda to the 8, where lambda would be your cutoff. Here, what is interesting, usually cutoff is implied on loops. Here, you would say that it's a physical cutoff on external legs, which is not a very standard procedure. And it's caused by the very, very simple point that it only makes sense to calculate it in perturbation theory if you manifestly break Lorentz. And you see, this rate is dominated by your, the stronger is the cutoff, the more it is dominant, right? So the larger is the effect. So basically for higher frequency modes, this effect is stronger and stronger. And you need to break Lorentz even on these very short scales in order to be able to calculate it. Otherwise, you also need to calculate all boosts. And integrating over boosts will give you infinity. And this is kind of similar to vacuum decay rate. So basically the statement is either you assume the breaking of Lorentz invariance in hard UV up to your UV cutoff of the theory, or you don't know the rate, because clearly either you need to forbid such situations by just physics, saying that it's completely wrong and should not be there, or you need to say that your methods of calculations are not appropriate for this, basically for estimating this quantity. So basically, I think more fair is to say that you don't know the rate of production of such objects. Here, I think it's very important analogy that normal mechanics kind of does not differentiate too much between momenta and the coordinates. And if you allow potentials, which are unbounded from below, it's well known that there are options for tunneling, right? And this tunneling rate is considered to be now finite. Taking analogy between P and Q, why cannot you have also unbounded kinetic energies there? I mean, unbounded from below. So why would it cause such a huge difference? So the key point here that you see this effect, you cannot calculate without interactions. And basically how it works, it looks like the scissors, you know, so where you bring ghosty matter and normal matter as two parts of your scissors, the interaction conserves the total energy. However, as time passes, the scissors can open up, and actually they can open up as much as you want, because the ghosty matter decreases energy, normal matter increases energy, total energy stays constant, and it all depends on this nail, which couples both parts of the scissors, on the interactions. So that gives you hope that, you know, if it's that important, what kind of interactions is there to really say anything about this instability, then maybe one could look at such interactions when it is stable. Okay, so let me give you an example, a simple mechanical example. How unstable can it be? So let's take normal oscillator. Let's take.
May I ask you a simple question?
Sure, of course.
I'm just curious, the scissors which you just presented, doesn't it mean that the spin in between assumes a heavy fine-tuning of your system?
Wait, say it again. The spin having fine-tuning, or
yeah. Does it mean you showed just scissors like normal matter, ghost matter? Doesn't it mean that you need a very severe fine-tuning in your system?
That's a good question. Actually, I don't know, but you will see that it's not that severe fine-tuning in reality. That's an interesting statement. But in some cases, maybe you need it. In some cases, maybe you don't need it. But it's a good question. I don't know. Especially taking into account gravity and universality of gravity interaction, I actually have no idea what is the rate of instability there.
Yes, kind of impossibility to avoid interaction through gravity through the square root of minus g. But I guess you don't couple to gravity yet.
Not yet. And I will actually not consider it because, you see, even for normal field theory, it's not known what the rate is with simple interactions. Okay.
Yeah.
Let's say you take normal one and you take a ghost, you take quartic interactions, nobody knows. And another point is that you see the old story of massive gravity with Boulevard Desert ghost. That's very important that this Boulevard Desert ghost appears only non-linearly. Non-linearly means that you need to have some background in a sense to see it, right? But it's still a degree of freedom. But this background then would break Lorentz in some sense. And so I'm not a big specialist and not a big fan of massive gravity, but surprisingly, even for this very old problem, there is no reliable, at least to my best knowledge, no reliable instability rate estimation. So basically, most people would just dismiss it. And especially for gravity, it's a very tricky business because, as we know, just diffeomorphism invariance would force you to have total energy to be zero in the bulk. And it's on one hand, right? And on the other hand, it's not even clear what does it mean to have localized energy for gravitational system. And the whole thing will persist if you increase number of degrees of freedom there. So that's a very, very tricky calculation, you know.
Okay, thank you.
Okay, and you see, I would be very happy to be able to perform it, but I don't know how to do it. So, but let's first understand what can happen with two oscillators, one of which is a ghost. So let's couple it quartically. And here, it's a very important statement already to make, that if these two oscillators were normal one, and you would introduce this quartic coupling, the system is chaotic. So in a sense, it's not that easy to predict what will happen even with two oscillators with quartic coupling, right? But let's make life even more complicated and take one of them to be a ghost. So in that case, what you can do, let's take this coupling constant for simplicity of calculation. You will see what the other reason to be pretty large. Let's say it's 4, okay? And let's take the frequency of the ghost to be a bit higher than the frequency of the, let's call it observer, and basically the normal oscillator. And this frequency we take 2.3 just, to avoid resonances and so on. And as you see, it takes you, like roughly speaking, 10 periods of oscillations for the normal guy to see onset of pretty strong instability, which looks like a parametric resonance. So basically, what is depicted on this plot is time in units of frequency of first oscillator, and then it's the energy of the first oscillator. And actually, here I took the logarithm. So as you see, it grows like e power 10. Okay. And basically, after that, my code would crash. So therefore, it goes only worse. So, but what is very, very interesting here, so for this relatively large coupling constants, this instability is pretty strong. And by the way, initial data, I took, roughly speaking, a vacuum one. Okay, roughly speaking, vacuum estimation for initial data. So it's the best which you could have here. And for the same type of initial data, you can just decrease your lambda from 4 to 2.35, let's say. And suddenly what you see is that this dynamics of the system is ultra sensitive to this parameter. Because if before the instability would start, basically, roughly speaking, 10 periods of oscillations, now it's around 600 or some hundreds of periods of oscillations. And only after that, you clearly see this onset of instability. But it still appears. So why am I saying this? Because there are quite a bit of numerical studies of systems similar to that. And in many of the cases, people were claiming that you decrease lambda and you see no instability. But the point is, you don't know how long do you need to wait in order to observe this instability. And this is highly non-standard statement because, as you see, you need to wait for a very long time till the instability develops, but when it develops, it's super rapid. It's very fast and very strong. So this is probably a manifestation of the result by Nekharoshev. So I just recently discovered this paper. I probably better included the reference. And it's the result of, I think, also 1976 or 77, where he would estimate for small coupling constants, the effect of such cross-coupling terms, and of course, completely general setup as a perturbation. And then the statement would be that in some cases for action variables, it would take exponential amount of time to deviate from the models where it was basically integrable models. So basically the statement is you take integrable models, you calculate the dynamics in terms of, let's say, of angle action variables, you introduce some perturbation, and then you can ask the question when this perturbation would spoil your solution. And it turns out that the time can be really exponential. But after this time, as you can see here, the whole system would just be dead, okay? But it also implies that, it's very hard to estimate the time even for such a simple case. And that numerics is not very instructive there because you don't know how long do you need to wait. And it's very hard to estimate how long. Okay, so now let me show you our model where we don't have these troubles at all. Okay, we constructed it to be sure that it's really stable, and what we are going to show is that it's stable analytically. So let's take a Hamiltonian, super simple one. Again, normal oscillator, Gaussian oscillator, and we put them in interaction. Okay, normal interactions through potential, no high derivative, no nonlinear terms in momentum, nothing. So the only kind of unpleasant thing here is that this potential is not polynomic. It's not polynomial one. So it's basically 1 over square root of a polynomial. And the polynomial has this kind of peculiar form. It's a bit ugly, but not too ugly. And stay tuned, actually, in the paper with Aaron Held, Shinji Mukayama, and Cédric Defayet, we will provide you other examples which are actually stable and polynomial. So this will be very interesting. So the point is that in this potential lambda is a coupling constant, and what is kind of unusual about this potential that actually the interaction is bounded, okay? So if you take this coupling constant away, the function itself, it's always between 0 and 1. So now let's consider the case when the potential has a true vacuum. So basically I call it symmetric. So we take total potentials, this interaction one plus harmonic parts, and what you see, it's a kind of saddle, okay? And that happens for lambda less than 1/2 by absolute value. And what is surprising, what I'm going to tell you is the saddle point is actually the point when the system is Lyapunov stable, which is kind of non-trivial. Because as we know from Lagrange theorems, the minimum of potential energy is usually a position of stable equilibrium. So let's do simplest job. We just expand this potential and we see the frequencies. So the frequencies are 1 minus 2 lambda and 1 plus 2 lambda, I mean frequency squared. So you see that lambda less than 1/2 guarantees you that naively the system would be stable by linear approximation. But one should note that linear approximation is not enough because your kinetic energies are not positive definite, and because your system, I mean, the very point of this instability is that it's due to interactions. So therefore, of course, through just purely linear analysis, you cannot claim stability or instability at all. Okay. So now let's take another case when lambda is larger than 1/2. And this case corresponds to kind of two saddles. And so in a sense, if you want, the interaction potential introduces symmetry breaking, right? So now the origin is not your stable equilibrium. However, these two saddles are stable. And the interesting thing is, these two saddles are given by this formula, doesn't matter, you can look at frequencies. And what is interesting here that you see, I'm considering, let's consider a case when lambda is much larger than 1/2. In that case, these two frequencies would have a hierarchy. So basically the frequency of the ghost oscillator would be very small, and the frequency of the normal guy would be very, very large. Okay, so basically you could look at such a hierarchical case, and you can expand around one of these saddles. Let's say we take X plus, and you see these two oscillators coupled through very strange potential. Let's take lambda really much larger than 1. In that case, you see that there are kind of cubic terms, quartic terms, and these terms are just for self interactions. And the interesting thing is, for very large lambdas, it is clear that these self interactions are kind of small, right? Because you divide by lambda. Then there are cross couplings, quartic, cubic, and so on, and they're also small. This is important. So basically, if you expand, it's kind of small. So in reality, so here I will not show you that this situation is nonlinearly stable, but it's kind of can be achieved in the same method as for the system which I showed before, and I will now show the stability. Okay, but let's first look at numerical solutions. Let's say lambda is 1/3, and we look at x and y. You see it's not much happening there, and we look for 500 periods, so it's all okay. But don't forget, in the previous example of instability, the instability would start at 600 periods, right? So therefore, who knows? One can look at projections at y-py space of moment, basically of the phase space. And here the color just shows how the time passes, and you see that these trajectories cover kind of donuts. You can also look at what is usually called Lissajous figure, so in x and y, and you see that there is a kind of pillar covered by these trajectories. And you see numerical solutions look pretty stable, but okay, and what? As we know, this may be just a false sign. And also, you see, numerically, you cannot check all initial data. There could be islands of stability, islands of instability. You never know. But it's a good indication, of course. So the question is, maybe it is just a stable system. And here it's very important that at least two notions of stability are relevant for such discussions. And what we are going to do, we are going to prove both of them. So first, the question will be, can one analytically prove what is called the Lagrange stability? So Lagrange stability is the statement that the system does not have runaway solutions. So basically, you take initial data, and for each initial data, you can predict a region of phase space where the system will evolve. So it never goes to infinity in phase space, even at infinite times, okay? So this is a very strong statement. And then there is a more practical or more, it's a bit different, I mean, local stability, which is also called Lyapunov stability, and it was introduced by Lyapunov. And its equation, let's say, usually it's applied to equilibrium points because it's much easier. It's a question whether if you deviate a bit, let's say, from your equilibrium point, whether you stay in the neighborhood of this equilibrium point or you go away from it. And you can, instead of equilibrium point, you can take whatever solutions there, okay? So in particular, that's important for talking about stability of vacuum, okay? Or if you want, of equilibrium points. So how we derived our systems, this potential is a bit ugly, but where did it come from? So actually this first integral is the power of our imagination, or if you want, of imaginary numbers. It happens because actually the system is integrable. So it has a first integral of this ugly form where k is kind of hyperbolic momentum, if you want. And one could check explicitly that this C does commute with your Hamiltonian, and that it is actually a conserved quantity. So then the point is that we actually obtained our guy from stuff which was derived for normal kinetic terms, and then we just made an imaginary valued canonical transformation, preserving all commutators, whatever, Poisson brackets. And the point is that, we thought that it was introduced by Darboux, and then in 1901, but it turned out after we dig up a bit deeper, well, by we I mean Cedric, it turned out that it was actually done by Liouville. And Liouville has done it in a much older paper from 1846. So roughly speaking, it's the same time as Ostrogradsky. Okay, so basically the point is they derived such a system for positive kinetic terms, so px squared plus py squared. Then they found a particular potential which implies conservation of this quantity C. In our case, we have done complex transformation and obtained a ghosty system with this integral which I show you. Okay, so now the point is that it's very convenient to introduce another first integral, which is a combination of the previous, a linear combination of the C and H. And of course, a linear combination of first integrals is a first integral as well. And it can be written as a sigma, where sigma is manifestly positive definite, sum of positive definite entries. So actually, interestingly enough, sigma is your, let's say, call it momentum. It's a bit sloppy, but let's call it momentum squared, plus free energy of first oscillator, plus absolute value of free energy of ghosty oscillator. So then there is this structure y squared minus x squared multiplied with interaction potential. And you see what is important. Due to the form of this potential, we see that the second term in this E is bounded. It's bounded from below and from above. Okay? So now this implies that, of course, this whole first integral E is bounded from below and from above. So basically, if I take initial data, right, I can calculate what is this E, what is sigma, and I would know that my E is located between sigma minus lambda and sigma plus lambda. So what does it imply? It implies the following. Suppose I have calculated it at the initial moment of time, okay, then E is between sigma, calculated in this initial data, minus modulus lambda, and sigma plus modulus lambda. Then I wait for some time and calculate it at later time. And what I will see is that it's sigma at moment of time B minus lambda and sigma at moment of time B plus lambda, okay? But E is the same. So I implied just the same inequality at two different moments of time, but the quantity E does not change because it's a conserved quantity. So therefore, what does it imply? It implies that sigma A minus modulus lambda is less than sigma B plus modulus lambda, and sigma B minus modulus lambda is less than sigma A plus modulus lambda. So therefore, what we immediately see out of these inequalities, that sigma at later moment of time is bounded between sigmas at the original moment of time plus or minus two absolute values of lambda. Okay, so what is very interesting, it resembles the shape of this donut, because think of the following way. This sigma, it's almost a modulus of your radius vector in phase space. So if you take radius vector in phase space, it's always less than this 2 sigma due to presence of this momentum squared, right? So therefore, this bound immediately implies that the shape of the phase space which you cover is kind of this, if you want, space between 2-3 spheres in 4-dimensional space. Okay? So therefore, the projection would give you this funny shape in YPY. So the system always evolves in a finite region of phase space for all initial data. This is a global result. So it doesn't matter where we start, it always stays in finite region of phase space. This is crucial if we want to study quantum mechanics of these guys, because wave function would investigate whole phase space. And therefore, the normal Lyapunov stability would not be sufficient. But the Lagrange stability, the global stability, is really important to try to quantize the system. Okay, so basically we showed analytically that the system always evolves in finite region of phase space. But for practical reasons, it's also very interesting to understand whether the origin is Lyapunov stable. Because of course, what we will try to do, we will try to do something in vacuum. And
sorry, you have 1-2 minutes.
Yeah, I'm actually finishing. Yes, very good.
Thanks.
So basically, look, what one can do next is to take this E, and one can show that it is actually what is called Lyapunov function, and one can use it as to prove Lyapunov stability due to his direct or his second method. And it's very interesting that he derived it in his doctoral thesis in Kharkov Imperial University. And, now it's actually basic for all these drone technologies and all the robotic stuff and control systems. So at the origins, this E is 0. And then you can see that if lambda y squared minus x squared is larger than 1, this first integral is positive, just manifestly. But if it's negative, due to the boundness of this term, you can find that this E is actually larger or equal than k squared plus the sum of absolute values of the energies. And that implies nonlinearly that for lambda less than 1/2 by absolute value, this E is also positive definite. Okay, so basically by doing that, you have shown that this E is a Lyapunov function, so that the system is indeed stable. Which is kind of fun is that, we could guess it from linear analysis, but normal linear analysis does not work, but Lyapunov analysis does. So basically, by Kolmogorov, Arnold, Moser, one could say that structural changes do not jeopardize the stability and finiteness of motion. So we could now change the system a bit by adding new terms. As far as new terms are perturbations, nothing will happen. Okay, realizations through higher derivatives, one can write Lagrangian of Q2 dot and reproduce the same dynamics. Okay, the major question would be in that case, why have not we seen such systems in nature yet? So it's not about stability, that's for sure. So thanks a lot for your attention, and I will use 1/2 of a minute to advertise the following thing, that in our institute, we won this Marie Skłodowska-Curie Action Co-Fund, and we will have a really extended postdoc program. It's actually 60 postdocs for 2 years. And it's not only, of course, for our group, like most people will be like experimentalists and so on, but stay tuned, it will be announced in this fall. And there will be a lot of jobs, and some of them, not 60, but some of them will go to us. So please consider it. Okay, thanks a lot.
Thank you very much, Alex, for your talk. And yeah, I can see already a question from Alexei Starobinsky.
Perfect.
Okay, thank you, Alex, for your very interesting talk. Actually, I have not so much a question, it is a remark, and this remark is in fact just coincide with your last sentence of your talk, but I shall formulate it in a little bit different way. But suppose that you can construct some system with ghosts which are stable in some sense. Okay, even to a certain then I would say that when in this case the problem of the problem arises actually not at the quantum but already at the classical level, and the problem of stability of dynamical behavior in usual cases. With ghosts is transformed to the question of the initial conditions for classical inclusion. So it's just exactly why we don't see in the real universe omega of usual matter exceeding unity, actually even much exceeding unity, and then this is compensated by, say, dark ghost dark energy or ghost dark matter having negative energy density. In your calculations which you presented, as far as I understand, you use something like quasi-vacuum initial conditions, but for all classical our applications, there is no reason why initial conditions should correspond to the vacuum case. And in case of non-vacuum case, as I said, the question is just exactly what you said in your last sentence. Why we don't see large amount of dark energy with negative energy density and or non-relativistic dark matter with negative energy, and this is compared can be compensated by sufficiently large by the corresponding large amount of usual matter.
Alexei, I would like to stress that our analysis, you see, that's very important. So we prove Lyapunov stability of the vacuum exactly as you said, but this is really for this point, basically, like for this, I don't know whether you still see it, like this point, and of course by continuity some small configurations around it. So that's we prove Lyapunov stability. But what is more important, we prove Lagrange stability for all initial data there. That's what is the key point. This integrability gives us the opportunity to say, in one of the few examples which I know, something about global dynamics. And global dynamics, the motion is always finite. And another point, what I wanted to stress, that you see, I don't know, my knowledge is not sufficient for that, but in this paper by the group of Alessandra Strumier, they claim that there are two examples of ghosts in nature, which I find completely crazy, but that's very interesting. So maybe you could judge better whether it's true or not. So they claim that it's kind of known for celestial mechanics guys that Lagrange point 4, L4, Lagrange point asteroids, after some transformations, that they look like ghosts. For me, that looks absurd, but they claim it's a known fact. And another thing, they have another example of particle in magnetic field with some repulsive interaction, but this repulsive interaction is introduced there by hand. So they claim that the gravitational system with these ghosty asteroids is a kind of established fact, but it requires some canonical transformations. This is non-trivial. Whereas, this point of particle in electromagnetic field, it's a bit more strange, I would say, because, okay, you need to introduce such potential first. It's one thing, but what is the key point that we really prove stability for all initial data in the systems? That's very important.
But once more, this is not the problem which I mentioned. Why we don't see a stable ghost, even negative energy. And indeed, I would say, speaking about the examples you mentioned, indeed, well, it's well known that even in case of the usual Newtonian gravity, with beginning from free particles, that where exist cases with chaotic behavior, and in case of chaotic behavior, it is possible to introduce something for some particles, a kind of ghost. So it's simply the case of chaotic behavior. But I'm speaking. But what I said were if a problem of, in particular, if a problem of cosmological initial conditions, even in the best case for you in the absence of chaos. Why initial conditions that were not such that which would, as I said, lead to the existence of a large amount of stable ghosts, stable ghosts with E negative omega m, which would result in the omega m of the visible matter exceeding or even much exceeding unity.
Mm-hmm. You want to have negative energies, like true negative energies in the universe.
Yes.
And then you say that this would not work, right?
Mm-hmm.
Okay.
Okay. Maybe also Anna has a question.
Hi, Sasha.
Hey.
Thanks for nice talk. I have a question maybe related to what was already discussed, but can in your model with ghost, can you just make a redefinition of your coordinate y to iy, where I is imaginary, like, and then you can arrive to the, you can get a system which doesn't contain the ghost, but the potential will be still real and it will be fine.
Yeah, no, absolutely. That's exactly how we derived it. That's exactly.
Yeah, I see, but it looks like not the true ghost, not what is normally happening in series, like with higher derivatives.
No. Look, look, it's exactly the point. You take a series with high derivatives. Okay, it looks a bit ugly. Well, because we started from not higher derivatives, but lower derivatives. You see this P2 is some function of this Q2 dot. So that's your high derivative system. And it does.
This is a very specially cooked higher derivative system, right? But typically you get something worse than what you considered.
But you see, one should understand the very simple point. If you take a normal system, you see, the question of stability is a highly non-trivial one. So if you take normal system, let's say, from basically what we took, there is a paper where not one, but quite a bit of reviews where people discuss integrable systems. And in most cases, people derive by brute force analysis those mechanical models with 2 degrees of freedom, which have conserved quantities, first integrals, on top of energy. And they, of course, were motivated by normal positive kinetic terms. The point is, if you do this complexification, in some cases, you arrive to complex systems, which is another point. But in some other cases, you arrive to systems with ghosts, but they're not stable at all. You see, just the presence of second integral and the point that it corresponds to normal 2 degrees of freedom after complexification does not guarantee you stability at all.
Yeah, of course, but you can study it like in normal systems, looking at the potential.
No. The solutions are completely different. You cannot do it. It's a nonlinear system, and the solutions are not the same. So, for example, what can have run away in normal situation, or let's say in ghosty situation, may have no runaways otherwise. Because it's not the same behavior. I mean, it's not the same system in a sense. So it's just a trick to derive it, but it doesn't guarantee you stability at all, or absence of runaways or anything. That's the point. So if you look at these guys, it's in most cases actually they're all unstable.
Okay. Maybe we can discuss more on this point also during the discussion. I also have a question actually about this. But let's thank Alex Wickman again. Thank you. And now we can move to the last talk of this morning session. We have Olaf Holm. Hello, Olaf. Good morning. Hey. Please, you can share your slides.
Okay. Can you hear me?
Yes.
You see my screen?
Oh, yes, I can see it.
Okay. You see my cursor, my mouse?
Yes, I also see your cursor. Yeah.
Okay.
Would you like me to give you 5 minutes warning, or you can just...
Yes, that would be nice.
Okay, I will give you then 5 minutes warning. Okay, so please, Olaf, you can start.
Thank you very much. So thanks a lot to the organizers for organizing this nice conference. So I will tell about a series of papers I wrote with my student, Felipe Diaz, who's in fact a joint student with Jan Plewka, who's also in one of the papers, and two of my postdocs, Roberto Bonazzi and Christoph Chiafrino. So the title is Quantum Gravity from Young-Mills Theory. The quantum is in parentheses, so I have to apologize because most of this talk will be about actually classical gravity in flat space, classical perturbative gravity. Now, this is a conference on quantum gravity and cosmology. Now, cosmology and quantum gravity is very much part of the motivation for this work. In fact, there's some related work with my former student, Alison Pinto, on cosmological perturbation theory and double field theory. And there's some work in progress relating to the quantum aspect. But we have to start at the beginning, and the beginning is the story of connecting gravity to Young-Mills theory. So let me start with the motivation and overview. So the starting point for our construction is the double copy construction and scattering amplitudes. So you probably all heard about this several times. So there's this intriguing connection at the level of scattering amplitudes between Young-Mills theory and gravity that's sometimes summarized by the slogan, gravity is Young-Mills squared. So this is a construction that, in fact, goes back to string theory, the so-called KLT relations in the 80s. And then more recently by Byrne, Carrasco, and Johansson was formulated for field theory, where you take the scattering amplitude of a gauge theory like Young-Mills and you break it up in a certain way into color factors and kinetic factors. And then you replace the color factors by a second copy of kinetic factors and obtain a gravity amplitude. So the question has always been, is there some sort of off-shell or Lagrangian derivation or understanding of this connection? Because if you just look at the normal Lagrangians of gravity and Young-Mills, they don't look anything alike. So it looks very much miraculous. And so in this recent work, we've found an angle where you can actually derive gravity, at least perturbatively to some order, from Young-Mills theory. So in a sense, gravity really is Young-Mills theory if you just interpret the term Young-Mills theory broadly enough. So the slogan gravity is Young-Mills squared is a little misleading. But anyway, so I will begin by introducing a very simple Lagrangian construction where we relate Young-Mills to gravity in the following way. So let's say you start with the Young-Mills action. You have the gauge bosons A mu A. A are the color indices. And now the rule is that you just replace the color index by a second set of space-time indices. So we denote them by a bar. And because you have, in a sense, now a second space-time, there's a second set of momenta, k bar. And this yields a gravity theory known as double field theory. So double field theory is something that came out of string theory. I don't assume you to know what it is, because in a sense, I will rederive or reconstruct double field theory starting from Young-Mills. And I will try to convince you that this is really the best framework in order to understand double copy, because the sort of double copy structure that you would expect starting from Young-Mills theory sort of built in to double field theory. Now, this construction is very simple, so it won't take much time, but is sort of limited. It works to cubic order, and it's hard to see how to go beyond it, and also doesn't work in a fully gauge invariant fashion. However, there's a much more sophisticated and much more powerful approach, which I call here the algebraic double copy, in which we interpret Young-Mills theory in the framework of so-called homotopy algebras. So this is something that I assume for most of you is rather foreign, and you don't know what it means, but I will give a self-contained introduction into these so-called homotopy algebras, one example of which is called L-infinity algebra. And in this one can think of Young-Mills theory, or not just think of it, in fact, explicitly derive it that way, as the tensor product of a certain kinematic algebra and the color-Lie algebra G. So then we can just replace the color-Lie algebra by another kind of Lie-type algebra, and it turns out that the kinematic algebra itself can take this role. So then gravity in the form of double field theory follows in this form K tensor K bar. So this is all about classical gravity, but there's an extension to something called the weakly constrained theory, a term I will introduce, which should exist on toroidal backgrounds, where one includes certain massive string modes, certain massive modes that arise in string theory and that have been speculated to be important in cosmology. And so that's something we have not yet worked out to quartic order. We know how it works to cubic order, but not to quartic order. And this is related to this question here, whether how to work this for time-dependent or cosmological backgrounds. Okay, so that's the overview. I will now introduce the first part, the Lagrangian double copy. And please feel free to interrupt me at any time. Okay, so we start very simple with the Young-Mills action that you all know. So let's say in D dimension, we write the action here. F mu is the non-abelian field strength. Kappa AB is something like the Cartan killing form. So AB are color indices. And we expand this action out. So we have the quadratic terms, cubic, and quartic terms. The quadratic terms are written here. So here I've transformed to momentum space immediately. A mu of k are the Fourier modes. And we have the kinetic operator here, where I scaled out a k squared. That is motivated by the double copy procedure at the level of amplitudes. And so since I've scaled out the k squared, what is left, the pi mu nu, is this expression here. So you can easily convince yourself that this is the proper kinetic operator in momentum space. And this is a well-known projector. So it satisfies pi squared is pi. And it is a projector because if you contract it with a k nu momentum vector, you see that these two terms cancel and you get 0. So it has a null eigenvector proportional to k mu. And that's, of course, an expression of gauge invariance. So if you shift the a mu a by something proportional to k mu with an arbitrary gauge parameter in front, it will just kill this term. And that's the standard well-known gauge invariance of Maxwell theory, or the linearized part of Young-Mills theory. Okay, so let's just ask, how could we double copy at this level? And so as I sketched, the double copy rule is simply to replace a mu a of k by replacing the color index by a second set of spacetime indices indicated by a bar, and by introducing a second set of momenta, which we also call k bar. And so the double set of momenta I also denote by a capital K. So the Cartan killing metric kappa AB, which was used before to contract here the indices, has to be replaced by something with the new space-time indices. And the obvious candidate is just to use this projector again. So you replace the action by a k squared times pi mu nu times the second set of pi bar of k bar. The same expression as before, but just with all momenta replaced by k bar. So this is now completely democratic between k and k bar, even though we have a k squared in front, not a k bar squared, but we impose now the condition, which is motivated by string theory, needed here for consistency, which is called the level matching constraint, that we assume that only those Fourier modes exist in which k squared is equal to k bar squared. So then, in fact, it's completely democratic. And now, because we have introduced these projectors, we have a gauge invariance as written here. So the original Young-Mills or Maxwell gauge invariance now acts on both indices. So we have the original one where you can shift by k mu, and the gauge parameter now carries a barred index. But we also have now gauge invariant on the second index, corresponding to the fact that the pi bar here replaced the kappa. So we can also shift by something proportional to k bar with a new gauge parameter lambda mu. So you have now two independent gauge parameters, lambda mu and lambda bar mu. And in fact, you see here, this looks already very close to the standard linearized diffeomorphisms of gravity. And in fact, it's part of this transformation. So there's one combination of these two parameters that can be identified with the diffeomorphism parameter of gravity, and another linear combination that can be interpreted as the gauge parameter of an antisymmetric tensor, the B field, which is also part of string theory. So let's try to see more specifically how to connect this to gravity. In fact, you can connect this to gravity in the form of double field theory, first at quadratic order. And to make this very explicit, let's introduce an auxiliary scalar field. So this is necessary because if you write out these projectors, remember what they look like. They have these 1 over k squared terms here. So there's 1 over k to the fourth coming from here. So that is not something that is immediately writable in a local form if you go back to position space. But you can solve this problem by introducing a sort of quote-unquote auxiliary scalar field phi, as written here. So if you now integrate out phi, so you just look at the field equation for phi and solve for it, you get this 1 over k squared. If you plug it back into the action, you in fact reproduce exactly this double copy action as written above. But now in this form, you see it looks local. You can go back to position space. And in fact, you get exactly the known double field theory action at the free level, the quadratic level, where you have the doubled derivative operators, partial mu related to the original case and partial bar related to the k bars. Of course, subject to this constraint, which we call the weak constraint, which comes from this k squared equal k bar squared of the level matching constraint. And this linearized double field theory, in turn, is related to standard linearized gravity coupled to a B field, an antisymmetric tensor, and a scalar field, the dilaton, if you now identify these two coordinates. So if you set them equal, you just get standard linearized gravity plus B field plus dilaton in a certain slightly different field basis. So in that sense, you get immediately gravity. In fact, it's even in a gauge invariant form. So you don't have to assume a gauge fixing condition, which I would argue is the simplest and most compelling explicit double copy construction that I've seen at the level of a Lagrangian. Now, of course, you can say the free theory, who cares? So let's go to cubic order. Let's switch on the first interaction. So in Young-Mills theory, if you expand out f mu nu, you could produce this cubic term here, which is proportional to the structure constants and has one derivative in it, as written here. So momentum space, you get something linear in momenta. So it can be written in this form, and it's most convenient to use the symmetrized version as written here. So the pi mu nu rho depends on the momenta. So there's a so we've written it as a threefold integral, but there's a momentum conserving delta function, of course. And these k12, k23, etc., means the difference. So k12 is k1 minus k2, etc. And so this is in momentum space, the cubic vertex. Now, if we do double copy, we replace again A by an E mu bar, let's say. So you have to find an object that contracts the new spacetime indices. So we have to replace the FABC, the original structure constants, by something carrying spacetime indices, namely the barred spacetime indices. And well, the obvious double copy rule is you just replace it by a second copy of the pi mu nu rho. So as we did before for the pi mu nu, now we do the same for the 3-index object. So you replace it by a second copy. And so then you produce something that's now quadratic in momenta. And that's, of course, exactly what you would expect for gravity. So in other words, the double copy rule here is to write this action. Everything is now double momenta. And you have two copies of these symbols here, the pi mu nu rho. All indices are contracted without the color indices. And now you can Fourier transform into a doubled position space to get a cubic action that looks kind of like gravity. Now, here you just produce 5 terms if you integrate by parts a bit and throw away redundant stuff. So you have just these 5 terms that looks much simpler than anything you would look up in terms of gravity to cubic order. But in fact, this is the cubic double field theory action, not completely, but in a certain gauge, which is called the Siegel gauge. So the Siegel gauge is a term coming from string field theory. But in terms of normal fields at this level, just means something like the Donda gauge if the dilaton is 0, or some slight generalization if the dilaton is not 0. So you do get correct cubic action just in a particular gauge. So the construction that worked at gauge at the level of gauge invariant objects to quadratic order doesn't quite give something gauge invariant to cubic order, but it comes very close to the complete action. And I just want to emphasize the simple form with just 5 terms, because in the more complete construction that I will present next, there is in fact just one more term that needs to be added to get the complete cubic action. Okay, so that's about the Lagrangian double copy. Are there any questions on that? Because if not, I will switch now to the more sophisticated.
Hola, I have a question.
Yes.
Is it possible to recover up to cubic order, the fully ungauged part of action, or you always end up with the Siegel or whatever gauge?
So no, there's a gauge invariant method, and which this is what I will explain in the rest of the talk. But it's more sophisticated. You cannot just sort of play around with the Lagrangian as I did here. At least I wouldn't know how to just do it at Lagrangian level. So in particular, you need a formulation where there are more pure gauge and auxiliary fields to make it work.
I see. Okay, maybe then I will ask the question just ahead, which you will explain.
Yes.
The answer. The gauge Yang-Mills theory action has a gauge parameter, which is 2 degrees of freedom.
Yes.
Now then the K and K bars, each part, you have 2 times 2 is 4, right? Do you recover from that the full ungauged gravity action with the ungauged?
Sorry, what do you mean by
just asking for the matching of the parameters of gauge transformations?
Yeah, so well, it's so in Yang-Mills you have this the number of gauge parameters is given by the number of by the dimension of the Lie group, right? The color Lie group. And so this parameter we replace by a second set of spacetime indices. But you, in fact, in the process, introduce an extra gauge redundancy because you replaced the Cartan-Killing metric, or we replaced the Cartan-Killing metric by something that has, again, a degeneracy, that has null eigenvectors, namely the projector. And that explains why you have an additional enhanced gauge redundancy. And that's as you would expect for this double copy procedure, because you have to get diffeomorphism gauge parameters and B-field gauge parameters.
Right. Okay, I see. Okay, good. Thanks.
Any other question?
Yeah, I have a short question. So this level matching constraint, can it be imposed, so it is imposed by hand, or how does it work in this action? Or you impose it by saying the fields depend on the momenta only in this restricted sense. So if you
write the general Fourier expansion or the Fourier integral of a, well, so the level matching really comes from a torus. So you have a Fourier series, and you just assume that only those Fourier modes are non-zero which do obey this condition. And then so at the level of free theory, there's no problem. Then you just write this action and it's correct. There's a subtlety if you go to higher order. To cubic order, also there's not really a problem, but then to higher order, that's a very non-trivial problem. How to make sense out of this constraint. I will say a few words about this at the end.
But can you impose it through delta function or not? Just multiply?
Oh, no, it restricts the field content. So if you think of sort of the theory being defined as an infinite tower of fields. So let's say there's a non-compact dimension and then a compact toroidal dimension where you have this doubling. You have an infinite number of fields, which is the infinite tower of Fourier modes, and you just restrict that tower to the subset that obeys this condition. So in that sense, it's just really a statement about the field content. Okay. But there are various interesting questions related to this, so we can discuss this.
Sure. Thanks.
Okay, so let me come to the second part. So the first part was very sort of humble and kind of child's approach to double copy, but I think not seen anything as simple in the literature. The second part is much more sophisticated and uses a certain algebraic approach based on something called homotopy algebras. So this may sound to most of you rather scary and foreign, but don't panic, stay with me. I will just explain everything in detail. So we start by just looking at perturbative field theory, classical field theory or tree level to begin with, from a more algebraic perspective. So let's say I'm given an action S that depends on some generic fields, which are called A here. And so we have broken up the action as a quadratic term, a cubic term, a quartic term, etc. Now here I've wrote this in a particular way using an inner product, the angle brackets here, which involve something like an integral, so the usual spacetime integral, and a series of maps called B1, B2, B3, which just indicate how many arguments they have. So they are multilinear maps in a certain vector space. So here we have a vector space, which is graded, and the grading just means that there's an integer which you attach as a bookkeeping device to each object. So a field has a certain degree, a gauge parameter has a certain degree, etc. And so we will encode the data of a field theory, which is just the familiar things you're used to, like when you write an action or equations of motion or gauge transformations. You have these objects like a kinetic operator, a cubic term, etc. You have those objects, and you just give them names, and you try to figure out what are the relations that these objects have to satisfy in order to have a consistent field theory. By consistency, I mean, for instance, gauge invariance. And the statement is that this general sort of set of relations is an algebraic structure that is called an L-infinity algebra. So L here stands for Lie. So it's a generalization of a Lie algebra, and this infinity means it's a homotopy version. So it means the Lie structure is not obeyed in general, but it fails in a certain controlled way. So let me just try to give you the definition in this one slide slowly. And then I will illustrate this with the example of Young-Mills. So we said we have a vector space, an integer graded space. So it's this direct sum. And on this vector space, we have a set of maps, graded symmetric maps, B1, B2, B3, and continuing indefinitely. And these I call graded symmetric, which just means that they are symmetric or anti-symmetric depending on the inputs. So depending on the degree of the inputs, this may be symmetric or anti-symmetric. And now these maps satisfy relations, in fact, potentially infinitely many, but the first three are given here. So in a sense, the most important relation is the third one here, which is the Jacobi identity, or rather Jacobi up to homotopy. So if you think as the B2, as the map that has two inputs, as a graded version of a Lie bracket, so it's something that maybe has components that are symmetric and components that are anti-symmetric, you can ask, does that satisfy a graded Jacobi identity? And this would mean that these three terms here, where you have signs due to grading, are zero if they have Jacobi identity. But in an L-infinity algebra, this does not need to be zero, but rather it can fail up to a 3 bracket or 3 map together with a B1, which we call the differential. So the B1 itself is called the differential and squares to 0. So that's the first L-infinity relation. And it acts on the B2, the 2 bracket, via the Leibniz rule. So up to some signs that look a little funny, which are due to conventions, this is the Leibniz rule of B1 acting on the 2 bracket. And then, as I said, we have Jacobi up to homotopy, which means that the B2 satisfies graded Jacobi up to terms involving the differential and the 3 bracket. And then there are potentially infinitely higher maps and infinitely more relations. And it's you can write that all in a closed form, but I won't need to go into those details here. So that's the definition of an L-infinity algebra, just the math definition. And I will now explain how to connect this to field theory. So let's do it just for Young-Mills theory immediately. So here's the action for Young-Mills theory written out, the quadratic terms, the cubic and the quartics. And I've used a particular formulation with an auxiliary scalar field phi. So if you integrate out phi algebraically, you can just do it. This is just the standard kinetic terms. And we like the phi, as I will explain in a minute, because it allows you to single out the box. That's kind of like the k-squared is important in the double copy procedure. It allows you to single out the box in a gauge invariant manner. Okay, so all fields are Lie algebra valued. And now the vector space that I before, the algebra, in this case has the following interpretation. So we have a space called x minus 1 of gauge parameters. You have the space of fields called x0. So the sub-index here is always the degree. And calligraphic A denotes this doublet of fields, so the vector fields and the scalar phi. And then the next space you can think of the equations of motion, or if you know the BV formalism, it's also called antifields. And then there's a space which plays the role of Noether or Bianchi identities due to gauge invariance. And I indicated already the B1 here, the differential, which acts along this arrow here. And this B1 encodes the data of the free theory. So for instance, the B1 on lambda encodes the gauge transformations. So delta A is B1 of lambda, is the linearized part of the gauge transformation. The B2, the B1 of A includes the linearized part of the field equation. And so they're written here, for instance. So this is just d mu lambda. You just put what the gauge transformation of A mu is. Here you put the field equation of A mu, which in this formulation with phi looks like this. And you can write similar formulas for the higher B's that include Noether identities. Okay, so that's the B1. Now the full Young-Mills theory is encoded in the nonlinear structure. So for instance, the nonlinear Young-Mills equations are writable like this. So it's what's called a generalized Zumara-Katan equation. If you take the previous B1 and you define a 2 bracket and a 3 bracket like this, and you see here, if you contemplate this a little bit, you will see this is just the familiar Young-Mills equation. You've just given a name to the quadratic term, and you've given a name to the cubic term. And similar for the gauge transformation, you can write like this. The nonlinear term now has a B2. And in general theories, there might be even higher B maps here, like a B3 and a B4, etc. But here I've written the Young-Mills example where with these formulas here, you can just check that you have the normal gauge transformations. You can check closure of the gauge algebra, etc. And so this algebraic structure, the L-infinity algebra, just encodes the classical consistency conditions that you would think of in field theory, like covariance, gauge covariance of the field equations or closure of the gauge transformations, all these things, encodes it in a generalized Jacobi identities, where by generalized Jacobi identities, I mean these relations and the higher versions. Okay, so now you will, of course, think to yourself, who cares? I mean, all I've done here is I've written Young-Mills theory. If you've seen it many times, and given funny names to the small building blocks. So what's the point? What can I do with it? So one thing you can do with it, why it's useful here, is you can now give a meaning to stripping of color. So in the amplitude approach, an important first step is that you take the gauge theory amplitude and you take a color strip version. So you take out the color factors. And this is something that at a level of a Lagrangian is not so, doesn't seem so meaningful. You cannot write a colorless version of Young-Mills theory. That doesn't exist. And similarly, there's no colorless version of this L-infinity algebra just defined. But in fact, you can realize this L-infinity algebra as a tensor product of a different kind of homotopy algebra, which I call K here, with the color Lie algebra. And now this different kind of algebra does not define a field theory by itself, but it's an algebra. It's something that has a mathematical structure and that you can work with. You can check that it exists, that it obeys the right relations. And in a second step, to which I will come in a moment, you can now take a second copy of this algebra and build a gravity theory that's again given by an honest L-infinity algebra. So let me now briefly explain how this works here. So in Young-Mills theory, of course, we have G-valued fields. So the gauge fields, they all live in the color Lie algebra. So that means all objects have an expansion like this, where TA are the generators, A are the color indices. And at the level of the vector space, it's clear that I can just split this up into a tensor product. So I can think of this as a tensor product with a sum over the generators TA here. And now the XA are just objects that are sort of colorless. They have this color index A here, but just a label at this point. And now I can think of the L-infinity structure coming from a new algebraic structure. So there's a new differential M1. So I write this relation, which only acts on the colorless objects. So the generators taken out. Similarly, the B2 can come from an M2, which also only acts on objects of the kinematic algebra. So this K will play the role of the kinematic algebra. And the structure constants are explicitly taken out. And similarly for the B3, here I wrote it just for the fields, because for Young-Mills, this is the only B3 that exists. And that's related to small M3. So the statement is that these new maps, M1, M2, M3, they form a different kind of homotopy algebra, which is called a C-infinity algebra. So before we had the L-infinity algebra, which is a homotopy version of a Lie algebra. And in the same sense, this is the homotopy version of a commutative and associative algebra. So C stands for commutative. So if you have a commutative associative algebra, it means you have a product that is symmetric and it satisfies an associativity relation. So if you call this product M2, the associativity relation would be just that these two terms here are equal. But in the C-infinity algebra, they do not need to be equal. They only need to be equal up to homotopy, which again is governed by a differential M1 and a 3 product M3, and then they're again potentially higher order terms. So we have two kinds of homotopy algebras: L-infinity that defines the field theory, and C-infinity that you sort of got by stripping of color, and that encodes sort of the kinematics of Young-Mills theory. Okay. Now, in order to do this double copy procedure, we have to realize a yet more sophisticated algebraic structure realized on the space, which is that it has this Z2 grading, which is indicated here. So I've copied again this kind of chain complex. So all these objects here, you should now think of as colorless. So in Young-Mills, they had color indices. Here, they don't have color indices, but you have sort of the same objects. You have something that you can think of gauge parameters or fields. But because of the introducing this auxiliary scalar phi, there's now this Z2 grading. You have two lines here, and you can group them in this fashion as written. And because of this grouping, there's actually a new nilpotent operator B that acts in the opposite direction of the M1. So the M1 here goes from left to right, and the B goes from right to left. So it acts actually sort of in this diagonal way here, going like this, and like this, as written here. So for instance, acting on fields, it just picks out the scalar component, or acting on the Noether identities, it takes the scalar component and copies it over into the scalar component of the equations, etc. because it acts in this fashion, it also squares to 0. So it's also nilpotent, and it satisfies this relation with the M1, with the original differential of the C infinity algebra. And this is a relation that experts on string theory may recognize as part of familiar relations of a BC ghost system. So this B is just sort of a silly operator. It exists because you have this auxiliary field, and it's purely algebraic. So acting here just picks out the scalar component and identifies it as an object in this space. But due to its existence, we can realize a hidden Lie-type algebra on K. So let me just remind you of what the goal here is. So we have Young-Mills theory, which is an L-infinity algebra. It consists of a factor K times a Lie algebra, which is the color Lie algebra. The color Lie algebra we want to take out, and I want to replace it by a second copy of the kinematic algebra. Now, the kinematic algebra, as I just introduced it, is an associative type algebra. It means it's a generalization of a commutative associative algebra. But for the double copy, it should really be a Lie algebra, like the color Lie algebra. And in fact, it carries such a structure in a generalized sense up to some failures that you can cancel on the double copied space. So here, the math is pretty obscure even for us, but it seems to be really there in Young-Mills theory proper. And I don't have the time or energy to explain all the details here. But the basic point is that given the B and given the M2, you can define something that is almost a Lie bracket, which I call B2 here, and which is like the failure of the B, which squares to 0, so it smells like a second differential. It's the failure of B to act via the Leibniz rule on M2. So if B would act via the Leibniz rule on M2, this would just be 0, but it doesn't. So this is not 0. And in fact, it's almost a Lie bracket. So in order to say more precisely what this is, I have to recall a notion called the Batalin-Vilkovisky or BV algebra. So most of you are probably somewhat familiar with the BV formalism. And this BV algebra is sort of the algebraic essence of what this is. Namely, it's the general algebra is defined as a commutative associative product, let's call it M2, together with a differential B that squares to 0. And that is of second order. Now, second order means it's something like a Laplacian. So true differential acts like a first order differential operator. Second order means it's something like a Laplacian, and you can just give a precise algebraic definition of what that means. And if you have that, then the B2 that is derived as written here from the M2 and the B actually obeys the Jacobi identity and a compatibility condition with the product. So you have a commutative product in a Lie bracket, and they work together. And so something like a Poisson structure. So like the Poisson bracket familiar from classical mechanics, together with the product of functions on phase space, has that structure. And this is sort of a graded super generalization of that. So these structures that we have in the kinematics of Young-Mills want to be a BV algebra, but actually fail to be that in a certain controlled way. So first of all, the M2 is not associative. So remember, the M2 here was part of a C infinity algebra. So it's not actually associative, but the failure is governed by the M1. So it cannot be a BV algebra, but I try to sort of get the point across that any algebra can have an infinity version. So maybe it's a BV infinity algebra, which is a precise notion. And even that is not quite true, because for that to work, the differential M1 that controls the non-associativity of M2 would have to be compatible with the differential B that defines the BV algebra. But they don't anti-commute, they rather anti-commute to box. So now there's a second declaration of the structure, which leads to this horrible name, BV infinity box, which is the version of this where you formalize these so-called box failures. So here's one instance of a relation that goes wrong. So if M1 would act via the Leibniz rule on B2, you had only these three terms, but now you have this failure here because box doesn't act as a derivation on M2. So this is a notion that was introduced not by us, but in a different formulation by Reiterer. So this at first looks like a super obscure, purely mathematical version of craziness. But I want to assure you that's really there in Young-Mills theory, and it's the right structure to identify in order to get double copy off the ground. Okay, so I have not given you a complete definition. I've given you just a sense of how this algebra comes about and how it functions.
Well,
So
you have 5 minutes.
Yes, thanks. Okay, so I'm now ready to do the double copy. So as I said, the idea is to introduce a second copy of this kinematic algebra. Let's call it K bar. So we introduce the space K tensor K bar. And now this is a space of functions of two coordinates, because all these objects in K were functions of X, like a mu of X was part of K. And now you have a second space where you have a mu bar of X bar. And so if you take the tensor product of two vector spaces of functions, you end up with the vector space of functions depending on all of the coordinates, like you know from quantum mechanics. If you take one particle Hilbert space and tensor them together, you get two and more particle Hilbert spaces. So this space itself is a chain complex again, which means it has this degree, it has a differential, and the differential is written here. So it's built from the differential on K, the differential on K bar, and it squares to 0. And the B, which has a B and B bar, gives rise to this B minus, which also squares to 0. And now this relation over here translates to a relation as written here, where the delta is the difference of the two boxes. You have now two boxes. And now you still don't have an L-infinity algebra on this big space. You don't have a consistent field theory precisely because of this failure. But now you can kill it by going to the subspace where this delta is set to 0. And in fact, you also need to impose this algebraic condition B minus equal to 0. And these are, again, the level matching constraints, which here sort of come out from the requirement that you want to have an L-infinity algebra. So on this complex, you have precisely double field theory. So for instance, if you look at the space in degree 0, you get precisely the fields that you would expect. So in double field theory, these are the general tensor field, which is the E, which we've seen before. So that includes graviton and B field. And then there's some auxiliary fields. So here you have two scalars and two vector fields. One of these scalars is pure gauge, so there's an additional gauge symmetry. And these vectors are just auxiliary, you can integrate them out. And in fact, they are the vectors that you would set to 0 for normal gauge fixing conditions. Okay, so the free theory just comes out from the differential and the complex. Now, what about the nonlinear structure? So we need higher brackets, like the 2 bracket that encodes the cubic vertex, and etc. So here's the B2 of double field theory. It's writable in terms of the small b2 of this BV algebra and the M2 of the C infinity algebra. And this obeys the Leibniz rule on the subspace, because on the subspace B1 and B minus anti-commute. So this relation here proves that. And we can also define a B3 that encodes the quartic couplings. And this formula is more complicated, but it's entirely definable with these BV infinity box structures coming purely from Young-Mills. So this determines all the data of this gravity theory to quartic order. So for instance, one can work out the cubic couplings, and they are written here. And so these are exactly the 5 terms I've emphasized before, but now we have the fully gauge invariant answer, which adds just this one more term or 4 more terms, depending how you count. And this must be the simplest form by far of cubic gravity. And in fact, it's field redefinition equivalent to the version given by, derived by Hull and Sweber from string field theory. But it's much, much, much simpler than that one. Okay, since I'm running out of time, I will skip this slide, which was just trying to get across that the cubic vertex of Young-Mills theory immediately determines the gauge transformations of gravity, of double field theory, which I found very shocking when we first realized that. everything we've done so far is really at the level of ordinary gravity, where this doubling of coordinates is only formal. So we have this doubling, but we impose this constraint at the end, boxes, box, bar, and we do it sort of in the most strongest form possible by just imagining that we identify these two coordinates. So this then gives you n equals 0 supergravity, which is the name for the theory wave gravity, B field, and dilaton. But the really interesting question is, how can you extend this to something called weakly constrained? So where the doubling of coordinates is not just formal, but in fact, you have genuine so-called Kaluza-Klein modes and tori together with winding modes at the same time. And that theory should exist on general grounds, because in string theory it does exist. But what was lacking until recently, on which we hope to find a new angle on, is how to get this explicitly using this approach of double copy. Okay, so let me just summarize. So there's this double copy procedure at the Lagrangian order, which works, at the Lagrangian level, which works to quadratic order in a gauge invariant way, and to cubic order in a gauge fixed way. But a fully gauge invariant version exists if we add a certain level of mathematical sophistication, in which we work with homotopy algebras and write Young-Mills as K tensor G, where G is the color Lie algebra, K is the kinematic algebra. And then we realize a hidden Lie type structure on K to then define gravity as K tensor K bar, where K bar is the second copy. So if one could extend this construction to all orders, so far it's to quartic order, if one could do this to all orders, I'm pretty confident this will eventually be possible, then this would be a complete first principle derivation of double copy. Now, there are many follow-up questions, like, can you apply this to classical solutions? Can you apply this to time-dependent backgrounds, cosmological backgrounds? So far, this is just flat space. And it would also be nice to have a more systematic homotopy algebra-based technique for going to non-trivial backgrounds. Okay, I think I'm out of time, so let me stop here. Thank you very much.
Thank you very much, Olaf. We have already some raised hands. The first was Zravan. Please.
Hi, Olaf.
Hi.
Thanks for a very nice talk. So I have a couple of very naive questions. One is about the double copy between Yang-Mills and gravity. I mean, gravity can be written as square of Yang-Mills. This is the standard way usually called double copy. Does it hold in covered space-time?
Well, this is really my
okay.
to-do question. So far, everything is on flat space as a background. Okay. But of course, we know that you can change backgrounds by shifting by classical solutions. So I'm pretty confident you will eventually be able to generalize this to curved backgrounds as well, but we haven't done anything in that direction yet. So what I'm emphasizing at this point here, you can of course work out double field theory independently on different backgrounds. So we've done this in this paper with my former student Alison Pinto for FRW backgrounds, Friedman, Robertson, Walker. To cubic order so far. And to cubic order, this weakly versus strongly constrained problem is solved. So here you have also a theory with genuine winding modes, but it would be nice to do this to higher orders as well. And there probably one would need a more sophisticated understanding of how to change backgrounds. But this really must exist, because we know in field theory, you can always shift the background by using a solution of the classical solution of the theory you start with. And this, in fact, also has a homotopy algebra interpretation, because you can always take a so-called Maurer-Cartan element, which is a solution of the equations that I wrote, and define a new L-infinity algebra, which is sort of the shifted field theory.
Okay, well, maybe at least it seems to make sense for FLRW, because it's conformally flat, and so maybe it will definitely exist. Double copy perhaps should fully exist in FLRW. I'm just feeling maybe in a complicated backgrounds, I don't know. My second question is actually, I'm a bit confused. Sometimes I read these thermo double field.
Yeah, that is a different double.
Context,
yeah, no, that's
okay.
There are a lot of doubles in the literature. The interesting thing is that the double copy is related to the double of double field theory. So this is a really intimate connection where you would at first would have thought it's just a crackpot idea, right? Someone sees double copy somewhere and double field theory somewhere else, and maybe they're related. But the other double, I think, is unrelated.
That is unrelated to the double field theory.
Yes.
Okay.
I mean, at least I don't know a connection there. Maybe there's also a relation, but I don't think so.
Okay. Thank you.
Then there is a question from Huang Wu.
Okay. Thanks for the nice talk.
Thanks.
I have a question. How to application this double field theory in ADS-CFT and holography? Because I work in holography.
Yeah. So it's so here, and so this so far has nothing whatsoever to do with holography or ADS-CFT. Let me see where I want to go here. But it does smell a little like it, because we're sort of saying that Young-Mills gauge theory is related to a gravity theory, or gravity theory secretly is Young-Mills, but it's really non-holographic in the sense that it's in the same dimension. So you can just build up the perturbative version of gravity from Young-Mills in the same dimension. However, this homotopy algebra framework more generally is also, I believe, useful for ADS-CFT because there's a notion of what's called homotopy transfer, which is the reason that homotopy algebras are useful, because you can relate the homotopy algebra on a certain space to a homotopy algebra on a very different space, let's say a smaller space, by a procedure called homotopy transfer. And in fact, I'm writing a paper right now with a postdoc and student where we give this homotopy transfer interpretation for ADS-CFT. So the map of going from a bulk theory like ADS to a boundary theory, like the dual field theory, can be interpreted at the level of the corresponding homotopy algebras as homotopy transfer. So in that sense, there's a connection, but it's not this double copy procedure as such.
Okay. So if there is no further question, we can thank Olaf again. And according to the program, now we have discussion session with the speakers of this, with the 4 speakers of this morning, plus more general discussion. So we can start maybe with some questions to the 4 speakers, and then move to some more general discussion afterwards. So please, if you have any question to any of the speakers, just raise your hands. I can
Alex?
see. Yeah. Please, Masai.
Yeah, can I ask a question? Alex, can you hear me?
Sure.
Yeah. So let me confirm that your system, Hamiltonian is still bounded from below?
No.
No.
The Hamiltonian is unbounded neither from above nor from below, but there is this first integral which can be used instead of Hamiltonian to bound the model.
I see. Because recently, some of my good friends told me that, for example, usually we say that if Hamiltonian is unbounded, like Ostrogowski theorem, we say the presence of ghost. On the other hand, for example, if we consider the general relativity or just with the diffeomorphism system, general covariance, thanks to the Hamiltonian constraint, Hamiltonian is always vanish, even if we have a kind of some instability mode. So with such system, how to judge ghost or presence of ghost or something?
Look, this is a very good point, because I don't know, in gravity, there is no local definition of energy.
Yeah.
Normal gravitons, right? One can write energy momentum tensor, but this energy momentum tensor is only linearized and on average sense. Sorry, there is a noise from my son, and my wife cannot. So yeah, it's a very good question, because you see, what would be, I think, very interesting is to take, let's say, this quadratic gravity and find solutions with localized negative energy. That would be very interesting, but I'm not sure whether was it done or not, because whole energy should reside there on boundaries. But I'm not sure it is done, to be honest.
Okay, good. Okay, but in your system, Hamiltonian is still not unbounded, but trajectory is kind of compact.
Yeah. Look, Hamiltonian is unbounded, but trajectory is always compact. Yes.
Oh, compact. I see.
For all initial data, all trajectories stay in compact part of phase space. Yes. And actually, in this paper which we are now preparing, there will be really tons of other systems where it is happening, parameterized by three functions. Basically, it's like not one potential; it's even polynomial interactions and other systems. It's really a lot of them. So it's a kind of more or less standard property of such integrable cases. Even though, of course, there are even more, as Anya was asking, there are even more integrable cases which are completely unstable.
I see.
Actually, Alex, related to the boundedness of the potential. So, as you said, you can make a canonical transformation by sending py to minus I p tilde y and y to I y tilde, for instance. If you do this transformation, you get an Hamiltonian that, if you look at it just by looking at it, you see that basically it looks like a Hamiltonian which is bounded from below, and it has a bounded potential from below. Okay, and this is a canonical transformation. So my question would be like this. So you see, let's suppose I come to you and I give you the Hamiltonian that you would get by doing this transformation, but you wouldn't know anything about, let's say, the Hamiltonian that you are considering as a starting point. If you look at the Hamiltonian, you would say, okay, I have two positive oscillators with some unbounded potential. Of course, just by looking at it, you would say there is no ghost. Then,
may I interrupt you? The problem is there that the point about boundness or unboundness is not invariant with respect to complexification, because we use the square root, and there is, if you remember, x squared plus y squared. If I take proper canonical transformation, making my momentum to be imaginary, my x will be minus ix in that case.
No, you're transforming only
singularities there, and you will have this potential.
You're transforming y, right?
Y doesn't matter, because I have both terms, y and x, and if I transform each of them, like one of them, this thing will be singular.
You mean if you send y minus y in iy?
Yeah. Wait, I can just show you, maybe if I share my screen.
Sure, because they were just a square of variables, right?
Yeah. But you see, it's this. The point is, it's such a transformation. Wait a sec. Let me first start the presentation again, so that you can see what is happening there. Okay, and then let's just take the potential itself.
Yes, sure.
Maybe it's better in this form.
This one,
you
yes.
see, here, the genius of this potential is that it's always the square root. I mean, the argument of the square root is always positive definite. For positive x and y, I mean, like for real x and y. But if I change either x or y, it doesn't matter, because you see, in this way, they're more or less symmetric, right? It doesn't matter.
Yeah.
I change x to ix or minus ix, doesn't matter. Here, the sign will be minus. This square root would become singular. I mean, at some x's, you go to one, or like basically this v would become infinite. And you see, we were considering lambda to be positive and negative, doesn't matter. And actually, what is interesting in this case, they can be arbitrarily large, negative and positive. I can tell you, no way such a thing would be stable in any sense. It's just a singular motion. You would just move to the singularities. You would develop singularities. It's not going to be a healthy system at all.
So you have a singular.
Well, it looks.
Sorry?
You have a singular potential here, right?
Yeah, in that case, it would be singular potential. This one is not singular. That's the point. So you see.
Wait. So the total potential would be the x squared minus y squared over 2 plus b interaction, right?
No. But you see, this is this is the square root of this guy.
Yeah, sure. No, because I plot. Yeah.
Let's do complexification. By complexification, this sign becomes plus.
Yeah.
But inside of this potential, y would get a minus here. I don't know whether you see my pointer.
Sure, I see it. And
you see, if y has a minus here, then you can get a large y and have this potential, this guy to be negative.
But you have y squared plus x squared to the square, which is greater, right?
Yeah, well, sure, but I mean, like it's still. I don't think it's okay. One should check.
No, it remains. I checked on mathematics. I mean, it remains positive. Like
it remains positive. Okay, maybe, but you know, like in some other cases, it. Wait a second. Then basically, wait a second. Suppose we are on. So here it would be minus y squared, right? Okay, maybe you're right.
Yeah, that's why it's like that. The starting potential, if you would do the canonical transformation, is fine, and also there is no ghost in the kinetic part.
Yeah.
So it looks like that what you're doing, you're just finding a way to use a canonical transformation to rewrite the system like if there was a ghost, apparently, but there is no such a ghost.
No. Look, there is a ghost. This Hamiltonian is unbounded from below, and the point is, look. For us, this complexification is only the way to find such integrals of motion, which we can use to bound the system. For example, I can give you a simple example when that definitely doesn't work. You take Kepler problem. Kepler problem is super integrable. And of course, you know that the motion there is bounded. I mean, at least for negative energies. You do complex transformation and you will develop singularities at finite time. So this goes.
I agree. No, in general, of course, it will not work. I would say just for this particular model.
This particular look, we have other examples when it's not necessarily true. I don't think this is related, to be honest. Because yes, you're right. The worst case scenario would be if we complexify, basically make this y to be here minus y squared, and then here it would be y squared plus x squared. This is positive definite. But
my naive question was like if you agree or not. Like for instance, let's suppose I come to you, I give you this Hamiltonian where instead of putting py, I put pi. I mean, I complexify py and y. The Hamiltonian would look like fine. There would be no problem.
Sure, but it's not related. You see, my major point is if we do complexification here. Even though maybe this potential, you're right, maybe there are no singularities, as you see, I never thought about this, but it doesn't mean that it's stable. Because even if your kinetic energy is positive, it doesn't mean that your interaction is stable.
No, I agree with that. I'm saying just for this particular thing.
No, but you see, like, it's very hard to show what is called Lagrange stability. This finiteness of motion.
Sure.
Even for some initial data. For all initial data, it's even harder. And we are talking about normal masses, normal kinetic terms. So therefore, I don't think it's related. And really, this complexification, I don't think it maps trajectories. Because you see, formally speaking, what you would need to do, you take this Hamiltonian system and you declare all these quantities px, py, and y to be just complex valued functions. You could do that. But of course, in that case, your dynamics is not 2 oscillators, but 4. And then you would take kind of I don't know, slices of this motion, or I don't know, some restrictions of these motions. And it's not necessary that these restrictions are I mean, on some projection it's finite, on another projection it's not. So in that sense, I don't think that you can easily infer stability or instability just by looking at let's say you take a normal system without integral of motion and without any ghosts. You think it's stable, you introduce the ghost and you think it's stable again. I don't think so. I don't think it can be proven in this way. Because it's the following way, what is the potential which is cosine hyperbolicus and bounding becomes cosinus in another axis. And that changes whole global properties for sure. Because what is the function which is let's say bounding you, now it's not bounding anymore. And of course, there are more drastic examples, right, of such a behavior. So for example, you may have singularities only on imaginary, on real axis, or somewhere in between. And this will change everything.
Well, I will think a bit more about that, maybe.
Yeah, no, I'm happy to discuss it because this is
because it looked to me that I mean there was no ghost if I made this transform, but yeah, I will think a bit more on. Maybe we can discuss.
Yeah, but you see, the point is you can take
this
whatever
particular
system.
potential, you can just plot it and see whether it's it is stable or not after the redefinition of after
Sure. But it will not. You see that the point is that even if when you plot this potential after a definition, it does not mean that it says anything about the potential before. You see, these questions are not related because this dynamics is very different. In one case, is take potential which is cosine and cosine hyperbolicus. Cosine hyperbolicus for 1 degree of freedom would globally bound your motion, right?
Yes. But this will
normal cosine does not bound your motion at all.
Yeah, but this will happen. This is bounded if the kinetic term has normal sign. Kinetic term with normal sign plus cosine potential. You have good system without.
No, you don't. You see, that's the point. You don't, because cosine potential plus a normal kinetic term does not imply that the motion is bounded.
Hyperbolic cosine.
No, normal one, normal cosine. Because you can move. Look, it's a question of boundness in all phase space, but here you can have energy higher than these oscillations of the potential, and you will fly out as far as you want.
I see. So you want stability in a very kind of, you want a lot from the system.
Yeah. No, of course. Look, this is a very strong statement. Basically, if you want, if we quantize the system, the spectrum will be discrete here because all trajectories are bounded. So it's like a bounded state from the point of view of quantum mechanics. So it's a really strong statement because what we prove both local Lyapunov stability for equilibrium point for the vacuum, and we prove Lagrange stability that the whole thing stays in finite space, finite part of phase space. And this is very non-trivial. I mean, like for most potentials, it's not there at all.
Yeah, that can happen.
Yeah.
By the way, when you quantize, is it a standard canonical quantization?
Yeah, standard quantization. No, look, I'm strictly in favor of having my probability to be positive. And exactly as Masahide said, look, in gravity, energy locally is not even defined or naively can be negative. You know, it's like what Slava Mukhanov likes to say, it's like how difficult is to create a new universe? Not difficult because closed universe has zero energy. Right? Okay. And then it becomes, of course, a question, what does it mean at all to have gravity, basically energy in gravity? But this is a different statement, different level of statements.
Okay, by the way, as you motivated your talk, giving several examples like phantom dark energy and stellar gravity, I'm curious if you have any example without involving gravity, where we require to have some kind of system with ghosts, but good ghosts in quotation. So do you have some example like that?
You mean for field theory? You see,
Yeah,
for field theory, it's very hard because it's much harder to hook up models of this type for field theory. What we see is that for field theory, classical solutions are kind of okay. It's also harder there to say what is stable, what is unstable, but they don't look to be strongly unstable. So definitely, numerical evolution shows you just pretty normal behavior in some cases. And also, see there, it's much harder to check what are the initial data, because you know there is a continuum of functions which you can probe. But at least for reasonable initial data, which we were thinking about, it all looked okay. The question is, of course, what to do with quantum stuff. With quantum stuff, that's more dangerous and more, I mean, in field theory case. In the case of these mechanical models, it will be all fine. I mean, you quantize it and it's just normal system.
I'm curious if people in condensed matter have ever thought about this.
Yeah. No, that's a good question. I actually don't know. I don't know because yeah, would be nice actually.
Okay, Alex, can I ask another question? So please go to page 5 or 6. Explain the Ostrowski ghost through the propagator.
Ah, this one, yes.
Yeah. So yeah, I also use this argument on the propagator for explaining the Ostrowski ghost, but I was asked some question and I couldn't answer.
Okay.
When capital M vanish, what happens?
Look, I think there is a discontinuity there.
Maybe
right?
Slavan asked me. No.
I think
maybe yeah.
I think we had discussion about
Yeah. In the past, I don't have still good answer.
I think I can comment you on this.
This
yeah, please.
Is singular. Probably there. What happens that you start introducing constraints in the model, and then of course these linear propagators, they don't work.
Actually, the best guy who can comment on this is Sergei Vernov. He had a paper about this. It explicitly tells you what happens when you have double or triple or whatever multiple roots or multiple poles. It's just the same procedure, a little bit more technique, but still normal field and ghost, no difference.
No, but you see,
we know the ghost, but yeah. What kind of argument? You see, simple argument to explain why long signature appears when capital M vanish as a propagator.
Simple argument because you have in some of equations you have degeneracy which you have to resolve and you introduce auxiliary variables. So it's not like you have to do this way and write 1 over p to the 4th equal 1 over p squared minus 1 over p squared. It's a bit too, and divided by 0. It's a bit too much, you know.
Yeah, it's a bit.
It's different.
Okay.
Actually, now I remember. Sorry, I kind of a bit misunderstood your question, but actually now I remember when I was very naive and I was a student. We published this paper with Zhenya and our late friend Alexei Anisimov, and there, you know, we saw that it's a degenerate system, and therefore it's okay. Basically, it was called B inflation, and we literally wanted to drive inflation on phi, on box phi squared term, which actually, if you look at this decomposition, it would kind of correspond to this situation with, I think, with 0M, because there's no M. But there is then a grow in 0 mode, also, what was a kind of problem. So, but otherwise, by the way, this system from the point of view of PDEs is stable if you don't include interactions. But of course, if you start including interactions and look how it is, it's kind of not stable. What I think is very important is that from the point of view of classical field theory and guys who are doing PDEs, this ghostiness or non-ghostiness does not spoil well-posedness of Cauchy problem, and that implies that this instability cannot be exponential. So it cannot be as bad as elliptic one. So in a sense, this ghost instability does not spoil hyperbolicity for quasi-linear equations of motion. So therefore, you see, elliptic unstable systems you cannot put on computer without doing something crazy, basically really introducing hard cutoffs there or doing something. This ghost instability, you can put it on computer and really calculate classically what it is. So your algorithm will not break down. That's an interesting point. But that implies some boundness, on some limits on this effects of these interactions. But how does it look exactly? Nobody knows, even for classical field theory.
Thanks.
By the way, there is one more comment here about this. Just recently, I don't remember, maybe in December, it was yet another paper just about 1/p to the 4th propagator from Arkady Zeitlin. It was some paper exactly about this propagator and nothing else. And as I understand, the bottom line system is sick. So just don't bother about it.
Yeah.
Well, actually, I a little bit participated in discussions with Arkady on this paper, and actually we tried to do similar things to optical theorem and non-local theories, but for the simpler case. And it ends up that you cannot fulfill optical theorem if you have box squared propagator, and doesn't depend. Choosing some other types like where to add I epsilon, it doesn't help to overcome this problem. So how classical quantum? Sorry?
Arkady was doing Euclidean, no? Wasn't he?
Well, the point was the transition from Euclidean to Minkowski then.
Yeah. No, of course, this is not trivial because.
Yeah, of course. And the point is the problem with optical theorem arises in this at this point precisely, because you don't have optical theorem in Euclidean series. You need Minkowski transition.
Right.
And it can be shown that if you keep box squared as it is, like a polynomial, you have still a problem.
Oh, that's quite interesting.
Yeah, we actually discussed the funny possibility that you can pretend that that box is not a box but a limit of some non-local operator, which is still polynomial and exponent of entire function. This is possible to arrange, but it would be a really strange limit. But in this limit, the theory is safe.
Interesting. And
a question from Marco.
Yeah, hi. Just a comment about what you just said about this propagator. I just want to say that just because, as I said, someone asked also to me the same, what happens when m goes to infinity and or 0? What was the limit? I don't remember.
0, I think.
0, sorry. No, I just wanted to say that it depends also how complicated is the theory, right? So this is the simplest propagator you can write for a higher derivative scalar. In the case of Stelle, I presented the same propagator just to say what happens in Stelle gravity. That you have this propagator, you have 1/π to the 4th and so on. But you don't have the same m. So the first 1/m in front of everything is m Planck. The mass of the ghost is m Planck times some constant, and that is the constant that you can play with, like sending to infinity, sending to 0. And those limits are fine in that case. So this was just a comment to say that maybe even if this is sick, as Arkady maybe said in his paper, some other might not be in this respect, in this point of view that making limits and stuff, like stellar gravity.
I think it's also important to say that in there is one important thing in stellar gravity. that there's these two terms needed, and due to Starobinsky inflation, we know that coefficient in front of R squared, if we believe to it, right? Because
yes,
fits all observations, that this coefficient is pretty large.
yes.
And it's like 10 power whatever, 11. And that implies that, the question is, what happens with the second term? Why cannot it be there? Because literally, you could claim that we observe Starobinsky inflation. At least so far, there's nothing contradicting to the statement. And this would be the most elegant of all inflationary models, arguably, just based on gravitational action. And then the question is, okay, we practically measured the first term. Why not? What happens with the second?
Sure.
But
the second term can stay stable. It's a stable situation that the second term is small. I mean, stable with respect to running of beta functions of all this stuff.
Yeah. These two terms are not connected. Of course, it's a bit strange to have such a hierarchy in coefficients, and also the origin of these coefficients is not entirely clear. But one can easily understand that, for example, usual arguments involving, say, evaporation of black holes, the second term, the Starobinsky basically term, doesn't change the picture. Whereas the Weil squared, would change the picture quite significantly. And what does it mean? I don't know. Of course, there is a speculation that these ghosts may be confined, and then you don't see them as 3 degrees of freedom at all, if they're strongly coupled. But to see that, I don't know.
Or decoupled.
Oh, well, decoupled is harder to see there probably, but if they're strongly coupled, then okay, you don't see them. That's possible.
It's important to understand clearly the behavior of ghost in the stellar gravity. At least in a not long ago paper, the Weil square term actually bad if you introduce large anisotropies. You will end up with singularities, at least in the context of cosmology, like Kastner type singularities. So anyway, even if you argue some kind of with prescriptions that stellar ghost in stellar gravity is good, not harmful, but still it will lead to a lot of classical instabilities if you go to backgrounds which are complicated than simple FLRW.
Sure, but it's the question, you see, whether this is, whether you're allowed to use this term on these scales, whether it's really there in a sense, right? Because of course, if you go to scales where these ghosts can kind of appear, right, and they're massive ghosts actually, and then the key point is the following: if you just forget about stellar original motivation and you want to treat it as effective field theory, the oscillations of these ghosts are too high, so you will smear them out and throw away, right? On the other hand, if you are not thinking about effective field theory in these terms, but you are thinking about production of them, then nothing forbids you from creating two of such ghosts and two of highly energetic normal gravitons, naively, out of empty space, right? And you could have billions of them. You could create billions of gravitons and billions of these guys, and nothing forbids you from doing that.
Yeah, let's say that recently there have been several approaches how to deal with these ghosts. I think even Marco Piva.
Yeah, but well, the question, the context, Alex was saying about black holes and the effect of Weil square term. So, well, surely even before dealing with the ghost, we first need to understand how collapse happens and what kind of object you really form. It can be Schwarzschild or maybe not, because there are other class of solutions with naked singularities like two holes. So it is not clear what kind of object you can really form in this class of theories.
Yeah, but maybe if your curvature is actually much smaller than the energy scale, which is basically m Planck, and then this whatever divided probably by this coefficient in front of Weil, then you would not care, no? Naively, you should be able to
naively, yes.
The same.
I agree, but I don't know about end stage of collapse. In
Oh
the
well,
beginning
end stage of collapse,
yeah.
nobody knows. I mean, because nobody
Okay.
knows. Nobody knows how the true gravity looks like in this case.
Maybe I don't know if
maybe
from the audience there is some other question related to this morning talks, or we can just.
I have a question to Yufu Sai, if he's around.
You mean the first speaker?
Yeah.
Yeah, Yufu.
Okay, maybe he's not around.
Hello.
But...
His
Okay.
ghost is around. It's okay.
Okay.
Yeah. So yeah, I mean it's 10 minutes past 12. The discussion session meant to end at 12. But of course, if there is any question or urgent discussion, we can.
As I guess, we reconvene at 1:15, right?
Yeah.
Yes, 1:15 in Europe, Central European time. Yeah.
Right. Okay.
Okay, then.
Okay, I had a kind of sorry for raising again this issue with ghosts. I have a question to Sasha. Actually, I just plotted the potential you have. Just for fun, I can show it.
Yeah. No, I agreed, of course, because
this is after changing after the canonical transformation. So it seems like a very well bounded potential.
Yeah. I agree.
And this is, I mean, you can just define your new coordinates and forget about the original ghosty formulation.
Oh, but you see, this would be again, the point is, it may be true for this particular model, but you cannot use this argument to prove anything. That's the point.
I mean, in general, it's not true. I think we agree on that.
Of course. I mean, but the point
even
is,
no, look, even not in general, even for this particular potential, it's not true.
But it's still a bit puzzling.
In the following sense that, look, this transformation, think in the following perspective. The dynamics, when it's complex and when it's not complex, has nothing to do with each other.
But it's a canonical transformation, right? You said.
Yeah, but canonical transformation.
I did a canonical transformation and plotted the potential. The potential, the system, I know that dynamical system with such form of the potential will always have bounded solutions. You can never go to infinity with that.
No, because again, think of the only way. Take potential, right, which is completely fine for real coordinates. Completely fine, normal dynamics, no ghosts, nothing, it's all trajectories are bounded. Now you change this potential to imaginary axis. This potential can have absolutely different features. It can have singularities, it can have whatever. Anything what you infer from real axis is not applicable to imaginary axis at all.
Yes, but at the same time, I changed the kinetic term of my.
Sure. But it doesn't mean anything. Look, it's completely two different systems related through transformation. But this transformation does not preserve any of the properties of stability or anything.
Well, I mean, I know how to study, more or less know, well, as I would say, I better know how to study stability when my kinetic terms are normalized in such a way that there are no minus signs. So I'll capture all minus signs in definition of the fields, like
yes. Look, I agree. My statement is the following. You take a system which is positive definite, forget about integrability, forget about everything. Take general systems with positive kinetic terms, with normal potential, bounded. Their motion is bounded, all good.
Yes.
It doesn't mean that after you do complexification, this remains the same. Not at all.
Well, I mean, why it should not remain the same? Because
very easy, because it doesn't mean that you just map this whole trajectories in the same thing.
Sure, but it does not mean that I have a ghost, right? It's nothing to do with ghosts.
You do have a ghost. Look, that's a strange. Take a system, right? It doesn't mean that you really can just rotate this whole solutions, because you don't know what is happening there.
No, but the question, I think.
Look, most simple example. Let's consider Lagrange stability. Let's take cosine hyperbolicus potential, 1 degree of freedom. Motion is bounded. It's all good. Now I do complex transformation, right? Now I have one ghost, right? And cosine potential. But it doesn't matter. It's 1 degree of freedom, right? The question is, are the trajectories bounded or not? No,
but would you say this is whatever happens? So we would say that you have a ghost in this theory, a ghost instability, like in terms of Ostrogarsky ghost? No, you wouldn't.
No. Look, that's even more strange thing, because think
may I ask you on the way?
Yeah.
Why at all should I complexify my system if I can already make it canonically normalizable and looking great? I think I will do it only if you really need it. If you really started with something like gravity, for example, to which you already know how your system has coupled.
Look,
unless it is the case, I would stop at the canonically normalized system and be happy.
No. Look, forget about this complexification. In the following, it was only way for us to derive things. We were lazy. We didn't want to repeat the same procedure with different signature convention for kinetic matrix. What I want to say you is a very simple thing. Take that the dynamics, when you do complex transformation, does not preserve the property of stability or instability. The trajectories are completely different. Let me give you an example. Take 1 degree of freedom, just one. Take cosine hyperbolicus potential, right? Then the motion is bounded, always, for all energies, correct? Now I do complex transformation. I have a ghost plus cosine potential, but cosine, not cosine hyperbolicus, cosine. But the point is that then it doesn't matter whether I have a ghost or no ghost, because I can invert potential, doesn't matter. But clearly I can have energy higher than the value of the peak of this cosine, and then my motion is unbounded.
But I think we agree.
What are your initial conditions? Are you
arbitrary
initial conditions real coordinates or
no, look, arbitrary? That's the
arbitrary is okay, but are they real or complex?
Real or imaginary? Or
no. They're all real. Real again. That's the point.
Okay, real and your variables which you define as okay. Now I see the difference.
Yes. So look,
my system would be equivalent to yours if I take for initial conditions something like
imaginary values
I and y equal to 1.
Yeah. So
but is it consistent to complexify system and then don't change initial conditions?
No. But you see,
why do you say no? I'm just asking.
Look, it's two different situations. One situation exactly as Anya described. Let's do complex transformation, but then keep these values exactly complex. Sure, in that case, dynamics is the same because you have not done anything. But no, we want to have to be them real. And this changes everything. So therefore,
I'm now asking, is it consistent with respect to original system to do this?
No, because it's a different system. It has nothing to do with each other. The only thing what is preserved is the point that the integral of motion is also integral of motion. But all dynamics, the form, or everything is completely different. It has nothing to do with each other. That's the point.
Well, I see the conclusion actually comes from something that we used to think about quantum theory, like where we know some sort of initial conditions like Bunch-Davis vacuum, and this is you define your Bunch-Davis vacuum starting from the point where you normalize fields canonically. And then you know what is the condition, but
of course. But
if you allow some imaginary conditions, then
this is a crucial point, that if you take normal field theory, you cannot plug in their imaginary numbers, because that would make out of Hermitian operators anti-Hermitian. And this is not normal quantum mechanics, right? So your operator should be Hermitian. And if you multiply Hermitian operator with I, it's not Hermitian anymore.
No, if you just multiply with I, it's not so bad. It's okay. It's just anti-Hermitian and you
Sure,
go.
sure. It's not so bad, I agree, but nevertheless, it does not.
If you multiply by 1 plus I, then it's a real problem.
Look, I agree, but nevertheless, the standard postulate of quantum mechanics that is Hermitian. And if you introduce anti-Hermitian, then you would need to change the norm to get the probabilities and do all the things, right?
Yes.
So, and this is exactly the key point. So here, this complexification, it's only a tool to derive a new system. The system is completely new because it allows different motion. Just we would know that because, this complexification does not change taking derivatives, right? That there is this integral of motion there. Nothing else. But whole dynamics is completely different. Like this example with cosine, if you have cosine and energy is larger than the amplitude of these oscillations, you fly, and you fly infinitely far away. If you have cosinus hyperbolicus, doesn't matter how high is your energy, you will be always bounded. So therefore, even for 1 degree of freedom, such a transformation does change physics. If you take them in interaction, in order not to change physics, you would need to use, exactly as Anya said, complex initial values. Then physics doesn't change, yes. But that's not what we want. That's true.
Okay.
But thanks. I think this is a good point because this can cause confusion for people, and I think it's good to explain that really it has nothing to do. I think Sasha Kamenchik and somebody else, they were trying to do to claim stability of ghosts by argument of this complexification. But of course, this is a very dangerous game.
Mm-hmm.
Yeah, I see your point now. Thanks.
Great.
Thank you. Okay, so I think now it's time maybe to go for lunch or dinner. I don't know where people are. And I think the second session will start at 1:15 Central European Summer Time or 7:15 China time.
And I will be your chairman, right?
Yes, Sasha, you will be the chair, yes.
Jawohl.
Okay, so thank you very much
see you in a
again.
bit. Thank you.
See you.
Thanks, everyone.
See you soon.
Yeah.
Alexei.
What? Just hello. Yeah. Hi.
I
I will
think we'll
decouple for half an hour. I need some break.
Okay, see you in a bit.
Yeah. I will not shut down Zoom, but I will decouple.
Okay. See you.
Hello. Astrid, do you hear me? Are you
Yes,
around?
I can hear you. Yeah.
Ah, nice.
Hi.
Great. Nice to meet you.
Hi.
Yeah. I am not so early because quite a short break after first session to get at least some dinner or whatever here in China. Hmm. So because I made you a co-host, you should be able to share slides.
Yeah. Shall I briefly try that?
Yeah, if you want. Maybe it's good to try because the first day we had two speakers who are not able, but for you it's okay.
Yeah, I think now you can see them in full screen, right?
Yes, exactly. Yeah, very good.
Now I'll stop sharing again for now.
Yeah. Okay.
Alexei, may I also check mine?
Hello. Yes, sure. You
Hello.
can check. Yes, sure. Check it, please.
How I do it?
Sorry?
How I do it technically? Okay. Share screen.
Technically, you press share screen and select desktop. You see, you can share, no problem. Great.
So it works.
Yeah.
Okay,
so
good.
we see your screen. Very good.
Okay.
No, you see, the problem which some people have is exactly not updated Zoom. As simple as that.
Okay.
For the rest, it's okay. So is it now around 9 o'clock around 8 o'clock, yes, in Brazil?
Yeah, 8:08 in Brazil.
I see. Very good. It's 7:08 in the evening in China.
Good.
Yeah.
So it's
Kind
really
of.
worldwide conference.
Yeah. Yeah. We prove that Earth is rotating by construction.
Well. Some people will not be convinced, but it depends.
No, I mean.
Hello, Ilya.
Hello.
Where is our chairman? What?
No. I just said hi to Astrid.
Yeah.
Yeah.
No, I was trying to understand where is our chairman.
Well, Sasha knows.
I hope that he knows where is he. Yes. Up to this extent, I have no doubt.
Oh, we still have 5 minutes.
Before the last word he said is when is the time? So yeah, surely he remembers. Well, we still have 5 minutes.
No, for me it's fine. And where is Philip? I'm curious about this.
Alex is here.
Sorry. Hi, guys. So, hi, Astrid. I'm your chairman.
Hi.
Hey, good to see you.
Good to see you as well.
Okay. So we have 3 more, right?
Yeah, we have a little bit of time.
Astrid, what do you prefer? If people interrupt you when asking questions, or if it is possible?
I'm happy with questions during the talk, and unless there's like a super big discussion, then that is maybe more better to be postponed at the end. But I'm certainly happy to be interrupted with questions.
Sure. Okay, very good. Yosha, are you in the office, or you're where? Are you at home?
Yeah, I'm in the office.
Oh,
yeah, but you see, for me, it doesn't make any difference too much, because my apartment is, even if I'm extremely super slow, like 10 minutes walk out of office, So it doesn't make any sense for me to move here or there.
Okay.
Because they here provide you apartment just on the campus, so just.
Oh, nice.
Yeah.
You can also have a bed in your office, some kind of couch.
No, you see, I don't need this, because if I need really something like that, then I go to my apartment. Why should I mix these two things?
Yes, that's true.
But apartment on campus seems to be extremely convenient thing, indeed. When you have literally 10 minutes at most of walking, no matter what.
How far is it from downtown, from, let's say, Bund?
Well, from downtown, it's quite distant, but maybe this is also not so bad, because it's less hectic, chaotic, and much clearer, I would say.
But you said how far is it? Sorry, I missed.
From downtown, it's like 1 hour by metro.
No, it's okay. For Shanghai standards, it's not bad.
Yeah, it's not bad. But what is good, around our campus, practically area is almost empty. Almost.
That's cool.
So it's like, for example, it's not polluted, almost at all, not polluted.
Oh, that's great.
And for Shanghai standard, it's also extremely non-standard, I would say.
No, of course. Okay, guys, we have 1 minute, no?
Yeah.
So
one day, Sasha, you should come here and you will see all of this.
Looking forward, man. Actually, for Shanghai, for up to a week, foreigners don't need a visa, I think.
Foreigners? No. Maybe you mistaken with something.
No. It used to be the case that you can be on transit. If you can claim that you stop in Shanghai for transit for up to...
Hi, Sasha.
Hey, Antonina.
Yes, you're right. You don't need the visa if you're in transit. It's still the case.
Perfect, Antonina.
Well,
so
I didn't know this.
You can come back at any time if you're on your way to
I'm happy to.
Japan or some other place.
Sure.
So, Sasha, just transit here from time to time. It's a bit expensive, but...
Oh, it's nice. It's nice. I like it. I like you guys. Okay, so look, but with this, we need to start Astrid's talk. I think we can wait. Okay, now we should not, maybe. And so it's our great pleasure to have Astrid Eichhorn today from Southern Denmark and CP3 origin. And Astrid will tell us about what can quantum gravity teach us about dark matter. So Astrid, welcome.
Yeah, thanks. Let me start my screen share and jump right into the talk. Yeah, so indeed the question I'll be asking, which I think you can now see in full screen, is what can quantum gravity teach us about dark matter? And I'll take some time to motivate why I think it's a useful idea to bring together quantum gravity with dark matter. And then I'll present some explicit results in the asymptotic safety paradigm. And I'll also take a little bit of time to introduce asymptotic safety and give an introductory overview into that approach to quantum gravity. So let's get started with the motivation. So connecting quantum gravity and dark matter, why should we do so? So usually quantum gravity and dark matter are their own two separate research fields that exist quite happily on their own. So why should we actually be looking for connections? So let me expand on that topic a little bit by sort of reviewing what these two fields are about. So in quantum gravity, what we try to answer is questions like, what is the quantum structure of space-time? What is the fate of space-time singularities? What is the true nature of black holes? So various questions that deal with the quantum properties of space-time and gravitational fields. The questions that we're asking in dark matter research are quite distinct. So there we are asking questions such as whether dark matter is a scalar or a fermion or a vector, whether it has self-interactions, whether it's even one field or whether it consists of a whole dark sector, and how that dark sector couples to the standard model and questions like that. So looking at the two research fields like that, it doesn't actually seem that there are a lot of questions in common, so it's not immediately obvious why we should actually be connecting the two. The reason that we should be doing so, it's actually two reasons. What I will advocate is that in trying to understand the connection between quantum gravity and dark matter, or in trying to establish such a connection, we can actually tackle one of the most significant challenges in each of the fields. And within quantum gravity, I would say the most significant challenge is to actually make quantum gravity testable. We have a variety of contenders for a quantum theory of gravity, and we don't know whether any of those is actually a proper description of quantum gravity in our universe. And the main reason why we don't know that is not, I would say, a question of internal theoretical consistency. It's actually a question of connecting the theory to experiment. And as I will be arguing, at least within some approaches to quantum gravity, specifically within asymptotic safety, we can actually make a connection to particle physics, and we can actually make predictions about what the structure of dark matter can and cannot be in such a theory. And thereby, by experimentally searching for those dark matter fields, we can actually at the same time test our assumptions about quantum gravity. And I'll explain in more detail how that works. On the other hand, why is it useful to connect dark matter to quantum gravity? Well, here again, I would say that what we can achieve there is to address probably the most important challenge within that field, and that is that within dark matter research, there is a proliferation of phenomenological, to some extent, sort of ad hoc models, so models which are motivated from a bottom-up perspective, but not so much from a top-down perspective. And so there's a huge variety of different models, and many of those models on their own have already quite a significant parameter space. And so taken as a whole, there's just a huge phenomenological parameter space for dark matter. And that is, of course, being searched through experimentally in part, but not all parts of that parameter space are accessible. And so what I would argue what we need here is more theoretical input that allows us to narrow down that parameter space and to give us a smaller class of theoretically preferred dark matter models. And so what I hope I can convince you about with this talk is that connecting quantum gravity to dark matter achieves both of these things. It makes quantum gravity testable, and it allows us to reduce the parameter space for dark matter. So in this talk, what I will do is then focus specifically on asymptotically safe quantum gravity with dark matter. I'll spend some time in giving an introduction to the asymptotic safety paradigm, and also explain where the predictive power of the paradigm comes from, because that predictive power will be crucial once we then include dark matter into the picture. And I will then talk about two specific dark matter models. One is a WIMP-like, so weakly interacting massive particle-like model, where I will show you how asymptotic safety imposes strong constraints and actually rules out some of the simplest WIMP settings. And then I'll move on to another popular dark matter candidate, namely axion-like particles. And I'll show you the implications that asymptotic safety has for those, and that it also rules out at least the simplest models of ALPS. I'll then also give you an outlook and highlight some sort of out-of-the-box ideas of what dark matter could be that fit more naturally into the asymptotic safety paradigm. So let's get started with the first point, the introduction to asymptotic safety and where its predictive power comes from. So asymptotically safe quantum gravity plus matter and dark matter, that is a paradigm for a quantum field theory of all of these fields. And so the starting point will be this path integral over metric fluctuations and over all of the matter fields in the theory, weighted by the exponential of some action. And within perturbation theory, at least, our starting point would be just the Einstein-Hilbert action for the gravity part, and then the standard model Lagrangian minimally coupled to gravity, and then also some Lagrangian for the beyond standard model part, in particular, including dark matter fields. And each of these three parts actually on its own has a problem, at least within perturbation theory, and I will show you or I will hint at how asymptotic safety could solve each of these three problems. Now, the problem of the gravity part is very well known. It's the perturbative non-renormalizability, which implies that as we go to successive higher orders in loop calculations, we get successive higher orders in curvature invariance due to the mass dimension of the Newton coupling. Each of these counter terms comes with its own free parameter, its own coupling that has to be fixed by experiment. And so we have a proliferation of free parameters as we go to higher loop orders. And so the breakdown, the predictivity of the theory just breaks down. Now, the standard model part also has a problem, and that is Landau poles, or more properly, triviality problems. So you can see those if you look at the scale dependence or at the running of the couplings in the standard model, for instance, at the abelian hypercharge, the screen coupling here, that approaches a Landau pole in perturbation theory. And beyond perturbation theory in lattice studies, you can show that indeed the breakdown of the theory due to the triviality problem persists. And so you associate that scale of the Landau pole with the scale of new physics. And here we're actually already getting an interesting hint, because there is a Landau pole both in the abelian hypercharge as well as in the Higgs quartic coupling. And before the mass measurement of the Higgs, we didn't know whether that a Landau pole in the Higgs quartic coupling comes before or after the Planck scale. And now we know that all of the Landau poles in the standard model occur at trans-Planckian scales. And so the scale of new physics that the standard model is telling us it has is actually larger than the scale of quantum gravity. And so I think that's a very interesting hint to say that maybe the only new physics that we need to add to make the standard model consistent is actually just adding quantum gravity. Of course, we then need to add beyond standard model physics for phenomenological reasons, for instance, to accommodate dark matter. And I would say that one of the main problems of that beyond standard model part is that it's just too unconstrained. There are too many options, and so we have huge parameter spaces that are in principle theoretically viable. Now, all of these three problems, I claim, could be solved by quantum scale symmetry, which is also known as asymptotic safety. How could that be a solution to all three? Well, quantum scale symmetry, because it's an enhancement of the symmetry, it actually relates the various couplings in the higher order curvature terms to each other. It actually leads to an infinity or an infinite set of relations. And so it solves the breakdown of predictivity and results in just a finite number of free parameters. I'll give you more details about that later. It also solves the second problem, the Landau pole problem, because quantum scale symmetry means that the couplings have to either become constant or drop towards zero. And in either of the two options, clearly they can't approach Landau poles. So if by adding quantum gravity to the picture, we can achieve asymptotic safety in the standard model, then we have solved the Landau pole problem. And finally, the third part, the sort of arbitrariness or the many options in the beyond standard model part, that is solved because quantum scale symmetry as an enhanced symmetry is not achievable in just an arbitrary model that I write down. In general, it requires a particular field content or particular values of the interactions. And so therefore, by demanding asymptotic safety in the beyond standard model part, we can reduce these many options to just a small handful of options. So let me go in a bit more detail on how this is achieved. So let's talk about quantum scale symmetry for a bit and what makes it a special form of symmetry. So since Noether's theorem, of course, symmetries play a crucial role in basically most of the things that we do in fundamental physics. Most of the models that we write down have some form of symmetry. There are in particular models that have classical scale symmetry, which means that under scale transformations, the theory doesn't change. The symmetries that we typically think about are symmetries that are already present in the classical theory, and where once we go to the quantum theory, we then ask whether or not there is an anomaly. Now, quantum scale symmetry is different in that respect, conceptually different, because here we are actually asking whether a symmetry can emerge at the classical level. Now, scale symmetry as such is generically something that you wouldn't expect in a quantum field theory, because quantum fluctuations give rise to a running or a scale dependence of couplings. And so from this sketch here, you can very clearly see there is no scale symmetry in the theory. From the values of the couplings, you can always tell which scale you're actually at. Now, of course, you can get scale symmetry back in a setting like asymptotic freedom, where essentially you switch off the effect of quantum fluctuations. And so in that sense, you're getting back to you can get back to a setting that is classically scale symmetric. There is a more non-trivial possibility, and this is really what makes quantum scale symmetry special. It's really a quantum form of symmetry. So it really relies on quantum fluctuations being present. It's not a symmetry that we realize at the classical level. It's that there is a symmetry that we realize only in the presence of quantum fluctuations, so only in the quantum theory. It's asymptotic. It consists in asymptotic safety. So in the couplings actually approaching finite fixed point values of the renormalization group. And because they are finite, it means that quantum fluctuations and interactions are in general still present and actually need to be there in order to balance out and give you scale symmetry or quantum scale symmetry. And so in that sense, asymptotic safety really sort of stands out from the symmetries that we typically consider. It's not a symmetry that we impose at the classical level and then ask whether or not it persists at the quantum level. It's a symmetry that is actually first generated at the quantum level of the theory. Now, in quantum gravity specifically, the main interaction to consider is actually, or the main coupling to consider is actually the Newton coupling. And what we are considering is the Newton coupling multiplied by the RG scale squared. That is a dimensionless number. And you can think of that as giving you the effective strength of fluctuations of quantum gravity. And the idea about asymptotic safety is that that dimensionless number is constant above the Planck scale. And then at the Planck scale, quantum gravity fluctuations dynamically start to become weaker. And you therefore get out of the scale invariant regime. And instead, this dimensionless strength of the measure of gravity drops quadratically towards zero. And if you're at scales around 10 GeV to 10 TeV, sort of LHC scales, you can see that this dimensionless measure of the strength of gravity is really tiny, which means it's a great approximation to neglect quantum fluctuations of gravity at the LHC. So cutting a rather long story and a lot of literature quite short, there is compelling evidence that this sort of sketch is actually something that describes the behavior of gravity, at least under a number of assumptions. And some of these assumptions are actually being investigated sort of as we speak, including whether the scenario can be realized in Lorentzian signature and whether it actually gives rise to a unitary theory. So I'm happy to discuss these points further if you have questions. about that. But for now, I would move on in the direction of phenomenology. In order
Can I ask a short question?
Yeah, sure.
Yeah. Well, since you are aiming to explain dark matter, but why do you look at only from the matter point of view? There are also proposals saying dark matter could be some form of modified gravity. So since your motivation is from quantum gravity, do you think some way to explain dark matter with modification of gravity rather than adding particle content?
Yeah, so I wouldn't make such a strong distinction between adding matter and modifying gravity, in the sense that in modified gravity settings, to explain sort of a modified the modified rotation curves of galaxies, what you do in these settings is you also add new fields. So for instance, you add scalars, vectors, or potentially even tensors. And so whether you think of these as matter or as modified gravity, really in some sense is just semantics. You end up adding new fields to the theory, right? And you call them matter if you write them on the right-hand side of the Einstein equation, and gravity if you write them on the left-hand side. But I would argue that that distinction is not that important. And what I will be trying to show you here is that asymptotic safety as a paradigm is quite predictive. And so you can essentially take whatever your favorite phenomenological explanation of dark matter is, and whether you call that matter or modification of gravity, and then ask, is that model asymptotically safe or not? So that's sort of the general spirit. So I don't necessarily aim at very particular dark matter models. I'm just trying to show you that it's a predictive paradigm that can actually constrain physics beyond GR and the standard model quite a lot.
Okay, thank you.
All right, so if we want to do that, we of course need a tool which we can let loose on our quantum field theory and search for asymptotic safety. And the tool that is typically used is the functional renormalization group that I'll just very briefly highlight here. It basically allows you to integrate out quantum fluctuations in a path integral starting from the ultraviolet all the way to the infrared. It is based on a formally exact equation for the quantum effective action as a function of scale. The right-hand side encodes how the scale dependence in this theory is driven by quantum fluctuations. And the key thing is that from this general equation, we can extract the beta functions for all of the couplings in the theory. And with that, we can then do two things that allow us to connect to phenomenology. First, once we have the beta functions, we just search for their zeros to discover whether or not there is actually asymptotic safety or scale symmetry. And if the answer to that is positive, then of course we want to connect this microscopic scale invariant regime to scales where we can make measurements and observations. And so we can use the same beta functions, typically integrated numerically, to obtain the couplings as a function of scale, and then consider low values of the scale to understand what the implications of asymptotic safety in the UV are for the infrared. Of course, that method is also subject to systematic uncertainties. Within this method, they arise because the full effective action is typically truncated to a finite subset of operators, and that gives rise to systematic uncertainties. And that is also the case for all of the statements that I will be making in this talk here. Now, what will be really crucial for me is how quantum scale symmetry generates predictivity. And the main mechanism for that relies on the fact that quantum fluctuations can either screen or anti-screen interactions. And we have examples of both behaviors in the standard model. For instance, in quantum electrodynamics, we have screening, and that's encoded in the fact that the leading order term in the beta function is positive. And that means that as you lower the RG scale, as you go to larger distances or lower momenta, the coupling will decrease. So it's being screened by quantum fluctuations. The opposite behavior you have in QCD, where you have a negative sign. And that means that as you decrease the RG scale, the coupling increases, so it's being anti-screened. And now, if you want to achieve quantum scale symmetry in general, you balance screening with anti-screening terms so that you get non-trivial zeros of the beta function. And depending on how you do that, you can either get a prediction or you get a free parameter. So if we first consider the case where we have the leading order term being a screening term and the higher order term being an anti-screening term, then it means the following. If we start with scale symmetry in the UV, and if we depart from that to slightly lower values of the coupling, then the screening behavior kicks in and drives us to even smaller values of the coupling. If we depart towards slightly larger values of the coupling, then the anti-screening behavior kicks in and drives us to even larger values of the coupling. And so if we demand scale symmetry somewhere in the deep UV, then we can still reach a whole range of couplings at the Planck scale. And so this is how we're getting a free parameter, or what is called a relevant coupling. Now, if we just switch the screening and the anti-screening around, so if we have a leading order anti-screening and a higher order screening term, then this is how we get a prediction for a coupling, because then no matter whether you depart towards larger or smaller values of the coupling, quantum fluctuations always drive you back towards scale symmetry. And so if you have scale symmetry in the UV, then you will also have one special value of the coupling at the Planck scale. And so this is what we call an irrelevant coupling, and this is how we get a prediction from the theory. Now, that predictivity is already at play in pure gravity, and there are numerous examples of that in the literature. I'm just highlighting some of those just to give you some idea of what are some of the interactions that have been considered, and they include all sorts of higher order gravitational terms. And you remember that in a perturbative quantization of gravity around the free fixed point, all of these would be counter terms, which would correspond to free parameters. But now if we want to achieve asymptotic safety, it turns out that most of those actually have to take on particular values. And so in this plot here, you see the critical exponents. If those are positive, then that signals a free parameter, and a negative critical exponent signals a prediction. And so you see that most of the critical exponents here, except 3, are actually negative, which means that most of these higher order couplings are actually predicted by asymptotic safety. The 3 free parameters are the Newton coupling and the cosmological constant that can, in fact, in the infrared, reach values that correspond exactly to the observed values. And then there is one more free parameter that corresponds to a superposition of these 2 curvature squared couplings. And if you are a fan of Stravinsky inflation, for instance, you can use that free parameter to adjust the coupling of the R squared term just as needed. You can also adjust it to be something smaller so that you don't get Stravinsky inflation. Now, all of the remaining gravitational couplings are then predictions of the theory, which of course it's nice, it makes a highly predictive theory. However, for phenomenological purposes, it's not that interesting, because phenomenologically, we don't have observations that allow us to constrain higher order gravitational couplings to something of order 1. There are constraints for the curvature squared couplings, but they are at values significantly larger than 1. And so the predictions that you're getting out of pure gravity and asymptotic safety are not something that we will be able to test in the near future. And this is where it becomes interesting to think about the effect of matter. So again, cutting a longer story short, there is now good evidence that the following type of picture is realized. If you take asymptotically safe quantum gravity and you couple it to the standard model, then at Transplanckian scales, you're getting a quantum scale invariant regime where the couplings are either asymptotically safe, so constant, or they approach asymptotic freedom, so they slowly go towards 0. Then what happens at the Planck scale is that the Newton coupling, this dimensionless version of it, transitions from scale symmetry into this regime where it drops off quadratically. And so this means that at the Planck scale, the interaction strength of gravity decreases quite rapidly, which means that quantum gravity fluctuations decouple dynamically from the theory. And then in the infrared, you're getting a regime where essentially the theory is just the matter theory, and the RG flow is just driven by quantum fluctuations of matter. And now the key point about this whole idea is that there can be predictions of couplings in the standard model, because some of the couplings in the standard model could correspond to irrelevant couplings at an asymptotically safe fixed point, or in other words, their Planck scale value is not arbitrary but fixed. And there are indications that that is realized, for instance, for the Higgs-Cortic coupling, for the abelian gauge coupling, the top Yukawa coupling, and the top bottom Yukawa coupling. So before I move on to dark matter and to set the stage, let me actually give you sort of a proof of principle of how this idea and the predictivity for the matter sector works, and I'll focus on the gauge sector here. So this is the leading order beta function for a gauge coupling, G, that can be either an abelian or a non-abelian gauge coupling. That doesn't matter at this stage. There is a quantum gravity contribution to that is linear in the gauge coupling. And where this Fg is just a short notation for the effect of quantum gravity. So it's actually a function that depends on the gravitational couplings, for instance, Newton coupling and cosmological constant and so on. The key thing about this Fg is that it's constant and larger than 0 above the Planck scale. And then because the Newton coupling drops to 0 quite quickly, or towards 0 below the Planck scale, this Fg drops to 0 below the Planck scale. The Fg is also universal in the sense that it doesn't depend on the gauge group. And that's simply because gravity doesn't know anything about internal indices or internal symmetries. Gravity just knows about whether it's coupling to a vector or a fermion or a scalar. And so therefore this Fg is independent of the gauge group. Let me make one brief, somewhat more technical comment on the Fg, because in the literature this has been calculated both in the context of asymptotic safety as well as in perturbation theory. And there are some different results in the literature, because it's been shown that Fg vanishes in some schemes, for instance, in dimensional regularization. And that, of course, would call into question whether there is a quantum gravity effect on matter. Now, there's a subtlety that Gustavo De Brito, who's a postdoc in my group, and I discussed. And that subtlety is that in these studies where Fg was shown to vanish, the gravity coupling is actually treated as a fixed external parameter, which you shouldn't do in asymptotic safety. So we gave an explicit example. We calculated the Fg in a setting where we have a free parameter, A, that sort of implements different schemes. And you can see that at small a, the leading order behavior of this Fg is that it scales with A log A times the fixed point value for the Newton coupling. So if you treat that fixed point value as a fixed parameter, and you take A to 0, then you would conclude that Fg vanishes. However, the fixed point value of the Newton coupling, if you calculate it in the same scheme, it actually scales with 1 over A log A. And so if you combine that behavior and then take the limit A going to 0 in a consistent way, then you're getting an Fg that is non-vanishing. And so this is what we think explains some of the differing conclusions that have been achieved in the literature. And that it shows that if you do things consistently and take into account that you should calculate the fixed point value for the gravitational coupling, then indeed you get a non-vanishing Fg. So with that, let me close this more technical bracket. And let's go back to the implications of that beta function. So because this gravitational contribution is negative, it means that you preserve asymptotic freedom for non-abelian gauge couplings. And you're getting a very interesting effect for the abelian gauge coupling, because for the abelian gauge coupling, the beta 0 is positive. And so you get a competition between a negative gravity contribution and a positive matter contribution. And that competition means that there is one specific value at which you achieve asymptotic safety. And it also means that you have a leading order anti-screening term and a higher order screening term. And this was exactly the combination that we needed in order to get a prediction. And so from scale symmetry in the EV, there's a unique value of the coupling that you get out in the infrared. And so this is how asymptotic safety is predictive for some of the couplings in the standard model. And with that general introduction into the predictivity, let me now move on to specific results about the dark sector, where the main aim besides sort of showing which dark matter models work and which don't work, my main aim is to show you that asymptotic safety as a paradigm is really predictive, and it can therefore be a selection principle for dark matter models. And I think there was a question.
Is there a question?
Or at least I heard something, but
I'm sorry. May I actually? It wasn't me who the person who made this sound, but may I make a question?
Sure.
Thank you. Yes, actually, in the last slide, I didn't get the meaning of the FG. Can you explain one more time, please?
Yeah. So the FG that parameterizes the effect of quantum gravity. So I can show you, maybe this expression helps. So as a function of the Newton coupling at the cosmological constant, this is what this FG looks like. So this happens, or this arises when you integrate out quantum fluctuations of gravity, just in the same way as the beta zero arises if you integrate out the quantum fluctuations of matter. I'm just writing the shorthand FG instead of showing this more extended function of the gravitational parameters, because in this schematic way, it's sort of easier to see what is going on. But what the FG is doing is this just captures the effect of loop integrals over metric fluctuations. Does that answer the question?
Yes. So it actually this term can somehow make a kind of it can help on the asymptotic safety scenario somehow. I mean, because it can somehow, I don't know, compensate the first term. I mean, that's actually increasing time.
Yeah,
so
exactly. Yeah. So the physical effect of this term is that it's an anti-screening term, and so therefore it can balance out this screening term that we have just in the standard model, and this is where you get asymptotic safety from. So this is where you can get a scale symmetry in the UV. So this you only achieve because there is this quantum gravity contribution. Without the quantum gravity contribution, you would just have the positive term, and you would just run into the Landau pole for the abelian gauge coupling.
yes, that actually happens in the Higgs sector. I mean, right, with the as you mentioned, right?
Yeah. So in the Higgs sector, something similar is actually happening. I think somebody has not muted the microphone. I hear somebody talking in the background. All right. Okay, so then let me maybe continue.
There is one shot as a question from Anna Tokareva.
Oh yeah, sure.
I have a question regarding this FG again. What is the mass dimension of FG?
In this setup here, FG is dimensionless because it depends on the dimensionless versions of the Newton coupling at the cosmological constant, right? So the beta function is always fully autonomous. There is no explicit dependence on the RG scale, and so therefore the versions of the couplings that appear are all of the dimensionless versions.
I'm just confused with this expression because lambda, I thought it's dimensional, or you
yeah, sorry. The G and the lambda that appear here are both the dimensionless counterparts of the couplings. So you take the usual cosmological constant and you divide by RG scale squared, and this is what I mean by the lambda. And similarly, you take the usual dimension full Newton coupling and you multiply with k squared, and this is what gives you this G. So those are both the dimensionless counterparts of the gravitational couplings.
So they contain the momentum explicitly?
Yeah. So those are the usual dimension full couplings rescaled with the RG scale to an appropriate power.
Okay, thank you very much.
All right. So then let me move on to asymptotic safety and the dark sector. And as I said, the main reason to consider asymptotic safety from a sort of phenomenological perspective is that we have this huge parameter space spanning a large number of orders in magnitude in the interaction cross section and in the mass. And we would like to understand whether imposing something like asymptotic safety in the UV, whether that can actually narrow down this parameter space. And I'll give you two examples as a proof of principle. I'll start with a WIMP-like scenario, and I'll then also talk about axion-like particles. So let me start with sort of the vanilla model of dark matter, which is just a single scalar, phi, that is a singlet under the standard model gauge groups, and that is coupled to the standard model through a Higgs-Porter coupling. So H is the Higgs. And through that Higgs-Porter coupling, the singlet scalar is thermally produced in the early universe. And that Higgs-Porter coupling also allows for direct searches, for instance, at the LHC or at dedicated dark matter experiments. Now, if we look at the beta function of that Higgs-Porter coupling, there is the usual matter contribution, and then there's again a contribution from quantum gravity, where F lambda will again be a function of the gravitational couplings. And the key point about this function is it's positive. And that actually means that as we go towards lower energies, quantum gravity fluctuations drive the Higgs-Porter coupling towards 0 at the Planck scale. And that actually means that the single dark scalar actually decouples in asymptotic safety, because if you've set it to 0 at the Planck scale, it will not be regenerated below the Planck scale. So that's actually one example of the predictive power of asymptotic safety. It rules out this vanilla model for dark matter. That is actually also so far compatible with all of the experimental constraints, because experimental searches for this Higgs-Porter coupling have narrowed down the parameter space quite significantly. So there are just sort of small pockets of parameter space that are remaining, but so far no detection has been made. So that's nicely compatible with asymptotic safety. But then, of course, we can ask, well, is there a way to regenerate this portal, this portal to the Higgs sector, and get a dark matter sector that falls into this WIMP paradigm? And there are two ideas how you can regenerate the Higgs portal. One is to add a dark gauge group with kinetic mixing, and the other is to add a dark Yukawa coupling to a dark fermion. So let me briefly talk about both of these ideas. If you want to regenerate the Higgs-Porter coupling below the Planck scale, you can just add a new abelian gauge group, a dark U1, that has kinetic mixing with the U1 hypercharge in the standard model. And the dark scalar, you make it charged under the U1, so it couples to the dark photons. And because of the kinetic mixing, it also has a very small coupling to the abelian hypercharge, which also couples to the Higgs. And in this way, you regenerate, or through diagrams like this, you regenerate the Higgs-Porter coupling. Now, because there is an upper bound on the abelian gauge coupling in asymptotic safety, that translates into an upper bound on the Higgs-Porter coupling in asymptotic safety. So again, here you have predictive power in this extended dark sector. Something similar happens in a different idea. So here, you generate the Higgs-Porter coupling already above the Planck scale, and you do that in a more complicated way by coupling the dark scalar to a dark fermion, psi, through a Yukawa interaction. And then the asymptotically safe fixed point that you get actually lies at a finite value of the Yukawa coupling, and this translates into a finite value of the self-interaction and of the Higgs-Porter. And I don't want to go into too many details. The important thing I want to stress about this model is the following. As an effective field theory, this setting has 6 free parameters, namely the scalar mass, the scalar quartic interaction, the Higgs-Porter coupling, then the mixing angle between the dark and the visible scalar, the Yukawa interaction, and a non-minimal coupling. So it's a 6-dimensional parameter space that you in principle have in this dark matter model. And now, if you want to have asymptotic safety, it turns out that all of those parameters, except for the dark scalar mass, are actually irrelevant couplings at an interacting fixed point, which means that they are predicted. And so, as a function of the dark matter mass, you can calculate the corresponding Higgs-Porter coupling, dark fermion mass, self-interaction, mixing angle, and non-minimal coupling. So in the study here with one of my former PhD students, we did that by coupling this dark sector to a toy model of the standard model, so not the full standard model. So the numbers that we show here, you shouldn't take them too seriously because they will change if you upgrade from a toy model to the full standard model. But our point was more to show that asymptotic safety here is really, really predictive, because it reduces a 6-dimensional parameter space to just a 1-dimensional parameter space. So the upshot so far is thinking about WIMP-like dark matter settings. The vanilla model is ruled out, so lots of predictive power. And then extending the dark sector by extra fields, you also have a lot of predictive power and reduced parameter spaces. However, I would say those models on their own are not so convincing anymore, because you have these extra degrees of freedom that were only introduced in order to regenerate the Higgs portal coupling. So I would say, from the point of view of something like Occam's razor, they are less convincing dark matter models. And so then let me spend sort of 2 minutes or so to talk about axion-like particles. So an axion-like particle is a pseudoscalar which can couple to the field strength, the electromagnetic field strength, and the dual. It's an ultralight dark matter candidate, and this coupling to the field strength times its dual gives rise to photon ALP oscillations, which experimentally you can use to shine light through a wall, and this is the main way through which one can experimentally search for ALPs. Now, within asymptotic safety, then the following happens. If you look at the beta function for that coupling without gravity, there's a leading order term that comes from the canonical mass dimension of that coupling, and then a term from interactions. Both are positive, so you see that without gravity, if you demand a UV completion, there's only the Gaussian fixed point at which the coupling is irrelevant. So if you demand a UV completion, then the consequence is that the coupling vanishes at all scales. Now, with quantum gravity, the situation changes somewhat, because there is a gravitational contribution of the opposite sign. This is something we evaluated together with one of my postdocs, Gustavo de Brito, and also one of my PhD students, Rafael. And what you can see from this beta function here is that you still get just a free fixed point unless this FG is actually larger than 2. And so if the gravitational effect is larger than 2, you already see that this is sort of something like strongly coupled quantum gravity. And so indeed, if you look at the space of the gravitational fixed point values, again, the dimensionless ones, then you would have to go somewhere to quite large values of the dimensionless Newton coupling in order to make FG larger than 2. And then the actual fixed point value lies quite far away from that. And even though it has systematic uncertainties, we don't actually believe that those are large enough to bring the gravitational fixed point value into this strongly coupled regime that you would have to go into in order to get a non-trivial fixed point for the ALP photon coupling. And so this leads us to the conclusion that there are no ALPs in the asymptotically safe landscape. And so I think in view of time, I'll skip the outlook on what could be potentially models of dark matter which are not ruled out in the asymptotic safety paradigm. And I'll just move directly to the summary. So the key message I wanted to convey is that asymptotically safe gravity, if it's coupled to models of visible or dark matter, constrains those models, because quantum scale symmetry is not something that you can achieve at all values of the couplings. And through those constraints, you make quantum gravity testable, because you make specific predictions for values of the couplings, or you actually even rule out certain beyond standard model settings. And on the other hand, you also make dark matter predictive and address one of the key challenges of dark matter, namely the huge parameter spaces that we have. So let me thank you for your attention here, and I'm looking forward to more questions.
Okay, let's thank Astrid for this very interesting talk. And I see immediately the first raised hand by Alberto Salvio. Alberto, please.
Hi, thank you.
Hi.
So I wanted to ask you about these FG times G terms. So are they assumed or are they computed in asymptotically safe gravity?
They are computed.
They are computed.
Yes.
Okay. So it cannot be anything else. It cannot be, for example, F times G to the cube.
No, the leading order term certainly is of that form. What you can also get is gravitational contributions to higher order operators in the meta sector. So those contributions can also be there. But if you look at the beta functions within the standard model, we know that the term has to be of this form linear in the coupling. And I mean, indeed, you can argue structurally why it has to be there, but you can also do the calculations and you get explicitly those terms. So there's a growing body of literature that also makes those calculations by varying different things like gauge parameters, varying regulator functions, and so on, to confirm that it's not a fluke of a particular approximation to get this type of term.
So it holds for any truncation. So it's independent on the truncation.
Yes.
Okay. And another question is, if you have matter fields that are neutral under the gauge group you are studying, then the contribution to the beta function are zero of that gauge coupling. Gravity is neutral. So do you have an understanding of why gravity can contribute to the gauge coupling even though it's neutral? So is there...
Yeah, so I mean, gravity, I mean, photons don't just interact sort of through quantum fluctuations of charged fields, right? But they interact through anything that couples to them, right? I mean, the key point is that gravity couples to any form of energy and momentum, and so gravity couples universally to any matter field, so therefore you generically expect that whenever you have a matter theory, that what you cannot avoid is that quantum gravity contributes to or generates interactions in that matter theory, because there is no way for you to switch off the coupling to gravity. So it's not about the question whether gravity is charged under the gauge group. It's more the point that the gauge theory is charged under the coupling to gravity. This is why you cannot switch it off, right? You can't switch off energy.
Okay, so in principle, if you allow for higher derivative terms, also matter would contribute, neutral matter would contribute to the gauge coupling of beta function, because you can write down terms of the form f mu nu times psi
so
bar,
you can write sort of non-minimal type of interactions, right?
Yeah.
And those, depending on what their form is, they may or may not contribute to the beta function of a gauge coupling at high order. Yeah, but I mean that is of course something that you get even without the coupling to gravity. Right? That's a general statement about quantum field theories and their interaction structure. Yeah.
Okay. Thank you.
Okay, guys, I propose, as we already 4 minutes late, I propose that if there are no really pressing questions, that we postpone questions till discussions. Astrid, are you okay with that?
Yes.
Okay.
I have to drop out, unfortunately, now, but I'll be back for the discussion session.
Perfect, perfect. So thanks a lot, Astrid, for a very interesting talk. And our next speaker is Ilya Shapira. Ilya, are you around? And Ilya is going to tell us about effective quantum gravity, corrections to Newton potential, and the running of fundamental constants in deep IR. Okay, I see Ilya's presentation. I don't see Ilya's face, though. Ilya, and we cannot hear you also.
Unmute. Okay, now you hear me?
Yes, yes, we do.
Good, because for some reason this switched off the Zoom with big Zoom window. Okay, do you see my slide anyway?
Yeah, but it's small. Maybe you can make it whole screen.
Okay.
Yes, perfect. Perfect.
Good. So I changed the title a little bit. So yeah. So I will tell about some recent works with Tiberio De Paulo Neto and Leonardo Modesto on effective quantum gravity. This is a very good studied subject, and I will give some reference. But I think that there are some adjustments which can be made. So I will give some general introduction to the effective approach to quantum field theory. I'm not an expert, so I will tell what I understand, and then go to effective approach. in quantum gravity, and finally we'll concentrate on quantum corrections to Newtonian potential. There are other things which can be done, but this is a kind of a classical subject to explore, and it's very interesting how it can be evaluated. So, so my talk will be based on this paper and on the lectures by Tiberio De Paoloneto, he shared with me. And then last days I had very nice discussions with Roberto Percacci and Josef Frenkel and learned something else and changed it actually transparencies. So let me start by this reference. So this is, we wrote recently with Buchbinder, Professor Buchbinder, the introduction kind of textbook on quantum gravity. Then if somebody wants to read more, you can start with these classical papers by John Donahue of '94. Then there is a review paper by Cliff Burgess. And also we are now close to finish, I guess, the handbook on quantum gravity, edited by Cosimo Bambi, Leonardo Modesta, and me. And there will be a big section about effective quantum gravity, edited by Burgess and Donahue. And I think there will be many interesting papers about this subject, review papers. But I will discuss something very basic. So my approach will be different from the standard one. And this, I will follow basically this paper by Dalvit and Mazzitelli, Argentinians, so who wrote it very early, so in '97. And then I had some ideas about this and wrote some proceedings paper, which is called Polemic Notes. And so finally we did these calculations. Also, it's interesting that we recently finished big calculation about in some model which resembles a lot the higher derivative quantum gravity. And it seems that one of the questions which I posed in this polemic notes is answered positively. It means that it seems that general relativity has a good chances to be universal inference theory of quantum gravity, because the decoupling of massive degrees of freedom in mixed diagrams really goes to this direction, at least in the Antoniadis Motola model. And frankly speaking, I don't see why it should not be different. It should be different in general higher derivative quantum gravity. So what means effective approach? Effective approach means in the wide sense that it's some very important thing, because it explains us why we don't care about fundamental ultraviolet physical theory when we deal with some low energy phenomena. You can meet some traces of effective approach even in classical mechanics, because you can deal with the motion of macroscopic bodies without thinking what that they consist from atoms, molecules, and so on. And if we go deeper into matter, then we can see that when we calculate like atomic spectra, we don't need to think about nuclei, or almost, and absolutely no need to think about gluons and quarks. And the reason is that the two energy scales are very different. And so when you go to a lower energy scale, the high energy phenomena are hidden somehow. So the idea, as far as I understood, the idea was introduced by Steven Weinberg in the 70s, and now it is like generally recognized quantum field theory framework. And so from some point of view, we can try to describe something at each level of physics, energy level, and instead of trying to do everything at the same time. So, and then when we do this, some parts are left behind, so we just ignore them, and it's perfectly acceptable. Classical examples are Fermi theory of weak interactions, Nambu-Lozino model of quarks, and alike. And another example is minimal standard model itself, which is a very successful theory, but we don't know whether it is actually perfect theory to arbitrary energies in ultraviolet, and maybe it doesn't, is not perfect theory, but still we can use it, and it works very well at low energies, let's say conditionally energy. Okay, and it describes everything we see on accelerators. So typically, in the effective approach, we have 2 or more energy scales, and it means that they must be well separated. And in the infrared, we can ignore the effects of massive fields because they are suppressed by large mass parameter. This can be seen as decoupling theorem, and it can be generalized, at least in many cases, to quantum and semi-classical gravity. So another point of view is that in order to separate ultraviolet phenomena from infrared, you need to concentrate on the non-local parts of quantum contributions, because local parts correspond to divergences, and in the infrared, you mainly need non-local parts of effective action. However, there is some special case. It's when you have massless field, then there is a certain duality between ultraviolet and the infrared. And this means you can calculate ultraviolet contributions and automatically get low energy contributions. And in quantum gravity, typically, as John Donahue in some review wrote, it looks like a perfect theory for applying effective approach, because you have basically massless graviton and you have heavy massive degrees of freedom, maybe you have, but they are all of the Planck order of magnitude. So we have in the same theory lowest possible energies and highest possible energies. If we go to numbers, then Planck mass, as we all know, is 1019 GeV, which is a lot of mass, and even if we take into account that the universe is finite, then the energy, the natural infrared cutoff is of the order 10 minus 42 GeV. So the separation of the two scales is at least 60 orders of magnitude. So this means that we have in quantum gravity maximal possible separation between ultraviolet and infrared, and we really can expect that quantum gravity will be a perfect object to apply effective ideas. So we can calculate many things. As I mentioned, there is handbook when you can find many reviews, but the traditional object of our interest is the quantum corrections to Newtonian potential of gravitational attraction between two massive point-like bodies. And this started for my generation by works of Donahue, which I already mentioned. Then there were some small mistakes. It was corrected in this and other papers. And then came David and Mazitelli, which I also mentioned, and paid attention that things must be gauge fixing independent. At the same time, we made some observation with José Lael Neto and André Penafirme that if we don't include all necessary diagrams, then what we have for the contribution to Newtonian potential is not an amplitude, and therefore it depends on the gauge fixing. So after that, now on another side, at some point I was thinking about this, and I got an idea that this all proves that gravity cannot be quantized at all. And then José Lael convinced me to think positively, and I wrote this paper of positive notes on infrared quantum gravity. So finally, there are two results which are considered correct by Birum Bohr, Donahue and Holstein, and Kriplovich and Kirillin. They agree in one part and disagree in another part. Let me note that there was earlier paper with the same basically calculation by Iwasaki in 71, and he found that interaction between two scalar fields, between two fermion fields, and between two vector fields is characterized by different quantum corrections. This is not good because it means that the quantum corrections are not universal. And in some sense, it's natural. Let me explain why.
Ilya, so before you go to the next slide, there is a question by actually John Donahue. John?
Yeah, I just wanted to say that we agree with Kriplovich and Kirillin. There is no disagreement there. The results agree.
Okay, good to know. Thank you. Thank you very much. So how works the standard approach to effective quantum gravity introduced by John? So you just have Einstein gravity, everything perturbative, no need to functionalization group or alike. Then you make a gauge fixing. The gauge fixing can be done in this theory with two parameters, alpha and beta. And then we have ghosts Fadeev-Popov, David Fadeev-Popov was, and matter. And matter is described by minimal scalar field. This is, in my opinion, a doubtful point. So why minimal scalar field? So we can we want to have interaction between two masses. And these two masses typically are two macroscopic bodies of mass M1 and mass M2. Why we use massive scalar field, minimal massive scalar field, to describe these two bodies? But if we make calculations, everything works until some point. So first of all, actually it works until the end. So at the tree level, you have this T function, making Fourier transform, you get Newtonian potential. So it's just perfect. Now, if we go to one loop level, then according to Donohue's terminology, there are two types of null localities. One are so-called p-type terms, which correspond to the polynomial contributions, and they produce 1 over r squared terms. And this apparently is responsible for the first relativistic correction to Newtonian gravity. And second, there are L-type terms, which after Fourier transform produce r cubed. R cubed is something very weak contribution for phenomenology, but still it's very interesting whether we can calculate this in some consistent way. So the massless, the L-type terms, they come only from these diagrams. No, they come from these diagrams, which include loops of gravitons of these three types, plus this diagram is supplemented by the loop of ghosts. So with this diagram, there is no question. Okay, we just say that to calculate these diagrams, we need to consider massive bodies, macroscopic bodies as classical external source, and then quantize only metric. This is absolutely undoubtedly correct. Now there is second set of diagrams which includes internal line of massive scalar field. And internal line of massive scalar field is something non-trivial, because remember that we use scalar field to describe macroscopic bodies like Sun and the Mercury, or Earth and the Moon. So when we put some of these fields into internal lines of the diagrams, it means that this field becomes the argument of the functional integral, for instance, okay? Or in other words, the subject of quantization. So it means that we quantize macroscopic bodies such as Mercury, Moon, and so on. And this is something, for me at least, it's something non-trivial. I don't like it, let's say. So the question is, if how we can think why this is not a good idea? Because by the end of the day, the baryonic matter, macroscopic bodies are made from, not made from scalar fields, they are baryonic matter, and they are made from fermions, and even fermions are not free. We know very well that baryonic matter consists of protons, neutrons, electrons, which are held together by electromagnetic forces. And these particles, except electron, are not elementary. So each of them cannot be described by scalar field. But even more, neutrons and protons are made of quarks and gluons. So you may think to replace scalar field by spinor and vectors and try to repeat the consideration, but it doesn't work because we know very well that these quarks are not free in nucleons. So, for example, one manifestation of this is that the sum of two masses of U quark and one mass of D quark is much smaller than the mass of the proton. So by the end of the day, matter is mostly made from quantum effects, which are already proportional to h bar. So describing all this by elementary field, we probably do something odd. Another argument is that if we think about Casimir effect, we know that when people calculate Casimir effect, they quantize field between, let's say, two parallel plates, conducting plates, and they don't quantize proper plates. So, and this, according to standard point of view, at least, this fits very well experimental data. So it means that the macroscopic bodies probably cannot be object of quantization, which is in general a strange idea. So the question is, if we restrict our attention only by L-type diagrams, is it possible to obtain well-defined quantum corrections? And here we come to...
There is another question again by John Donahue.
Please.
John?
Yes, sorry, I forgot to unmute. Ilya, there's an answer to that question, and there's even an experimental answer, because if you don't include those diagrams, you don't get the classical behavior of massive bodies like planets, because the same diagrams that are included that you're describing there are required in order to get the post-Newtonian expansion. There's by now a large subfield of work of getting the post-Newtonian expansion out of Feynman diagrams. It requires those diagrams and even higher order diagrams. To exclude them is experimentally incorrect. It's also theoretically incorrect because we have theorems about the low energy coupling of gravitons to any object. This is in E&M, it's done by Weinberg. In gravity, it's done by Gross and Jakiv. We know that the two graviton coupling to objects independent of size is given by a particular form, and it's a low energy theorem. And those are sufficient to derive these quantum corrections. So I think excluding them is in fact experimentally and theoretically incorrect.
Well, I have different opinion. I think first, non-relativistic approximation can be perfectly well obtained from relativity, because these quantum calculations are done using general relativity, not Newtonian theory. So maybe this taking into account p-type diagrams is another form of calculating on first relativistic correction. This I can agree, but for me it is a strange idea anyway to quantize macroscopic bodies.
You don't even have to quantize the macroscopic bodies. There are ways of getting the exact same result using just these low energy theorems, where all you do is you assume the form of the Compton amplitudes and use unitarity. This isn't a matter of opinion, this is a calculation.
Okay, maybe we can discuss after if you want.
Yeah, I think there is a good time for discussions there.
Okay.
This seems to be an important question. Okay.
Certainly, yes.
Yeah.
So, yeah, so we can ask the following question. Can we, taking only L-type diagrams, quantizing only gravitational field, we meet another problem because our calculations don't give automatically the amplitude. So it can be dependent on the gauge fixing parameters, in our case, alpha and beta, and on the parameterization of quantum fields, because you can parameterize quantum field at one loop, at least in this way, with 6 arbitrary parameters, gamma 1, gamma 2, etc., gamma 6. So everything may depend on these parameters. And the calculation was done, and the scheme was found how to provide this independence by Dalvit and Mazzitelli, and we recently, they checked actually the independence on one of these gauge parameters, and we recently checked the independence on parameterization. So, yeah. So how works the scheme of Dalvit and Mazzitelli? Then instead of scalar field, you take as a source massive particle. The action of massive particle with a mass m has this form. And then we can calculate first variational derivative in this form. It's energy momentum tensor. And this matrix is the second variational derivative. Then we can say that we only need to quantize gravity and do not quantize matter field. And this gives you this expression. And then gauge fixing plus S second order expression is this. We don't need even to take diagrams because we can do it in functional form. And then we have to calculate trace log of this operator plus contribution of Gauss, which does not depend on the matter source. Then these two matrices T and M satisfy these very useful identities. And so things get relatively simple at this level. So after some calculations, we arrive at this expression. This expression is nice, so it has square of the wild tensor R square, this mixing with T mu and so on, but these coefficients depend on the gauge fixing. I did not even give full form of this dependence in parameterization because they're too bulky. So these coefficients which we have here, psi1, psi2. Sorry, what's it? Apparently there is some music. What's it?
I just muted. There was some noise, and
it was some random sound.
Yes.
Okay. So
I had to mute a person.
Yeah. So this is the divergences, and here, since we quantize only massless fields, we have this duality between ultraviolet and infrared, and in principle, we can easily restore infrared behavior from these formulas. However, this infrared behavior will depend a lot on the parameterization and gauge fixing. So what we can do is to go on shell. If we go on shell, then we can check easily that everything which depends on the gauge fixing and parameterization disappears, and we have this expression, which is well defined. However, it's useless for us because it is not sufficient to calculate corrections to Newton potential and whatever else. This square of the Riemann tensor is actually Gauss-Bonnet invariant. It's not just square of the Riemann tensor. It's very important observation. So if we go to the procedure to take the non-local, extract the non-local contributions, leading logarithmic contributions from dimensional regularization is like that. And so we arrive to this expression. However, let me remember that these beta functions, beta 2, beta 0, beta RT1, 2, and beta TT depends, all of them depend on the gauge fixing. So now let me show you how we work with these expressions without effective approach, just to compare. Actually, Breno Guccini yesterday gave some review of this. So I will be very brief. So let us consider this expression. It's very general because if we want just a propagation of gravity on a flat background, then this is the most general expression you can have, except cosmological constant. So there are three non-local form factors, F1, F2, and F3 with tilde. They may be even be local, no problem at all. One can prove that this combination is proportional to the cube of curvatures. And then we get this most general expression, relevant expression for us with two form factors, F1 and F2. And now, if we have these two form factors, we just make it linearized, and we arrive to this expression when A1 and A2 are written in terms of these original form factors, F1, F2. The misprint should be F2. So now we take the spherically symmetric static metric with two functions, phi and psi. We need it static, so we spherically symmetric, so we can say that they depend only on R, and trade the Lambertian operator for Laplacian. After that, we arrive to these two equations for phi and psi. Interesting that if we take generativity, then these functions A1, A2 are very special because these F1, F2 are 0. So these two functions are just boiled down to 1. And then we can see that phi equal to psi, as we all know from generativity. You can provide the same with form factors, but have to require this condition for these form factors. And then we have this expression, which means we have R term plus Einstein tensor contracted with a Ricci tensor. This is simplest choice, and calculations become simple, results become simple, but conceptually it's not very special. So if we make Fourier analysis and use these equations, we arrive to this representation. And after introducing these interesting two functions, F1, F2, we get this phi and psi in this form after some calculations. So when we have these two forms, we can actually put here any form factors and get the result. And the first point is that if I have four derivative of gravity, if for Einstein gravity, you can easily get from here that phi and psi are equal to minus Newtonian potential. For 4-derivative gravity, we have these two expressions obtained originally by Stella in 78. And we can see that there is no singularity, as Brennan discussed yesterday. There is no singularity in this case when R goes to 0. Actually, Alberto Salvi was completely correct yesterday because he said that by itself, Newtonian singularity has no importance. This is true, but historically, this question was raised first by Arkady Tsetlin in 95 when he attributed this singularity to black holes. Actually, this is a very interesting question because apparently these are similar, the two singularities. They both are like 1 over R, but I cannot find any connection between the two. Anyway, in the theory with 6 or more derivatives, including infinite derivatives, typically there is no singularity, Newtonian singularity. Of course, once again, this is not obvious. The sense of this is not obvious because Newtonian limit is not obvious for these theories and so on. So now this was not an effective approach. Why? Because here we have this denominator F2 and F0, which means propagators with non-trivial poles for spin 2 and spin 0 parts. And in the effective approach, things are completely different. Why? Because in the effective approach by law, you have to treat all these 4 derivatives and non-local and so on corrections as small perturbations. This approach was introduced by Simon and then discussed by Parker and Simon in 90s. So if we make this in our theory, we actually come to these expressions. And here in our case, F1 and F2 are these two formulas when beta, kappa square beta is by definition a small perturbation. So we cannot use these formulas like this one, and we have to solve it perturbatively in kappa, let's say. This changed completely the result. And if we do this, the equations are different. Equations are like that. And this is the example of perturbative solution. In our case, with logarithmic form factors, which come from integrating over gravitons. And then when we do this, we come to these solutions. This is a 0 order solution, which is just Newtonian. And this is quantum corrections. Those two are quantum corrections, delta phi 1 and delta psi 1. They're linear and can be solved in a standard way by Fourier transformation, which is not difficult. And so by the end of the day, we arrive to this at these two expressions, phi 1 and psi 1. So replacing them into our making the Fourier transform, we have these two solutions. Everything looks fine, but these combinations, these two parentheses in these two lines, are completely dependent on the gauge fixing. So it cannot be regarded as final product of any reasonable physical consideration. For example, if I take minimal parameterization and minimal gauge fixing, then we have these two formulas. It looks nice, but this has nothing to do with reality because the coefficients depend on the gauge fixing, depend on parameterization. So it's not the full story. So Dalvik and Mazzitelli introduced the following trick. Let us now consider that one of the two bodies is heavy and represents a source, and another body is very slowly moving test particle with a mass m. So we get second source, which is a test particle. And now let us consider the motion of this test particle. We shall see that using this test particle, we actually go on shell. And by the end of the day, we arrive at the on-shell well-defined expression. So this is the effective action, which this is quantum correction to the effective action. It's logarithmic. Coefficients depend on the gauge fixing and parameterization. But then we take variational derivative, and we have this equation 4, which is the geodesic equation for the test particle. And now, if we calculate it, make once again Fourier transform, we arrive at the acceleration of gravity in this case. And acceleration of gravity has this part, which is Newtonian and correction. And so finally, we come to this correction to the Newtonian potential, which has original Newton part plus correction. It's amazing that this correction does not depend on the gauge fixing and does not depend on the parameterization. It's completely universal. So let me explain why this correction is universal. The reason is the following. What we are doing is quantizing Einstein gravity with additional matter source, classical matter source. When we do this, we actually can use the following general quantum field theory theorem, saying that the difference between the two effective factions in different parameterizations and different gauge fixings, which are here alpha 0 and alpha I, is always proportional to the classical equation of motion if we deal with the one-loop divergences. At higher loops, things become more complicated, but now we need only one loop. So it means that this is for our case, this is the one-loop effect, classical, three-level equations of motion, and we have some f mu, which is arbitrary function. However, we know by power counting and locality arguments that these two guys are at most 4 derivatives. So the integrand have mass 4 dimension, and they're local. What it means? It means that this expression for f mu can be only of this form. If we replace it back to our formula, then we see that the variation of parameterization and gauge fixing gives you this general expression. And now we can note that changing these parameters b, because these parameters b are not under our control, they are completely arbitrary. If we start to modify them in an arbitrary way, it means that we can modify the coefficient c in the original divergences in this way. And out of this 6 coefficients c, we can construct one is invariant C1, it is Gauss-Bonnet, and second is this combination. This combination is invariant. And it turns out that this combination is exactly this beta invariant, which appears here in this formula. Okay, so it's not by chance that the motion of test particle is invariant. It is invariant because of this general theorem about gauge fixing and parameterization independence on shell for the effective action. So we can conclude that if we don't like, of course, there are people who like to quantize scalar field and think that scalar field describe very well massive bodies, macroscopic bodies, no problem. But if you don't like this, then the method of Dalvit and Mazzitelli provides a consistent scheme of calculating quantum gravity corrections to Newtonian potential in the effective framework. And of course, it looks more complicated than the derivation of diagrams because it requires this extra piece with test particle, with the motion of test particle. But by the end of the day, it gives you consistent result in the sense it is does not depend on gauge fixing and parameterization. So, yeah, so let me go to conclusions. So effective quantum gravity is certainly simplest option for quantum gravity in general. And it's not, from the general perspective, it's not satisfactory option. Why? Because one of the motivations for quantum gravity is for example, to deal with singularities. And this effective approach by definition cannot deal with singularities because it ignores extra degrees of freedom, which may wash out the singularities. However, if we agree that we restrict our interest only to low energy physics, then we see that we can actually describe quantum gravity in the deep infrared, separate it from singularities, from ultraviolet divergences. And if we think about Newtonian corrections to Newtonian potential between two macroscopic bodies, this can be done even without quantizing scalar field, which using it as a model for macroscopic objects. So unfortunately, the numerical effect is negligible, but still, I would say it's very nice that we can calculate something in an absolutely consistent way. Thank you very much.
Thanks a lot, Ilya. And are there further questions? I think we still have like 5 minutes time. So Ilya is ahead of time in a sense. So do we have more questions?
By the way, do you see me?
No, actually not.
For some reason, I cannot go back to this. I will try. Go back to this main area. No, I don't know how to do it.
So you see, I can see Philip Monheim. Hey, Philip, but I cannot see you, Ilya. It's some you know, conspiracy plot. They don't let us.
No, I found myself, but I don't see how to come back to this main main window.
Ilya, what happens if you stop share screen?
Stop share screen. I can just close it. Oh, good.
Oh,
here
now we can see
everybody.
Hey.
Good idea.
Yes.
So now I can try to share screen again. Why not? So if somebody wants to ask questions, John, please, or we can postpone to the discussion sections, maybe.
Yeah, up to you. We still have 3 minutes time, that's for sure.
Yeah.
I wanted to ask you something, okay, in general to experts on this effective field theory approach to quantum gravity, since nobody's asking anything. It seems that maybe inflation is the best physical situation where one can use this machinery. In constructing the observables, we already quantized the metric there. Maybe one can include the contribution of high order terms in the effective field theory approach, like R square, R cube, etc. So I was wondering if somebody is doing this, maybe most probably for the models, for most of the models, this is going to give negligible contributions, because in the model of inflation, typically the energy densities are much smaller than the Planck mass. So probably this is going to give very small contribution, but probably more sizable than the one that corrects the Newtonian potential, I guess, because the scales are less separated. Do you know anything about this?
I guess John knows much more than me, because he is the head of this big section for handbook on quantum gravity with effective field theory.
So in that case, you don't have an expansion around the flat space, but rather on an FRW metric. So maybe you cannot use most of the usual formulas we use.
Of course, you know that Starobinsky inflation uses the R squared term.
Right.
Yeah,
sure.
There actually, I mean, the answer is there is a series of works that have done it. They are reviewed in this famous handbook by Dan Green. So there's a recent paper by Dan Green reviewing the applications of effective field theory to inflationary theories.
Who did this? Sorry, say it again.
Daniel Green.
Daniel Green. Okay.
Right. So it will be in this handbook. But the paper's out there already on the archive. I can send it to you if you want, Alberto.
So in the case of Starobinsky inflation, we have a very large coupling in front of the R squared term. So and in that case, we do include the extra degree of freedom. So this is not along the lines of effective field theory, in which we don't include the extra degrees of freedom due to the high order terms, but rather treat them as perturbations, as far as I understand.
That's correct. Well, I would say that a lot of the work that I do with various collaborators is looking at quantum gravitational corrections in the de Sitter phase of inflation. And you do find interesting things. You find secular growth corrections. One thing that you're fighting against is that the loop counting parameter, GH squared, according to the tensor to scalar ratio bounds, has to be a very small number. It has to be less than about 10 to the minus 10. But you do find secular enhancements of the thing that grow like the number of e-foldings and could get arbitrarily big if you considered a very long phase of inflation.
So you're talking about corrections of these higher order terms to the inflationary observables like R, NS,
no,
etc.,
corrections of the Einstein term that are in the context of effective field theory. So they're not corrections of higher order terms. They're corrections due to the Einstein term that give rise to, that need to be canceled by BPHC counter terms and that are effective field theory, are treating Einstein quantum gravity as a low energy effective field theory in exactly the sense that John is talking about.
Like including higher loop corrections to these observables. Is it something
That's
like
right.
this?
Looking at one loop corrections.
One loop corrections.
One loop is the only chance that there is to be observable. So if it gets
I mean
enough,
the first loop corrections I meant. Yeah.
that's right. If it gets enough log A's, then in principle, with 21 centimeter cosmology, if things shake out right, the one loop correction might possibly be observable.
But so when you include the one loop correction, you don't need to include some higher order terms to cancel divergences?
You do. You need to
Okay,
treat it as a low energy effective field theory, adding the BPHC counter terms to cancel the divergences. And then you're left over with a finite contribution, which is a non-local finite contribution, exactly the same way as in standard effective field theory, exactly in the same way as in the corrections to the Newtonian potential. And you do get interesting corrections that grow secularly. You also, if you look at corrections to the Newtonian potential again, you get corrections that grow like the co-moving distance as well. So you can see that because you've got another dimensional parameter. You've got in flat space, the only thing you can get is G is a correction that looks like G over R squared. That's the only thing that's dimensionally allowed. But in a cosmological setting, you have another dimensional parameter, namely H. So you can get terms that go like GH squared. And then you can get logarithms of things like the logarithm of the scale factor or the logarithm of H times R.
And then you neglect the finite parts due to these higher order terms. So the higher order terms you use just to cancel the divergences of the
right. Well, they're of order 1. So what you would get is something of order 1. And then compared with something that grows like logarithm of A, you wait long enough, logarithm of A is bigger than order 1. Or you can put them into the renormalization scale. So you would get terms that go like logarithm of A over logarithm of HA over mu, or excuse me, it's typically logarithm of mu, the renormalization scale, times A over H is typically what you get.
Guys, what I would suggest that we move forward and keep it for discussion, especially if I'm right, Richard, you are in US now, so because it's you have a daylight in your window, right?
That's right. It's 8:50 about.
Then it's okay if we postpone it to discussion, and let's move to the next talk. But first, thank Ilya for the interesting talk. Ilya, thanks a lot. And now we have another speaker, namely Philip Mannheim, who is going to tell us about normalization of the vacuum and the ultraviolet completion of Einstein gravity. Philip, welcome.
Yes. First of all, everyone, good morning. Thank you for the kind invitation. And is everything clear on the screen? Alex?
Yeah, it's all clear.
Yeah.
Oh, okay.
Yeah, I can see it.
Thank you, Richard. Okay, so let me give an outline of what I'm going to discuss. I'm going to raise what sounds like a primitive question. Is the vacuum normalization finite? Now, how could it not be? Now, the answer is, if you specify an action and canonical commutators, that does not fix the Hilbert space. You need to find a Hilbert space in which the Hamiltonian is self-adjoint. Now, if you said Hji star equals Hij, that only makes sense if H is self-adjoint when it acts on the states in the Ij basis, and that depends on boundary conditions. So in order to analyze this question, you have to know about the boundary conditions of the field theory. Now, I'm going to present a procedure to determine whether or not it is finite. And then I'll show you that it is finite for the second order derivative bosonic field theory. And the procedure itself allows us to write quantum field theory Hamiltonian as a first quantized derivative operator. In other words, set up the quantum field theory eigenvalue problem as a derivative problem. I mean, if you have derivatives, then you can check on boundary conditions. I'm also going to show you that when you do exactly the same thing for fourth order theories, this quantity is not finite. And in the Hilbert space in which you use this Dirac norm as the inner product, the Hamiltonian is not self-adjoint. Now, that means that all the discussion that we've had from Astrid, from Ilya, and people who talked yesterday, it means that what they've done is not correct because they're working in a Hilbert space where the Green's functions are not finite. Now, that turns out to not be the end of the world because I'm going to show you that there's a different Hilbert space in which everything is finite and all of their results are going to hold, except the derivation, the reasoning has to be modified somewhat. Now, in general, if you wanted to construct a norm, the best norm you can use is the overlap of the left eigenstate of a Hamiltonian with the right eigenstate of a Hamiltonian. That's the most general quantity that you can use. This is also the same as the overlap of a vacuum with its CPT conjugate. The Dirac norm is the overlap of a vacuum with its Hermitian conjugate. This is actually the most general possibility. That's something I showed. And when you have this one and the Hamiltonian is self-adjoint, then the vacuum norm is finite. There are no states of negative energy and, of course, no states of negative norm. For a fermion theory, this vacuum expectation value is automatically finite. I'm going to show you that if you take these fourth order theories and you Wick rotate to the Euclidean, you'll find that the contour circle at infinity contribution in the rotation is not only not zero, it's even infinite. I'll discuss results from the perspective of the Dyson-Wick expansion, which is what everybody's been using when they've been doing perturbative gravity. And finally, I'll discuss what all this has to do with constructing a quantum gravity theory. Now, let's just see what the problem is. Take very simple scalar field, write down the equation of motion, Hamiltonian, canonical commutators, expand the field out in terms of creation annihilation operators, calculate the Hamiltonian, and you can show that there's a state omega that A annihilates, and it's the ground state of H. What that does not tell you is what its norm is. It only tells you that there exists such a state. It doesn't tell you what the norm is. Now, why would you need to know the norm? You look at the propagator for the same theory. It obeys a differential equation. You can solve it in terms of the Feynman propagator. You would like to associate this quantity with the T product, but when you stick the T product back into this differential equation, you generate the delta function, but you also get the overlap of omega with omega. So this quantity only satisfies the differential equation if the vacuum normalization is finite. If it's not finite, then you can't represent this propagator as this particular Green's function. Now, if it's finite, we can always rescale it to 1. So either it's 1 or it's infinite, and we'll have to see how that works. Now, I don't know of any proof in the literature that the normal of the vacuum is not infinite. And I think taking it to be finite is a hidden assumption which appears on the first page of every quantum field theory book. And I'll show you how we can check. I'm going to give you a procedure for checking, and I'm going to generalize to quantum field theory what we know from quantum mechanics. So quantum mechanics is very beautiful because it has one special feature. We can write down the Hamiltonian as p squared plus q squared and commutate a q plus p, q with p as I, and we can solve the p as I d by dq in a differential basis. We find that the ground state is E0 is a half, and the wave function is e to the minus q squared over 2. That's straightforward. We can also do occupation number space. We can write q as a plus a dagger, p is a dagger minus a. Then we can find a state that A annihilates, and that's the ground state, and it has, of course, the same energy. That does not fix the norm of omega. However, to fix the norm, we have to relate the two bases, the differential basis and the occupation number space basis. So we write A is q plus ip, A annihilates the vacuum, project it onto q, and you get a differential equation. The solution is q with omega is e to the minus q squared over 2, and therefore the ground state wave function that we got over here is also the overlap of omega with q, namely the probability of finding an eigenstate of the Hamiltonian in an eigenstate of the position operator. Now we calculate the norm of the vacuum, put in a complete set of position operator eigenstates, integral psi star psi, psi 0 star psi 0, integral e to the minus q squared is root pi. We've established that the Dirac norm of the no particle state is finite. And then on setting psi 0 q is divided by pi to the quarter, we've normalized it to 1. We're able to do this because we know the form of the wave function. So the procedure is straightforward and familiar. It works because the wave function basis approach and the occupation number approach have something in common. They're both based on an infinite number of degrees of freedom. In the occupation number space, we represent them as an infinite dimensional matrix labeled by omega, a dagger squared omega. And the wave function basis, the coordinate q, is a continuous variable that goes between minus infinity and infinity. One basis is discrete, the occupation number space. The other basis is continuous. Both of them are infinite dimensional. The advantage of the continuous basis is that it allows us to express the normalization of the vacuum as an integral with an infinite range, an integral that is then either finite or infinite. Now, for field theory, we certainly have an occupation number space basis, but can we write it as a wave operator? If we can, then we can check on the normalization.
By the way, Philip, sorry for the interruption. I think it's a bit confusing. I think I know what you meant, but I think it's a bit confusing to say that there is an infinite number of degrees of freedom. And then quantum oscillator has just 1 degree of freedom, right?
Oh, I'm sorry. The basis of the A and the A dagger is infinite dimensional.
Yes, yes.
And
it's an infinite dimensional Hilbert space.
It's an infinite dimensional Hilbert space. It's not an infinite number of field degrees of freedom. We'll get to that in a moment.
Okay.
All I meant here was that the representation of the modes was infinite dimensional.
Sure, sure.
But we're going to use that fact almost immediately. Thank you. Now, let's go to the quantum field theory case. We have phi with phi dot is a delta function. Now, can we realize this as a differential operator? No, we cannot. We can't replace phi dot by minus I d by d phi. That's completely meaningless. The only thing we could do with this expression is to write phi dot as a functional derivative. But we can do something else. We know we have creation and annihilation operators. So what I'm going to do is reverse engineer and convert it back into what we did in the quantum mechanical case. Namely, for each A of k, I'll write them as q plus ip. A dagger is q minus ip. Q with P still has a delta function normalization, and H just becomes P squared plus Q squared, and phi is Q plus IP times the positive frequency plus Q minus IP times the negative frequency. Now, these Q and P don't have to have anything to do with physical position or momentum operators. Their only role is to convert for every given K an infinite dimensional representation of the A's by a differential representation of the A's. That's all I want to do. And so I can look at these commutators, the Q with P, I can write P as a derivative operator, and then the Hamiltonian becomes itself a derivative operator. I introduce a vacuum that A annihilates for each K, project onto Q of that K, I get a differential equation. I get that Q of K is e to the minus Q squared of this K over pi to the quarter, and then the vacuum normalization is beautifully 1. So what I've been able to do is to show that the normalization of the vacuum of the free second order field theory is indeed finite. Was there a question?
Yeah, Philip, sorry, I'm again confused. I think if you use Fourier transform and not Fourier expansion, but
Yes.
Fourier transform, then you are still dealing with continuum, as one can see by this QP relation on delta function.
Yes, the K is continuous.
Right.
In other words, what I'm saying is for every mode in the expansion of phi, I'm going to write a differential representation, but then I have to take the product over all of the Ks.
Sure.
But that's the infinite number of degrees of freedom of the field.
Yes,
So
yes, absolutely.
Yes.
But you still cannot write a derivative operator for P of K. It will be also a variational derivative.
No, I freeze K, and I just write it as d by dk.
But you have an integral and you have delta function.
I'm going to do that integral in a moment. Yes.
But just
no. I have this relation. This is the relation that was gone.
No. I mean, if you have delta function commutator, you cannot write derivative because it's delta function.
Well, okay. All right. I'll have to.
Maybe we should discuss it a bit later. And
if you like, I'll make this a discrete basis.
Yeah, discrete basis that could work. Yes.
Okay, that's implicit. Okay.
Okay.
Yes. Now, so anyway, this is the procedure to check if the vacuum normalization is finite. Okay. Now, I've only done the free theory. Now, what about the interacting theory? So to do the interacting theory and to do the Wick expansion, which is what we use for perturbation theory, we have to express this quantity, this T product, and we express it in terms of the infields, which are free field equations, and the interaction picture Hamiltonian, and the relation between the true field and the infield, and you come up in the standard textbooks with this relationship. It's a product of the term we like and a vacuum piece. You divide out by the vacuum piece, and that's the standard expression that is used in developing the Wick contraction expansion. Now, to do this, we had to make that division. Now, at first, you will say, well, now it doesn't matter if the vacuum's not finite, the normalization, because it drops out of the ratio. But that's not true. You can only divide by this quantity if it's finite. And now let's look at this quantity. If we expand it out to lowest order in HI, the first term is the overlap of the vacuum with the vacuum, the free theory. That's the free term. Now we've got the interacting terms. If the theory is renormalizable, then this quantity can be renormalized, and then the vacuum remains finite in perturbation theory. So whether or not we can even begin the Wick expansion depends on the finiteness of this quantity, which in turn depends on the finiteness of the normalization of the vacuum. Since if in a theory in which that's not the case, in which the normalization of the vacuum is not zero, is not finite, then you can't use this expression and you can't do the Wick expansion. Now, why would I be doing all of this? Oh, let me just make one more comment. Sorry. what I've shown is how to write the Hamiltonian as a differential operator in this particular way. Now, what about interactions? In principle, I can write the phi as this differential operator, feed it back into lambda phi to the 4, and I can set up the entire problem as a differential equation. And in principle, I can therefore do quantum field theory entirely in terms of ordinary derivatives. Okay, now, except this is not, for this particular case, it's not exactly easy, and we don't know how to do it exactly. And this does not enable you suddenly to be able to do it exactly. For fermions, they are big anti-commutators. Because of the Pauli principle, B squared is 0, B dagger squared is 0, you can represent them by finite dimensional matrices. So because of the Pauli principle, the issue of normalization of the fermion vacuum is straightforward, and the norm is automatically finite because there's nothing infinite dimensional. So fermions turn out to be simpler. Higher derivative theory is the one that has a lot of interest in this conference. Just take a high derivative theory. It has a differential equation. We want a propagator to obey this equation, and we can write it in the form of a differential 1 over k squared minus m1 squared minus 1 over k squared minus m2 squared. You all know the benefits of this. It falls off as 1 over k to the 4, which is good for renormalization. And the issue is, what do you do with the negative residue, which is the ghost problem? So we'll see how to deal with those. But we're also going to have to deal with something else, and that is the vacuum normalizable? So to do that, we introduce the Lagrangian. We've got the energy momentum tensor, the canonical conjugates. We can write down the canonical commutators. The only one that's interesting is it's not phi with phi dot, which is 0, or even phi with phi double dot, which is 0, but it's it's non-zero. It's phi with phi triple dot, which is non-zero. You take these commutation relations, you assume that d of x over here is going to be the ordinary t product, feed it into this differential equation, and you find that you get minus vacuum times the delta function. And therefore, this is only a solution to this differential equation if the vacuum normalization is 1. If it's infinite, then Wick's theorem and the associated Feynman rules are not valid. And the hope that way below M2 energies of M2 squared, that you could be in an effective theory, even in the effective theory, omega is still 1. In fact, if you think of this as a set of positive norm states and a set of negative norm states, and the negative norm states have a much higher mass, the problem is the negative norm states have an infinite negative norm, and the positive norm states have a infinite positive norm. So you don't, when you get rid of this term, you don't make this term suddenly have a finite norm. It only will have one if we can show that the vacuum is normalizable. Otherwise, splitting up the Hilbert space in that way will not give you an effective theory for which you can do the Wick theorem, because you can't identify the propagator as this particular quantity. However, I'll show you in a few moments that, in fact, for the fourth order theory, this quantity is infinite. I've described before how Carl Bender and I have solved the negative norm problem by going to a different Hilbert space, by finding that the Hamiltonian is not self-adjoint, and we'll find exactly the same thing is going to happen here. So the solution to the negative norm problem is also going to be the solution to the vacuum normalization problem. And once we've done that, then everything that people have been describing in this conference and in studies of higher derivative theories, everything goes through, everything's correct. You got the right Feynman rules, you just didn't get the right reasoning. Okay, now, so how do I do this? First of all, I have to introduce creation and annihilation operators, and then I'm going to have to convert them into a differential form. So I just do it as I said, and I find when I calculate out all the commutators, lo and behold, there's this famous minus sign, which we think means a negative norm, and there's another minus sign, which might mean that there are states of negative energy. So these are the challenges of the theorem. So now I've got to turn it into a wave mechanics, and then I can come back and check for the normalization. The wave mechanics of the full theory, the full quantum theory, is you freeze out the space and you just keep the time derivatives, and that's this equation, and there's the fourth order equation of motion. Now, for this theory, you have z, z dot, and z double dot. That's 3 variables. That's too many for one oscillator, but not enough for 2. So this is a constrained system. So to undo the constraint, you introduce a new variable x is z dot and a new conjugate. You use the method of Dirac constraints, and Aaron Davidson and I discovered that the Hamiltonian for this theory is the following function, where there is this p squared, px squared, and x squared. That's one oscillator. The z squared and the pz, that's the second oscillator. There's this cross term, which drives the theory, which this is the important one. And you'll notice that there's a minus sign here, which would mean the Hamiltonian becomes unbounded from below. That's the famous Ostrogrodsky problem. 2 sets of canonical commutators, z with pz and x with px. Try and set pz as minus id by dz and solve this as a Schrödinger problem. You find that the wave function, when you solve that, turns out to be minus in the x squared and plus in the z squared, and that wave function is not normalizable. So the state with energy omega 1 plus omega 2 over 2 is the lowest energy state of an infinite tower of positive energy modes, and acting on those states, the Hamiltonian is not self-adjoint. Therefore, all of the previous discussion, if this carries over to the field theory, which of course it will, if all of the previous discussion is not valid, because implicit in the analysis with the assumption that the Hamiltonian was self-adjoint, namely that the wave functions converge, and then you can integrate by parts and throw away surface terms, and you cannot do so. However, if you look at the alternate solutions, where omega 1 minus omega 2, this is an infinite tower of modes which increasingly go down, that's the Ostrogrodsky instability, then you'll find that the wave function, omega 2 goes to minus omega 2, is nice and normalizable. That's a point, something that Bender and I noticed in 2008, and Richard Woodard had discussed this a few years ago. Okay, now we've got the theory, we introduce the Hamilton's equations of motions, we get 4 z's in terms of the a's and a daggers, we convert them back, we write the Hamiltonian in terms of the a's and the a daggers. We're in deep trouble because there's one minus sign and there's another minus sign. We know the wave function of the ground state, we calculate the norm, and the norm of the ground state is infinite. So what we discover is that this fourth order theory has the following disturbing features. Either we work in a Hilbert space with a state of lowest energy, in which case the Hamiltonian is not self-adjoint, or we work in a Hilbert space where there is no state of lowest energy, in which case the Hamiltonian is self-adjoint. So both of those options are rather disturbing. I don't know how to deal with a theory which has no ground state, so I'll only discuss the theory where I have a state of lowest energy, but I have the problem of wave functions and vacuum that is not normalizable. So I've done all this algebra, and now what I want to do is go back to the field theory and just do the same thing at every k, exactly as we did for the second order theory. I just generalize, you don't need to follow all the algebra, but obviously if I know how to do the a's in terms of the z's for the quantum theory, for the quantum mechanics, I can do it for the field theory. I can get the z's and the pz's, x and px's at each k, the way I described for the second order theory. I find that I get a canonical commutation algebra, just as I would want, and the Hamiltonian is px squared plus pzx plus x squared minus z squared, which is exactly the Hamiltonian of the quantum mechanics at every k. Remember, I went from the field theory to the quantum mechanics by freezing out the x dependence. I can now restore it as a K dependence. But once I've got this Hamiltonian, then I can construct the wave function, do exactly what I did in the previous case, and it won't surprise you that when I'm through, I get something which diverges when z squared goes to infinity, and I thus establish that the Dirac norm of the field theory vacuum is infinite. And so what we see is you freeze out the X dependence, you look at the associated wave mechanics, and if you got that wave mechanics, then you get whatever you get for the wave mechanics, if you get a finite or an infinite one, you will get the same one in the associated quantum field theory. And that is exactly what we've established. So the result is that we have finished up with a theory which now has an infinite vacuum. So what have we got? We've got a field theory. Take A2, the usual A2 that goes with the negative frequency, and annihilates the vacuum. Energy is bounded from below. This quantity is both infinite and negative. A2 dagger annihilates the vacuum. That's unbounded from below. This becomes an annihilator instead of a creator, which means positive, negative frequencies propagate forward in time. Energy is unbounded, but nonetheless, that quantity is finite and even positive. Now, those are two different Hilbert space. One, A2 annihilates the vacuum, A2 dagger annihilates a different vacuum. Therefore, we don't have two problems, the negative energy and the negative norm. We have one problem in one Hilbert space, and we have a different problem in a different place, and in a different space. However, we have a new problem, which is that even if we went into the bounded case, not only are the norms negative, some of them are even infinite. Let's look at it from the perspective of the Feynman propagator. Put in the normal I epsilon here and the I epsilon there. Positive frequencies propagate forward, negative residue. Do the alternate, take A2 dagger as the annihilator, put here a minus I epsilon. You still have negative frequency poles propagating forward in time, but because of that minus sign and that minus sign, when you go round the contour, you get a positive residue. So those are the two options. Now, there's a clue here, and the clue is we've seen that A2 dagger comes out to be negative. But it can't be if A2 dagger is the Hermitian conjugate of A2. That would be positive definite. Therefore, A2 dagger cannot be the Hermitian conjugate of A2, and therefore phi cannot be Hermitian, and therefore the Hamiltonian cannot be Hermitian. But of course it's not Hermitian because it wasn't self-adjoint, because the wave functions were not normalizable. So we have to deal with a non-Hermitian Hamiltonian and not with a Hermitian Hamiltonian. Now, the Hamiltonian is not Hermitian or self-adjoint. Now, the Dirac inner product, you just calculate omega omega. If the Hamiltonian is not Hermitian, this quantity is not time independent. Therefore, it could never be the correct inner product if the Hamiltonian is not Hermitian, because H is not equal to H dagger. The most general thing you can do is look at the left and right eigenstates of the Hamiltonian, and then you find e to the minus IH, e to the IH, and that one is time independent. So the general one you need is find the left eigenstate and the right eigenstate of the Hamiltonian. Now, when you do that, you're guaranteed that this is going to be time independent. So it's the only possible inner product. Now, of course, if the Hamiltonian's Hermitian, the left eigenstate is just the Hermitian conjugate of the right eigenstate. So that's the special case. But this is the more general case, and that one, which is also the same as the CPT conjugate of the right eigenstate, that's the correct one to use in terms of being time independent, but is it finite and is it positive? So that's the question that we have to use, we have to study. Now, let me just tell you how we do this. We saw a moment ago that we had a minus z squared term, which gave you an unbounded energy. So I'm going to get rid of it by making a similarity transformation. I'm going to transform z to minus iz in the quantum theory, in the quantum theory, in the quantum mechanics, and pz of k to ipz of k, which I'll call q of k, and I'll call minus IZK y of k in the quantum field theory. So when I transform the Hamiltonian, lo and behold, what was a minus z squared becomes a plus y squared, but what was a pzx becomes an iqx. So I've transformed to a Hamiltonian, which is not Hermitian. It's self-adjoint because that transform makes the wave functions normalizable, but it's not Hermitian because of the I. But nonetheless, all the poles in the propagator were on the real axis. And therefore, all the poles are on the real axis, and therefore the eigenvalues of the Hamiltonian are real, despite not being Hermitian. Well, that's not an issue because there's a very general theorem which says, if I can find it, hermiticity is only sufficient to get real eigenvalues. The necessary condition is that the Hamiltonian have an antilinear symmetry. This was first discussed by Carl Bender in the case where P was linear and T was antilinear, and these are called PT theories. CPT, of course, is the more general. But basically, in those theories, you will still get real eigenvalues as long as you have an antilinear symmetry. The reason being that if E is an eigenvalue, then so is E star. And therefore, E equals E star is an allowed solution. So antilinear is the necessary condition. So this theory, therefore, is a PT theory. However, the x squared and the y squared are normal Hermitian operators. They are self-adjoint acting on the eigenstates of the full Hamiltonian, but at the same time, they are appearing as Hermitian operators. But the total Hamiltonian is not Hermitian. When the Hamiltonian is not Hermitian, you have to distinguish between left and right eigenstates. And therefore, you have to distinguish between left and right derivative operators. You calculate the right eigenstate and the left eigenstate. They both have a minus y squared and a minus x squared. You calculate the overlap and you find that it is finite. So what we will finish up with is, once we've made this transformation, we'll finish up with everything being finite. Same story, you can calculate the wave functions and the wave, I won't discuss that now, I've discussed that on many of these meetings before. Now the norms are positive, we're in a normal Hilbert space, we have a positive norm, we have a positive time-independent product. So finally, finally, let me just show you, I can get rid of that minus IQX by making one more similarity transformation, and I bring the theory to P squared plus Q squared plus X squared plus Y squared, which is a completely normal two-dimensional harmonic oscillator, and these harmonic oscillator wave function states are normalizable. I needed to transform with an operator Q, and therefore the norm of the theory before I made the transformation was simply n e to the minus qm. This is the right eigenstate, and n e to the minus q is the left eigenstate. Now I'm closing in on finishing, then doing the relativistic case, of course, it goes through the same. But now I want to conclude by just discussing this from the point of view of path integrals. Here's the path integral. As such, it oscillates. It doesn't yet exist. To exist, we have to introduce damping factors. The standard Feynman I epsilon prescription, replace m squared by m1 squared minus I epsilon, m2 squared minus I epsilon. And then this gives me minus 2 epsilon sigma mu, where sigma mu is the derivative of d mu phi, m1 squared plus m2 squared times epsilon phi squared. Now, as I said before, this was a constrained system, and therefore the derivative of phi is an independent degree of freedom. It's not just take phi and take the derivative. Why do I need this one as well? For a fourth order theory, I need two pieces of information at the endpoints of the path integration, which is 4 pieces of information, and therefore I can't just integrate over phi. Now what I find is this one is nice and bounded, but this one is not bounded. So the path integral with real phi does not exist if I use the Feynman I epsilon prescription. However, if I use the funny one, the m1 squared minus I epsilon, m2 squared plus I epsilon, two things happen. Now the phi squared is well behaved, but the sigma mu has no suppression at all. The path integral doesn't exist. Well, of course, it can't exist because it's got no energy bound. So if you put in a complete set of energy states, you just get infinity. So we have two possibilities. One is the standard Feynman I epsilon. The other one is the funny I epsilon. One gives us a path integral which is halfway there. It's bounded on one of the degrees of freedom, but not the other. And the other one, the funny one, gives us a path integral that doesn't exist. But we can make this one exist if we take phi to be pure imaginary, which is exactly what I just did when I did that similarity transformation. And now I get minus epsilon phi squared, and this path integral exists. So to conclude, what I've been able to show you is that the path integral, when you first write it, you don't yet know what to do with the phi. If you take the phi real, you force yourself into the Ostrogrodsky realization. If you take the phi pure imaginary, you force yourself into what we used to call the negative norm realization, but now you get a completely well-behaved path integral. But now phi bar is still real, because I defined the path integral once and for all with pure imaginary phi, made that similarity transformation to real phi bar, and I asked, what's the quantum theory that would be associated with this path integral? And the answer is it's the one where I made the similarity transformation of the quantum operators. And when I've done that, the quantities that appear in the path integral are the eigenvalues of the quantum operators, and everything is real. And since this exists as a perfectly well-behaved path integral, the Green's functions that you generate from it are well-defined. And now you indeed can treat second plus fourth order theories as a, as an effective theory. So summary, the summary is exactly the same as the outline. Is omega finite? Not always. How can we find out if it is? Replace it by an equivalent wave mechanics. Do that for the fourth order theory. You find that it's not finite. So everything that we usually do doesn't work. The Hamiltonian is not self-adjoint. That was the assumption that was made in the discussion of the fourth order theory with the negative norm possibility. It was assumed that the Hamiltonian was self-adjoint, but you have to check in, is it indeed? And the answer was no, because we saw the wave functions were not normalizable. We found another vacuum in which another inner product in which everything was self-adjoint, everything was finite, no negative norms, no negative states, negative norm states, no negative energy states, perfectly well-defined quantum field theory. For the fermion theory, this issue never existed. We discussed we discussed path integrals. I didn't get around to the Wick rotation. We don't need to discuss that now, but we found a way of formulating the path integral in a way that made the Minkowski one well-defined. We've seen how this affects the Dyson-Wick expansion. How does it affect quantum gravity? Well, because R plus R squared is a theory that is used a lot in gravity. It's used in Starobinsky's inflationary model. We heard a lot about it in the two talks this morning. And as long as you can construct a Hilbert space with an inner product in which the Hamiltonian is self-adjoint and the operators are self-adjoint and their eigenvalues are real, then the resulting quantum output field theory is well-defined, a well-defined gravity theory with real gravity fields. So for the Ostrogrodsky theory, the input classical fields are real, the output fields are real. For the negative norm realization, the input fields are pure imaginary, the output fields are real. And so everything that everyone's been describing, I believe, is now justified. They weren't doing the Wick expansion correctly because the Green's functions weren't finite. But once you've gone into this different norm, then everything works as you wanted it to do. And all the results, it didn't matter what the Feynman diagrams, what was the relation of the propagator to the vacuum expectation value. As long as you got the Feynman rules were correct. They just, in my opinion, were derived incorrectly, but what I've done today shows you that, in fact, you can derive them. You can still get the same Feynman rules after all. Thank you.
Thanks a lot, Philip, for this very interesting talk. So, Alberto, you probably was the first. Alberto, you are muted.
Yes, so I don't know if I was the first. Just raise the hand. Can I go?
Yeah, please do, please do.
So I have a comment. So at some point you said that the Hamiltonian is not Hermitian in this construction for higher derivative theories. Just wanted to point out that as long as the Hamiltonian has a complete set of eigenstates, which is the case, I guess, in your construction, and correct. It has real eigenvalues, it's always possible to redefine the inner product in a way that the Hamiltonian is actually Hermitian.
Yeah, that's exactly what that is.
Okay.
Yeah, but you have to get it's not. It doesn't start off Hermitian. That's what all these. That's what all these. Where is it gone? That's what all these similarity transformations.
Yeah,
do.
it depends on how you define the norm.
Yes, let me just see if I can.
So the statement about hermeticity is a norm-dependent statement.
Let me try to explain.
As long as it has a complete set of eigenstates, it is normal. It is a normal operator with respect to some norm.
Yes.
If it has also real eigenvalues, it is also Hermitian with respect to that norm.
Okay. The statement that you're making is the statement that I usually make, and that is that this condition, Hij star equals Hji, is basis dependent. It doesn't hold in any basis. It did not hold in the basis that I was discussing. However,
well, not only that, it is norm-dependent.
Alberto, hold on. If the eigenspectrum of the Hamiltonian is complete and the eigenvalues are all real, then you can bring the Hamiltonian to a form by a similarity transformation in which you can use the Dirac norm. That is correct. However, the theory that we started with was not in that form. The Dirac norm is correct when you're through, but it wasn't the correct norm when you started. That was all I'm saying. I'm saying is, you are correct that if the Hamiltonian has a complete basis and all of its eigenvalues are real, you can find a similarity transformation which will bring the norm to the Dirac norm form. I agree completely. However, you have to do that. You can't write down the theory and say, I'm already in the Dirac norm. The answer is you're not. You're in whatever is the inner product that the theory will give you. Once you've got that inner product, you can then similarity transform it exactly as I've done here into the Dirac form. So the end product is the Hamiltonian's Hermitian and the Dirac form holds, but that's not the starting. That's the output. That's not the input. That's my point. But my other point, of course, is that when I started this theory and I found that the Hamiltonian was not self-adjoint, I didn't at that point know that I would ever be able to transform it to a Hermitian form, to a form that is manifestly Hermitian. I didn't know that. I didn't know that I could do that. But
you knew. No, you could know it from even.
Oh, I knew it. Of course, I knew it. What I meant was simply by finding that the wave functions weren't normalizable is not on its own a guarantee that I can find a normalizable basis.
Also Hermitian.
Well, however, because the energies were real and complete, that was the guarantee.
Because the energies, sorry?
Because the energy eigenvalues were real and the eigenfunctions were complete, that was the guarantee that I would be able to do it.
Oh, okay. So basically, it's what I said.
Yes, but you need that extra information.
Yeah.
Guys, maybe we postpone this part of discussion to discussion session and let Richard to ask a question as well.
Okay, thank you. Philip, am I correct that you're claiming that after you use this revised norm that the metric fields are now real and that they're moving in a real space-time? That is, that their time derivatives and space derivatives are also real.
Yes.
If so, how do you reconcile that with the negative norm that's evident in the perturbative rules for the propagator that you want to use?
Okay, the negative norm, if the negative norm had been finite, then the theory would be dead. The surprising
But I don't understand. The propagator is supposed to be a correlation function between two fields. If it comes out to be negative, then one of those fields must be imaginary, right?
Hold on, Richard. This is the propagator. Whether we can write it as this quantity depends on the Hilbert space. It may be that we have to use a different left vacuum in order to identify the propagator correctly. You can't simply say, here's the propagator, here's the C number propagator, and here's the matrix element of the time-ordered Green's function, and say that those two are the same. You have to construct the Hilbert space first, and then derive this, not afterwards. You have to do that first.
All I'm asking is the operators, however you define what you want the vacuum to be, if the product of two operators, the same operator that you now claim is a Hermitian operator, hence would correspond to a real field, comes out to be negative, how do you, it seems to me like that operator must correspond to an imaginary field or a field moving in imaginary time.
No. These are real fields because I showed you that after I made the transformation, I obtained a Hermitian operator. I showed you that these functions were Hermitian. Once I went into a Hilbert space, were the wave functions were normalizable. Now, what you're asking me is the question is how does that become?
But I don't understand. If you get the expectation value of a product of two, the same operator to be negative, then surely that operator is corresponding to an imaginary field.
No, you're missing the point. I've got to put in a complete set of states. And the states are not just NN. They're NN.
I'm just asking about the result. I don't care how you got it. Just the result. It seems like it must correspond to a field that's imaginary, not real. And then my next question is, doesn't that bother you?
It doesn't bother me because it's not correct. I mean, I've showed you that the field phi bar is real. It is a Hermitian operator with a real eigenvalue. I'm also telling you is how can I understand that T product? And the answer is that when you insert this as the completeness relation, you don't get a modulus squared. That's the difference. And that's how you can generate the minus sign in the propagator in a theory
So
with
where does the minus sign come from?
When you plug this in to the, when you just take the T product in the correct vacuum and you plug this in, the completeness relation, and then you evaluate it, you take the vacuum, the one particle state, you calculate it, and you will get exactly that propagator.
The point is that somehow or other, a square of a field is coming out to be negative, right?
It's not a square. It's not a modulus squared because you see, Richard, I'm not putting in some NN. If I did, then it would be modulus squared.
I'm not talking about the states. I'm talking about the operator. And somehow you're getting the operator to...
No, I'm evaluating the operator, not in a... It's not a modulus squared. That's all I'm saying. In the standard theory, it is a modulus squared. In these theories, because of the twist in the similarity transform, it's not a modulus squared. You have to do the calculation, which I've done and published. When you plug this in, you generate a minus sign in the propagator without a negative residue, without a negative norm.
I think it's also a perfect subject for today's discussion. I'm afraid we are 10 minutes past the schedule. And so let's have it in the discussion because it's an interesting topic to discuss. And let's thank Philip again, and we come back to discussions. So thanks a lot. And our next speaker is Ashok Sen. And Ashok Sen will tell us about d-instanton amplitudes in string theory. Welcome, Ashok.
Thank you. Let me... Okay, can you see my screen?
Yes.
Okay, thank you very much for the invitation. So my talk today will be on d-instanton amplitudes in string theory. And since this is perhaps not the main topic of the conference, what I have done is to try to give a general overview instead of going into the details. Okay. So I'll try to explain what the problems are and how you solve them. And here are my various collaborators in various combinations, and there are also parallel developments by the Harvard group who in fact started this subject. So let me begin by introducing d-instantons, what they are. So d-instantons are like d-branes, but the main difference with normal d-branes is that we have Dirichlet boundary condition along all non-compact directions that includes the Euclidean time. So these are d-brane configurations in the Euclidean string theory. So physically, they describe finite action classical solutions in string theory because they are localized in all non-compact directions. That includes time as well. And because they have finite action, okay, and the action can be shown to have the form of some constant divided by the string coupling GS, they are analogous to instantons in quantum field theory. The only difference with normal instantons in quantum field theory is that there you have the instanton action is proportional to 1 over g squared, but d-instantons are special in the sense that their action is proportional to 1 over g. But otherwise, they play the same role as instantons in quantum field theory. So in particular, they give non-perturbative corrections to string amplitudes. And because the action has the form of a constant over g string, the string amplitude, the instanton contribution to the string amplitudes have this form. There is an exponential suppression factor. And then there is a power series in GS. And the main task in computing d-instanton amplitudes is to compute this power series, at least give a systematic procedure algorithm for computing this power series. Now, because d-instantons are part of string theory, one expects that the worldsheet theory of closed and open strings, okay, we need open strings because open strings describe the dynamics of d-branes, including d-instantons. So you'd expect that the worldsheet theory of closed and open strings will provide formal expressions for the d-instanton contribution to the amplitudes. More specifically, if we integrate over the moduli spaces of Riemann surfaces with boundaries, they should generate the series expansion in GS that multiplies this e to the minus c over GS. So in this talk, I'll describe this in more detail. Okay, and we'll also see that there are various hurdles that appear on the way. Okay. And I'll focus on single d-instanton amplitudes. Okay. But of course, you can also consider multiple d-instanton amplitudes, which just require a little more technical details. So let me begin by describing the systematics of d-instanton induced amplitudes. Now, as I said, the d-instanton induced amplitudes should be given by the usual sum over worldsheet diagrams that we do in string theory. One difference between the d-instanton amplitudes and the normal string amplitudes is that if we look at individual worldsheets with boundaries on the d-instanton, they do not conserve energy or momentum. And the reason simply is that because we are putting Dirichlet boundary condition on all non-compact directions, including time, that breaks space and time transition invariance. Okay? And hence, we don't have energy and momentum conservation on the individual worldsheets. And this means that the disconnected worldsheets contribute even for generic values of external energy or momentum. Okay? So you can compare this with the usual string amplitudes or even usual field theory amplitudes. In the usual field theory Feynman diagrams, of course, you have disconnected Feynman diagrams. But the reason that we don't consider them usually is that if you have disconnected Feynman diagrams, then each connected piece has its separate energy momentum conservation. So if you consider generic energy and momentum of external states, which has the overall energy momentum conservation, then these disconnected diagrams don't contribute. And this is also the case for usual string amplitudes, but not for the D-Instanton amplitudes, because on the D-Instanton induced amplitudes, the disconnected worldsheets contribute for generic energy and momentum because you have violation of energy momentum conservation. We'll see later how the energy momentum conservation is restored. So with this understanding, we see that to get leading contribution to the D-Instanton amplitudes, basically, okay, so now we use the usual rule of string perturbation theory that a given worldsheet is weighted by a factor of G string to the power minus the Euler number. So to get maximum negative power of G string, we have to maximize the Euler number of the worldsheet. And this means that we should use as many disks as we can, because each disk gives a factor of 1 over G string. Okay, G disk has Euler number 1, so you get a factor of 1 over G string. And also we can use as many annulus as we want. Okay, so annulus is a diagram like this with 2 boundaries. Because annulus has Euler number 0, okay, so it doesn't have any G string suppression. So you can use as many annuli as you want, and you can so resum and write it as an exponential of the annulus amplitude. So then this is the structure of the leading contribution to a D-Instanton amplitude, that you have this exponential suppression factor outside, the exponential of the annulus, because you can use as many annulus as you want. And then we have a product of disks. Now the number of disks is limited by the number of closed strings that we have, and the maximum number of disks appear in diagrams where each disk has just one closed string vortex of it. So closed strings are the external states whose amplitude you are trying to calculate. Now at the next order, there are more possibilities. For example, you can insert 2 closed string vortex operators on a single disk. So the price you pay is that you have one less disk altogether. Okay, so you lose one factor of G string. Or you can take you can replace a disk by an annulus. Okay, so you have n minus 1 disks and 1 annulus, okay, on which you insert a closed string vortex operator. Again, replacing this by annulus, you lose a factor of G string. So these diagrams are of the same order. And this way you can write down systematically the expression for D-Instanton induced amplitudes to any order in the string coupling. So as far as the worldsheets diagrams are concerned, okay, the writing them down is not a problem. You can just draw all possible diagrams at any given part of G string. The problem, however, comes when you try to evaluate these diagrams. Okay, because to evaluate these diagrams, you have to integrate over the moduli space of these Riemann surfaces. And what one finds is the moduli space integrals diverge from regions in the moduli space where the Riemann surface degenerates. And here I am giving some examples. Okay, this is from C equal to 1 bosonic string theory. I'll say in later what this theory actually is. Okay, but this is just normal string theory. And here, for example, the annulus partition function for the D-Instanton has this shape, this form. And you can see that this integral diverges from t equal to infinity n. This diverges exponentially, and this one diverges logarithmically. If we take, for example, a disk 2-point function of 2 closed strings, it's proportional to a finite part, and then there's a divergent part, because this expression here you can see diverges from the y equal to 0 end. We'll explain what this variable y is later. And omega 1 and omega 2 are just the energies of the 2 external closed strings. Annulus 1-point function has similar divergence. It has a 2-dimensional integral over these variables v and x. And you can see that the integral diverges both from the v equal to 0 end as well as from the x equal to 0 end. And the question is, how do we deal with these divergences? Now, you may worry that, okay, these divergences are coming from bosonic string theory, but maybe bosonic string theory is not totally sensible. So you can look at superstring theory. So if we take, for example, D-instantons in type 2B string theory in 10 dimensions, the annulus partition function has a form like this. This 8 here comes from the Nebuchadnezzar sector. These are the bosonic excitations on the D-instanton. And this -8 comes from the Ramon sector, the fermionic excitations on the D-instanton. Now, if you look at this answer, you may be happy because this looks like it's 0. But if we actually take this as 0 and proceed, we get results for instanton corrections to the amplitudes that are inconsistent with the prediction of S duality. And that basically means that almost everything that you have learned about string theory during the last 30 years will be wrong. Okay, in particular, ADS-CFT correspondence will break down because the dual n equal to 4 super Young-Mills theory certainly is S duality invariant. So if the string amplitudes are not S duality invariant, then you are in trouble. So as we will see, the lesson is that we shouldn't treat this cancellation. We shouldn't just think of these as 8 minus 8 as 0. We have to carefully understand the divergences that come from the separately from the Nebel-Schwarz sector and the Ramond sector and learn to deal with these divergences. So the idea is that we have to make sense of these divergences and extract a finite result using string field theory. So I'll now explain what role string field theory plays in this analysis and why we need string field theory, but we will not really need too much details of string field theory. So what is string field theory? So string field theory can be regarded as a regular quantum field theory, which has infinite number of fields. Okay, basically one for each mode of the string. Okay, we know that in string theory, you have, of course, the usual massless states, which include the graviton and other gauge fields, massless scalars, etc. But then there is the infinite power of massive states. So string field theory is a way to write down a field theory which has all of these states as fields in the theory. And like in a regular quantum field theory, the perturbative amplitudes in string field theory are given by sum of Feynman diagrams. So for example, the propagator has a structure like L0 inverse, where L0 is the worldsheet scaling generator. Now this looks somewhat unfamiliar, not like ordinary quantum field theory propagators. However, if we look at the eigenvalues of L0, okay, in the string spectrum, the eigenvalues are proportional to k square plus m square, where k is the momentum that the string carries and m is the mass of the string. And then you recognize that the L0 inverse is indeed the usual propagator 1 over k square plus m square. And then depending on the spin of the particles, there are also numerator factors which I have not written down here. So we can build amplitudes in string field theory by summing over Feynman diagrams, just like a normal quantum field theory. And string field theory is designed so that formally the sum of Feynman diagrams reproduce the worldsheet expression. But to do that, we have to use what we call the Schwinger parameter representation of a propagator. So what we can do is that we take string field theory, we write down the sum of Feynman diagrams to any given order, and then we replace each propagator, L0 inverse factor, by an integral of this form. Okay, T is the Schwinger parameter. And after some manipulation, okay, we can match this to the usual worldsheet expression, where the T's become the moduli of Riemann surfaces after appropriate change of variables. So for example, this variable T that we saw here, okay, the T, Y, V, all of these come from these Schwinger parameters in string field theory language. So let's now look at the origin of the divergences. So in string field theory, the propagator is given by L0 inverse. And in the worldsheet, we replace it by the Schwinger parameter representation, which is here. Once you do that, then the correction to worldsheet becomes automatic. But now if you look at this relation, we see that this is, of course, an identity as long as the L0 eigenvalues are positive. But if L0 eigenvalue is negative, then the right-hand side diverges, because this diverges exponentially. But the left-hand side, of course, remains perfectly finite, okay, because it's just 1 over a negative number, which is perfectly sensible. And this is the first hint that string field theory is better than the worldsheet description in dealing with the divergences, because while in the worldsheet description, we'll run into a divergence when you try to integrate over T, in string field theory, you get a finite answer. But the most troublesome states are the L0 equal to 0 states, because you see that for L0 equal to 0, both sides diverge. Right? These diverges as well as these diverges. That looks like trouble. However, on the left-hand side, these divergences have a physical meaning, because 1 over L0 is a propagator. And the divergence that we see on the left-hand side means that we essentially sit on a pole of an internal propagator. Okay? That's the source of the divergence. And we know in quantum field theory that whenever you have a 1 over 0 in a propagator, we are doing something wrong, right? You are using you are manipulating the expression in a way that you shouldn't have done. Right? This is the usual infrared problem, that whenever you have a 1 over 0 in the propagator, you go back and ask what you are doing wrong. And this is what we'll do. So basically we'll use insights from quantum field theory to deal with this divergences when L0 eigenvalue is 0. And this is the essence of why string field theory is useful for dealing with divergences in the integrals over moduli spaces of Riemann surfaces. So we'll see that whenever we run into divergences of this kind, we reinterpret these expressions in the language of string field theory, and then we try to repair the divergence using insights from quantum field theory. So let me begin by writing down the exponential of the annulus amplitude. Okay, and the analysis that I'm going to describe in the next few slides will be general, right? This doesn't really rely on whether you are doing bosonic or fermionic strings or what kind of background you have. So the exponential of the annulus amplitude in any theory, okay, with the d-instanton boundary condition on the two boundaries of the world sheet, is given by an integral of this formula. Okay. The z of t is the world sheet partition function. Okay. So let me explain what this t is. So t essentially is the ratio of the circumference to the width of the annulus. Okay, so large t means that the circumference is becoming large compared to the width. And it's only the ratio that is of relevance because of the conformal invariance. So z of t, okay, the integrand that appears here, is a trace over all the open string states on the d-instanton, okay, weighted by this factor. So first of all, this -1 to the f counts whether your state is bosonic or fermionic. This is the factor which e to the minus t L0, where L0 is the L0 eigenvalue of the state. Okay. And so this e to the minus t L0 basically propagates the state over a distance proportional to t, okay, along the circumference. And this B0, C0 is a projection operator. These are the Gauss zero modes. This is needed to remove the Gauss zero modes. Because without the B0, C0 projection, you will just get 0. Because for every state, you will have every bosonic state, you will have a fermionic state by applying a B0 operator or a C0 operator. Okay. So the correct way to compute the annulus amplitude is to project into by this projection operator. This is sometimes called the Siegel gauge states. Okay, this projection operator is what is called the Siegel gauge. So with this, we can write z of t in a more suggestive form. So it's given by sum over the bosonic states weighted by e to the minus t times hb, where hb is the L0 eigenvalue of the bosonic states, and minus the sum over the fermionic states of e to the minus t times hf, where hf is the L0 eigenvalue of the fermionic states. And now we can also see that this integral will diverge when hb and hf are either negative or 0. Okay, for negative it will diverge exponentially, for 0 it will diverge logarithmically. So our strategy for dealing with the large T divergence is that first we'll take the case when hb and hf are positive and manipulate the expression to bring it in a form where we recognize this as a contribution coming from the string field theory. Okay. So for this, we'll use some identities, okay, that are valid for hb and hf positive. Okay. The first identity is that this integral for hb and hf positive is given by square root of hf and hb. Okay. This is just a mathematical identity. Both sides are well defined, and you can check that this is true. The second identity is that if you have hb to the minus half, it can be written as a Gaussian integral over a mode psi b. And similarly, if you have hf can be written as a integration over a pair of Grassmann variables weighted by this factor. Now notice that even though you have square root of hf here, I have written the expression for hf because it turns out that the fermions always come in pairs. So even though individually you get square root of hf, ultimately you always have integer powers of hf. For any hf, you get always even number of fermions. So now the idea is that we replace this by these integrals. Okay, integration over the bosonic modes and integration over the fermionic modes. And one can show that these integrals, we can interpret now the modes psi b, uf, and bf as open string fields on the d-instanton. And whatever appears in the exponent can be interpreted as the open string field theory action. But both of these are in a gauge fixed version of open string field theory, what is called the Siegel gauge. Okay, because the states that we have here all are projected by this B0 C0 operator. Now, once we have written it this way, right, we can say that this is the expression we will now use also for the other modes. Okay, when HB is negative or when HB or HF are 0. In that case, we can ask what is the interpretation in string theory, in the language of string field theory. And I should have said that here I have said it's string field theory, but the string fields here are really zero-dimensional fields, because on the d instanton, the open strings do not carry any momentum. So these open string fields, so even though I'm calling it field theory, it's basically the integral will run over infinite number of ordinary variables. Okay, zero-dimensional quantum field theory. Now with this, if we can interpret the modes with HB less than 0 as tachyonic modes. And as is normal for instantons, that when we try to carry out integration over these tachyonic modes, we carry out the integration by choosing the steepest descent contour, which basically means that instead of integrating over positive psi b direction, you should real psi b direction, you should integrate over imaginary psi b direction along which the integral falls off. In practice, this basically means that we can continue to use this 1 over square root of HB formula, except that HB is negative, so you'll get a factor of I. Okay, and that factor of I can be interpreted by saying that the psi b contour has to be deformed towards the imaginary axis. The more subtle issues come with the modes with HB equal to 0 and HF equal to 0, because they represent respectively the bosonic and fermionic 0 modes, and these have to be treated carefully. And here, the insight from quantum field theory has to be used effectively. So what I'll do in the next few slides is to explain where these 0 modes come from. The origin of 0 modes. So first of all, there are a class of physical 0 modes. So a physical bosonic 0 modes can arise from the freedom of translating the instanton along the flat directions, okay, like the Euclidean time. So as I said, the instanton is localized in space and time. So given an instanton, we can always shift its position in space or time. And those are, of course, 0 modes. Those are usually called the collective modes of the instanton in normal quantum field theory. So you expect that there should be bosonic 0 modes of this kind. And on the d instanton, they appear as particular modes of the open string. And here you know what the remedy is. We have to change variables from the bosonic 0 modes, okay, namely these psi b's for which HB is 0, to the d instanton position y. This will give rise to a Jacobian factor in general. And then at the end, you have to do the integration over y, but this has to be done at the end of the calculation. And this will eventually produce a momentum conserving delta function, just like ordinary instantons in quantum field theory. The integration over the instanton position is done at the end, and that produces the energy momentum conserving delta function that is missing at the intermediate stages of the calculation. And similar treatment has to be done and is needed for the fermionic 0 modes. If, for example, the d instanton in a supersymmetric theory, if the d instanton breaks certain space-time supersymmetries, then there will be fermionic 0 modes. Those are the collective modes. And you have to do a similar treatment, right? You have to integrate over those fermionic 0 modes, but at the end of the calculation. But what is special for d instantons, which you normally do not encounter in quantum field theories, is that you have a pair of fermionic 0 modes that come from the ghost sector. So these fermionic 0 modes arise even in bosonic string theory. Okay, the d instantons in bosonic string theory also has this fermionic 0 modes. So these are the world sheet ghosts. These have 0 L0. You can see that their conformal weight is 0. And these give rise to a pair of fermionic 0 modes. And that basically will tell us that we have a pair of integral UF over UF and VF with no weight factor. And that apparently will give you 0 answer, right? Because integration over the Grassmann variables give you 0 if you don't have any weight. As we'll explain, that these are the results of wrongly fixing the U1 gauge symmetry on the instanton. So for this, let's go back a little, and we consider a DP brane instead of a D instant. If we have a DP brane, okay, a D brane that spans P spaced directions, so P space and one time direction, Then it is known that it has a U1 gauge field living on it. And the action of the U1 gauge field is the usual Maxwell action. Except that when you come from the open string field theory, you find that besides the Maxwell field, it has one auxiliary scalar field phi. Okay, this is a gauge invariant action, which appears in the action in this form. Now you see that this field phi is actually trivial because it can be just integrated out. Okay, and recover the usual Maxwell action. But since string field theory gives us this, let's keep it as it is. Now the phi is the particular open string field that is associated with this particular mode. And you can see that because of this presence of the C0 factor, this is not a this is out of single gauge. So once we gauge fix, this field will not be there. Okay, but in the gauge invariant form, this field is there. Okay. And this action is of course gauge invariant. The Maxwell field transforms in the usual way under gauge transformation, and phi transforms by this, and you can easily see that this combination is invariant under this combined transformation. Okay, so this is what I have written again. And now we consider gauge fixing. Normally, in order to go from the gauge invariant form of string field theory to the gauge fixed form, we use Siegel gauge because that's what is used to make connection with the worldsheet picture. Okay, because in the Siegel gauge, the propagator is 1 over L0 as we described. So Siegel gauge here will correspond to setting phi equal to 0. Okay, because as we saw, phi is out of Siegel gauge. So in the Siegel gauge, you have to set phi equal to 0. And now you see that this combination becomes the usual Lorentz gauge, Maxwell action is Lorentz gauge. And because we are setting phi equal to 0, you have to pick up the Jacobian because transformation of phi has this box of the gauge transformation parameter. So you get the determinant of the box. And as in the Fourier procedure, you insert a pair of fermionic ghosts and you write a fermionic action like this. So on DP blend, everything is fine. Right? This is the way the DP blend, the string field theory, it gives a DP blend action. Okay, and that also makes connection with the worldsheet theory. But now let's ask what happens for the D instanton. Now for D instanton, as I said, this is like a zero-dimensional quantum field theory. Right? So the U1 gauge field that we said, right, has 0 components, right? There's no AV. The U1 gauge symmetry is still there, but there's no gauge field. And all the fields are X independent. The U1 transformation is also X independent, right? So theta, for example, is X independent. So you see that the ghost action vanishes, right? And this is the origin of the ghost zero modes that we saw in the earlier. Now you can also go back to this expression here and see what is the origin of this vanishing of the ghost action. Because on the DP plane, on the D instanton, this is identically 0. So phi actually doesn't transform under gauge transformation. And Siegel gauge corresponds to setting phi equal to 0. So this basically says that fixing the Siegel gauge is not allowed for D instantons. But the worldsheet theory gives the answer in the Siegel gauge, right? And that's how you get into all this trouble. So this is the way we identify what is the origin of this trouble. Okay, what is the origin of this extra 0 mode that we are finding? Once we have identified the origin, okay, the remedy is clear. Because phi doesn't transform under gauge transformation, we shouldn't gauge fix. So the remedy is that we undo the gauge fixing by simply using a original gauge invariant form of the path integral. Right? So you use this form of the action. Right? Mu is not there, so this part is not there. So the action is just minus phi square, as you can see. Okay, and there is no sense in which you can set phi equal to 0 as a gauge. So integrate over phi and drop the integration over the ghost because you are not gauge fixing. Okay, so integration over phi gives you this factor of square root of pi. But now you have to divide by the volume of the gauge. Okay, so that is given by the period of this gauge transformation parameter theta. Now theta is a string field theory gauge transformation parameter. And you have to carefully relate this theta to the standard gauge transformation parameter alpha. Okay, where the transformation of the field takes the form to the I alpha times psi. This can be done by carefully comparing the string field theory gauge transformation parameter with the standard gauge transformation laws, and then using the fact that alpha has period 2 pi. So once you can find the relation between theta and alpha, right, and you use the fact that alpha has period 2 pi, you can find the period of theta, and that's what you divide by. So this is the general procedure. So let me now give the example of the C equal to 1 bosonic string, right? I mentioned some of the results here. Some of the I showed you some of the divergent expressions. So let me explain what this C equal to bosonic string theory is. This is a toy string theory, but it's a very useful toy example because it teaches us a lot of things. So the world shift theory of this has a scalar field, including that describes the time direction. And then it has a Liouville field, which has a central charge 25. So total central charge adds up to 26 as is needed for bosonic string theory. And so the Liouville field describes an additional space direction, but there's a potential in the space direction. You don't have full translation invariance. And then it has the usual BC host system, which has central charge minus 26. So total central charge adds up to 0. So this theory has d instantons, what are known as ZZ instantons, Zamolodchikov and Zamolodchikov instantons. And this has Dirichlet boundary condition on both coordinates, x as well as this Liouville direction. And action in appropriate normalization is just 1 over G string. So in this theory, the exponential of the annulus diagram is given by this expression over here. Still the divergent expression, the same divergent expression that we saw, but now we should be less scared of this divergence because we know how to deal with them. So first of all, this e to the t, right, basically tells us that we have a tachyonic mode with hb equal to -1. So in the path integral representation, this will just contribute to 1 over square root of hb, which is I. -1, okay, is logarithmical divergence. So this is the result of the 0 modes, right? As we saw, the hb equal to 0 and hf equal to 0 modes give these logarithmic divergences. And this -1 turns out to be the result of a single bosonic 0 mode. And that is associated with translation along x, right? The instanton can be placed anywhere in the x direction. That's the mode. It cannot be placed anywhere in the Liouville direction because there's a potential in that direction. Okay, so the only translation 0 modes is along the x direction. So that's the bosonic 0 mode. And then this has these 2 fermionic 0 modes, which are the universal ghost 0 modes that we saw. The vacuum and the C1, C-1 in the vacuum. So now that we have identified the origin of these 0 modes, let's evaluate them. So the contribution from translation 0 modes is given by this d psi b over square root of 2 pi. Right? Let me show you the expression that we had. Right? D psi b over square root of 2 pi. The hb is 0 here. And the point is that you have to carefully find the relationship between the psi b and the actual d instanton position of y along the time coordinate. That can be done by a simple worldsheet calculation, and this is the relation it finds. Right? Here, GO is a constant, okay, what is called open string coupling, and this has definite relation with the the usual string coupling, GS. So this y integral will eventually have to be done, okay? And this integral will eventually produce this, that y dependence has the simple structure, okay? And this integral will eventually produce the energy conserving delta function, right, which is missing from the individual worldsheets. And the ghost 0 mode integral is replaced by the phi integral, as we have said, divided by the integral over the gauge volume. The phi integral gives you square root of pi. And this integral, after you carefully analyze the relationship between theta and this alpha parameter, which has period 2 pi, this integral turns out to be given by 2 pi over G open. Okay, G open is the same constant. So at the end, the net result of these 0 modes of this divergent expression is a product of this I that you see here, this factor 1 over square root of t pi times 1 over pi 0 root 2, and this factor. This product is the 1 over I over 4 pi square, and this in fact agrees with the dual matrix model result. Right? I should have said that the reason that we study, this is one of the theories one studies extensively, is because this has a dual matrix model description where the amplitudes can be independently calculated. Now it turns out the divergences continue also at higher order. So for example, the disk 2-point function has divergences from region where one vortex operator approaches the boundary. Annulus 1-point function also has divergences from the region where the vortex operator approaches the boundary or the circumference becomes large, right? These are expressions that we have already seen. Okay. So here, let me just point out this y, basically, so this, we are calculating this 2-point function. One vortex operator can always be inserted at the center of the disk, okay, because there is an SL2 isometry. Using that, you can always place one vortex operator at the center. So the y is essentially the distance of the other vortex operator from the edge of the disk. And you see that there is divergence as y goes to 0. Similarly, annulus one-point function is given by this expression over here. Here, x is the distance of the vertex operator from the edge of the annulus, and v is essentially related to the ratio of the circumference to the width of the disk. Okay, in fact, v is related to this e to the minus t. So the strategy is that we express the amplitudes as sum over string field theory Feynman diagrams. Once we do that, this will automatically replace the tachyon contribution by 1 over h. Okay, where h is the L0 eigenvalue. So whenever in the internal propagator there is a tachyon, right, the worldsheet expression will give an exponential divergent contribution, but the string field theory expression will just give a finite answer, okay, with a negative h. For the zero modes, okay, the idea is that from every propagator, zero modes would have given a divergent contribution, 1 over 0, even in string field theory, but you are supposed to remove the zero mode contribution. Because the integration over the zero modes are either to be done at the end, this is for the physical, bosonic, and fermionic zero modes, or they don't have to be integrated at all, like the host zero modes, right? We saw that host zero modes appear because of wrong gauge fixing, and we should not have them. And then we have to add the propagator of the field phi, which was not present in the worldsheet formulation. Because for every propagator in string field theory, right, the field phi propagator has to be added separately, because we have to use this gauge unfixed version, right? So we have the additional field phi that was not present in the single gauge. The worldsheet doesn't know about the existence of phi. And then you have to also account for corrections to the Jacobian factor, right? This change of variables from psi b to y or from theta to alpha, okay, gets corrected at every order, and that has to be taken into account. So here I have given the Feynman diagrams that contribute to this two-point function. Here the thick lines are closed strings and thin lines are open strings. And you see that there is an open string propagator here, and where all these divergences are coming from. Similarly here, these are the Feynman diagrams for annulus one-point function. And as I said, the general strategy is that you simply remove the zero mode contribution from each open string propagator, and you have to put the explicit phi contribution in each open string propagator. So at the end of the calculation, these divergent integrals that we saw earlier, after you basically apply the algorithm that we inherit from string field theory, this integral, for example, gets replaced by a finite expression over here, and this integral gets replaced by a finite expression over here. Now you see here there is a parameter lambda that has appeared. Now what is lambda? Lambda in fact is an arbitrary constant parameter that labels the various versions of string field theory. Here I have been saying, talking about string field theory, but it turns out there is no unique string field theory that describes string theory. There is a whole parameter of family of string field theories. But one can also show that those families of string field theories are all related to each other by field definition. So all physical expressions should be identical, right? They shouldn't depend on which member of the family you are choosing. So this lambda parameter is essentially labeling one such family. Now this lambda dependence looks like bad news, because these will appear in the string amplitude. So how can you have a lambda dependent expression over here? However, it turns out that the final result for any amplitude, okay, say take an amplitude in external closed strings of energies omega 1 to omega n, right? That always involves a combination of this form. Right? The f of a pair summed over all pairs, and g of the energy summed over all external states. And you can easily convince yourself that when you substitute these expressions over here, the lambda dependence simply cancels out. Once you impose the overall energy conservation, right, which happens at the end because of the integration over the zero modes, the lambda dependence simply cancels out, and the final physical results are all independent of lambda. So that's second consistent with what you know in string field theory. So here I have given the summary of all the theories where this kind of analysis has been done. C equal to bosonic string theory I already explained. So in fact, these authors, okay, they first started analyzing the C equal to 1 bosonic string theory. And they basically left these divergent contributions untouched. Okay, they basically said that, okay, we don't know how to deal with the divergent contributions, but anything that they could test without, by where the divergent contribution can be subtracted out, they found that it agrees with the matrix model. And then once we understand how string field theory deals with the divergent contributions, we found that even the expression is not only divergent contributions, once you grind it through string field theory techniques, they are in agreement with what you get from the matrix model. Then you applied it to C less than 1 bosonic string theory, where again there is a dual matrix model description. Type 2 being D equal to 10, right? That 0 that is showed earlier turns out to be not 0. We have to deal with the bosonic and fermionic zero modes separately. You have to deal with the ghost zero modes separately. And at the end of all this, we get results that are in exact agreement with S duality. And here are some other examples. And now, of course, we have tested it against many theories where the dual description exists, but we have also done new calculations where there's no dual description. For example, the 2A and 2B on Calabi-Yau 3 Orient reports. These are n equal to 1 supersymmetric compactification. Here, there is really no dual description which we can compare with. Okay, so here this is a new result that we obtained by using string field theory. And this is still some work in progress, and we expect that we will get new results here as well. Let me just say one word about unitarity. So based on our understanding of how to deal with d-instanton amplitudes and how to deal with divergences, we can now ask, are these amplitudes unitary? And the result is that the only source of breaking of unitarity is in the imaginary part of the exponential of the annulus partition function. We saw that the annulus partition function or the exponential of the annulus partition function can sometimes get an imaginary part if there are tachyonic modes. And those tachyonic modes typically signal that there can be or possible unitarity violation. And this has to be then understood in more detail, right? So whenever you have instantons with tachyons, okay, with tachyonic modes, that means the instantons are not really a minimum of the action, but they are saddle points. We could possibly have a unitarity violation, okay, because basically the contour of integration in the field space is getting rotated in the imaginary direction. Okay? And this, there has to be checked separately whether there is a genuine unitarity violation or not. So now let me just give my conclusion. So what you have seen is that the worldsheet theory aided by string field theory provides a fully systematic procedure for computing d-instanton amplitudes to in string theory. And this is, of course, of practical use, because in fact, in many string compactifications, one wants to know the superpotential, okay, for EI16 compactification. And in many cases, the dominant contribution to the superpotential come from d-instantons. Okay. So clearly understanding how to compute d-instanton contribution to amplitudes is a practical use from string phenomenology perspective and from any other perspective. Okay, in particular to gain deeper understanding of string theory like duality testing, various duality conjectures, role of resurgence, and so on. So with this, I'll stop. Thank you.
Okay. Thanks a lot.
Thank you.
Are there any questions? Let me see, maybe there is something in the chat or at least
I'm sorry. Okay, there's one before me, I think.
Oh wait, I see one raised hand. Alexei.
I am. Thank you very much, and thank you, Ashok, for your very inspiring talk about the instantons. I have actually a couple of questions. On the slide which you showed, well, I don't remember exactly the number. Yes, here, no, the next one, where you said that there is dependence on lambda, but this dependence is somehow irrelevant, which lambda, which is label of this string series.
Okay. Yes.
Here I'm a bit confused. So there is dependence on lambda, but then you get rid of it. How should I understand this? It means that if I get result in some string theory and I get this lambda, does it mean that I can somehow restore or recover answer from another string field theory approach?
Okay. The point is that this F if you remember this is a disk 2-point function.
Yeah.
And G is the annulus 1-point function.
Okay.
But in any d-instanton induced amplitude, you don't individually get F and G. Okay? So let me go back to the slide that I showed near the beginning. Here, for example, right? If we look at this expression over here, both of these are the same order in G string.
Yeah.
So you have to combine these two to get the d-instanton amplitudes, the first, the subleading correction to d-instanton amplitudes. And here you see that you have the disk 2-point function here and the annulus 1-point function, and it's a combination of these two that appear in the final amplitude. And what we found is that the lambda dependence basically drops out in that particular combination.
I see. So it drops when some particular combination is taken. This is what you say.
Yeah, the particular combinations which appear in the string amplitudes, there it drops.
Yeah, I see. Okay, and maybe another question. I want to understand what you claim about unitarity, that it depends only on not depends, but it's a result of imaginary part of tachyon in annulus partition function. This I understand, but does it is it clear that this statement somehow preserved when you go to higher genus surfaces?
Yeah. So this we can give a general proof that if the annulus partition function is real, then all higher genus amplitudes satisfy the reality constraint, satisfy the unitarity conditions. So the only source of violation is the annulus partition function. If the annulus partition function is imaginary, then unitarity can be violated.
This seems like a very, very powerful result, I can say.
Yeah, but see, this is basically because you have the worldsheet picture, right? And, yes. Okay, you have the worldsheet picture, you have the string field theory picture, and you can in general show unitarity from string field theory. Using in usual perturbative string theory, you can prove unitarity using string field theory, right? Or even using worldsheet diagram. So you use the same techniques. The only place where it breaks down is that if we have the annulus partition function has an imaginary part, then the effective action that we get becomes imaginary, right? So the reality constraint on the action breaks down. Because reality constraint of the string field theory action is one of the conditions that we use for proving unitarity. And what we can show is that this is the only source of breakdown of reality constraint. All the other higher genus amplitudes can be shown to be real, shown to give real effective action.
I see. Thank you very much.
Are there any further questions?
Yes, I have one. It's very simple, actually.
Sure.
Yes. So thank you for this talk. My question is, what's the physical meaning of a d-instanton? I'm sorry.
D-instanton, it's the same as instantons in quantum field theory, right? It's just they are in some of the string theories, and you can't. So any string amplitude gets contribution from instantons, just like so it gets contribution from perturbative diagrams as well as the instantons.
Okay, so the
it's
same
like
thing
in Young-Mills theory, right? You just have the instantons in the picture, and any amplitude in Young-Mills theory will get contribution from instantons. It's the same with the instantons, right? These are just part of the string theory, and string you cannot just avoid it. String amplitudes will get contribution from these instantons.
Okay. Okay. Thank you very much.
Okay. I see two more raised hands. So I don't know who was the first. Maybe Pulkit Khoderal.
Yes. Hi. So yeah, so this is just a clarification question. So we said that d-instantons have Dirichlet boundary conditions. So so that means the energy momentum is not conserved. But when we calculate in the string field theory, at least the bosonic zero modes, then we are getting energy momentum conserving delta function. So is there something which I have missing, or what's the?
Yeah. So the point is, individual worldsheets do not conserve energy or momentum.
Okay.
But so you have to combine the contribution, all the contributions first. So let me explain what we mean by it doesn't conserve energy or momentum. Right, so you do the calculation first at this level.
Okay.
Right, at the, or even a leading term is at this level. Right. If you look at individual worldsheets, there's no energy momentum conservation on this. Otherwise, this amplitude will be trivial. Right. If there is there's only one external string. So if this had energy momentum conservation, then the external string would have to carry zero energy and zero momentum.
Right. Yes.
But that is not the case. So you calculate this first, right? Okay. And at the end of all this calculation, you take the product. Okay. And after you do that, you are supposed to integrate over the instant on position. Right? The zero mode that was separated out, that has to be integrated at the end. And that integral recovers the total energy momentum conservation. So you recover the energy momentum conservation or only the sum of the energies is conserved. Right? Not the individual ones.
Right. Yes. Okay.
And this is the case even for ordinary instantons in Yang-Mills theory. Right? When you try to calculate the instanton-induced amplitudes in Yang-Mills theory, the instantons break space-time translation invariance. Right? Yes. So it looks as if you violate energy and momentum in the instanton background. But at the end, you have to integrate over the instanton position, and that recovers the energy momentum conservation.
Okay. Yes.
Right? So once you make connection with string field theory, right, and you put it in the language of a quantum field theory, then whatever you have learned in quantum field theory can be applied.
Okay. Great. Yes. Thanks.
Okay, Bob Hold'em.
Yes, you have negative propagators showing up, and you called them tachyons, but could they also be called ghosts?
Okay, you could call them ghosts, except that, see, these are zero-dimensional theories, right? So there's a momentum, because these are these degrees of freedom are the degrees of freedom on the instanton. So because they have no momentum, right? It's not clear. Normally, the ghosts are the ones which k-squared has a negative sign.
Well, it's usually when the propagator is negative, the whole propagator is negative, that's a ghost.
Well, that's not, I'll not call that a ghost, because even in normal quantum field theory, right? If you take k-squared to be sufficiently negative, the propagator becomes negative. Right? That we don't call ghosts normally. The ghosts are the ones where the kinetic term is negative. See, otherwise, take a scalar field theory, it's propagated 1 over k square plus m square. In the Lorentzian theory, k square is not definite. It doesn't have definite sign. So you can certainly have internal scalar lines for which k square is negative. K square plus m square is negative. Right? Okay. But the point is, because they're instantons, you can't really distinguish between ghosts and tachyons. They are just modes. They are just reflection of the fact that the instanton is a saddle point rather than a minimum of the action.
So for me, a negative propagator means a negative norm as well. So you don't think
so these don't have negative norm. No, these are all positive norm states.
Yeah.
Yeah,
okay.
They're all positive norm states.
Okay.
Are there any further questions? Well, if not, let's thank Ashok again for this interesting talk.
Thank you.
Move to discussion session in that case. So, and I'm not a chairman, or am I? I don't know.
You initiate discussion, and then it will go.
I should instigate discussion. Okay, good.
Can I try to answer Richard's question? We didn't really have enough time to go into it at the end of my talk.
Yeah. Sure. Richard, are you there?
Richard, are you there? Oh, okay. Wait till he comes back.
Yeah, maybe we should wait a bit till Bob, you have another question, or is just
for Philip?
Sure.
Similar to Richard's question. So Philip, have you considered how the optical theorem is satisfied?
The answer is no, but I have considered how the Lehmann representation is satisfied. I've not looked at the optical theorem.
See, with negative, with negative propagators, there are minus signs that show up.
Okay, thank you.
On the right side of the optical theorem, and theorem to be satisfied, you need negative signs on the right-hand side as well. And those negative signs usually come from the negative norms.
Okay.
But if you remove the negative norms, then I don't see how it's satisfied.
Okay, I have, now I realize I have looked at the issue. If you draw a loop graph and you cut it, then you will get a negative discontinuity because of the minus sign. Right. Even with the positive norms, you'll get a negative discontinuity. That's correct. However, in these PT theories, you get something very, very strange. You get a correction coming from the tree graph. And the tree graph exactly cancels the negative discontinuity in the loop graph. And the result is that the entire tree plus loop graph is unitary with no negative discontinuities. I wrote a paper on that in PhysRev D a few years ago.
Can you phrase that in terms of the optical theorem?
I did not go beyond that. What I wanted to show was that the perturbation series, you have to do something special with the tree graph plus the loop graph, and together they were unitary. Now, what that would mean is you'd have to do the same thing for the optical theorem, except I had not done that. In fact, I did. I did. The point is, it's TT dagger is equal to the discontinuity. So there's a mismatch in powers, in perturbation powers. The TT dagger is lambda squared, and the discontinuity can be lambda. And so you have to, I did match them. Now I remember. I did discuss unitarity from the point of view of the S matrix in that theory. That's in the paper.
But if you look at the optical theorem with the same orders on both sides, then the left-hand side is a loop amplitude.
Yes.
And those have negative signs coming in.
Well, then you've got to go to second order in the tree graph.
Well, no, you just go to the right-hand side, which is also second order, and these signs should compensate each other.
Well, I'm claiming that the ones I've looked at did compensate. I haven't gone beyond one loop, or I haven't gone beyond 3 plus 1 loop. But that's anyway. It's all there. I mean, the theory has to be unitary because you've got it. You're working in a well-defined Hilbert space. But the way it works is very, very funny. Yes,
it would be interesting to check that. Yes,
that would be wonderful. That I agree. Basically, the issue for the S matrix is I showed you that the left eigenstate has this extra factor of e to the minus q. What happens is that so do the outstates. The S matrix is in out times e to the minus q, and that's the one you have to use to check for unitarity. Now, I haven't done everything in that regard, but I have shown that definition of the S matrix is unitary. That's the thing I've shown. And the other thing is this: S is not equal to S dagger is not equal to S to minus 1. The thing that is S to minus 1 is e to the q S dagger e to the minus q, because there's this e to the q on the in and out states. And so the unitarity is very different. And I've worked that all out. I haven't done everything that you asked me.
Yeah, well, the optical theorem is just the statement of what you're just talking about.
Yes, that's right. But then it's just that it's called pseudo-unitarity. It's not S dagger, which is S to minus 1, but it's this similarity transformed S dagger. And then you get, I would guess, the pseudo-optical theorem.
Well, I agree pseudo-unitarity is what I'm talking about too. And,
yes.
And here you need the negative norms to make things work out.
Yes, but there are funny little things coming from the tree graphs which take care of them. I mean, the first thing I thought about was, okay, I've got rid of the negative norm for the free theory, but as soon as I have a loop, I'm going to get a negative discontinuity, and I have to get rid of it somehow. And that's exactly what I did, because I realized that I'm using pseudo-unitarity and not regular unitarity. And that's I mean, I haven't done a pseudo-optical theorem, if that's what you're asking me. But I think it's pretty much there.
By the way, Philip, if I may ask, so
yes.
I hope I did not misunderstand your talk. I have not misunderstood it, but it looks like you would claim that if I take one oscillator with a plus sign in front of the Hamiltonian,
yes,
add to this oscillator another oscillator with minus sign in front of the whole Hamiltonian, then suddenly, and no interactions whatsoever, then suddenly I would not be able to define a vacuum state there?
What I'm saying is you have, there are many different ways of writing the PU oscillator. The one that you're referring to uses phi and box phi as the dynamical degrees of freedom. And then you get exactly what you said. You get one oscillator with a plus sign, one oscillator with a minus sign.
Sure.
But box phi is not the conjugate of phi. The conjugate of phi. No, the conjugate of phi is phi triple dot.
Yeah.
Once you know that, you then have to do exactly what I did, and then you will find that the Hamiltonian is not self-adjoint until I have to transform into a different region in the complex plane.
Sure. But let's forget
about... Back up a second, Alex.
Mm-hmm.
What you can show from what you suggested is that the Ostrogrodsky issue of unbounded energies is there. But that's a different Hilbert space than the one I'm working in.
But it looked like for me that you can take basically one oscillator with plus sign in front of the Hamiltonian, another oscillator with minus sign in front of whole Hamiltonian, no interaction whatsoever. And can I don't think there is any problem with defining vacuum state. Of course, it's not a state of minimal.
But that's a state, right? That's a state with no. That configuration in a Hilbert space where the states are normalizable is a state with no lower bound on the energy.
Of course, because there is none classically, right?
There's none classically and there's none quantum mechanically.
Exactly.
That's correct, but that's not the realization. There's another realization of the fourth order theory in a totally different Hilbert space, and it's the one that you think has a negative Dirac norm. But in that space, the Hamiltonian is not self-adjoint.
Sure.
The one you described, the Hamiltonian was self-adjoint.
Yeah, exactly.
But not bounded below.
But so are classical solutions, right? So we know that from basically from correspondence between classical and
okay. Let me go back to what you're asking me about. As far as the correspondence principle is concerned, the first thing that you think to do is to write the theory with real variables. Sure. And then when you write the quantum theory with operators that are well-defined, whose real variables are the eigenvalues, you find that you are in a state with no lower bound on the energy. And the point is, a Hermitian operator can be self-adjoint, can have all eigenvalues real, but does not necessarily have a lower bound on the energy. That does not follow from the reality and the self-adjointness. And I'll give you an example. The position operator is, its eigenvalues go from minus infinity to plus infinity. It's perfectly well defined. So that's what happens if you simply start with the classical theory with real variables and try to identify a quantum theory that will correspond to it. Both of them are not defined because both of them have no lower bound on the energy. And as I showed in the talk, in that case, the path integral, which is only integrated over the classical real variables, the path integral diverges, which it has to because it goes like e to the minus e0 tau at large Euclidean time, and e0 is negative.
No, but suppose we don't want to do, you see, the point is, it would be very strange. So we can perfectly well formulate Hilbert spaces for these two decoupled oscillators, write tensor product, write Schrödinger equation.
Oh, yes.
It's all working fine. So now, of course, if you write proper path integral, it will work out fine, right?
No, the path integral doesn't exist. It can't exist if the energy is not bounded below.
No, of course, Euclidean path integral does not exist, and what to do with Lorentzian path integral, that's a different story. But
I showed you in the talk the Lorentz path integral is not damped either.
But that's a no. Look, with that but that would be a miracle, right? That you write path integral.
Yes.
The system for which we know from Schrödinger perspective, from Schrödinger picture, from Heisenberg picture, we know that everything works perfectly well. Now we write path integral and it doesn't work. That would be strange. It means that we use the wrong definition of path integral. No.
No, the path integral has if you have matrix elements of e to the minus IHT and you let t go into the deep Euclidean region,
but
then
it's not allowed.
No, that's how you read off the energies. I'm not doing a Wick rotation. I'm just replacing IT by tau.
I agree. But it's this part of the procedure. You see, when we derive path integral, let's say Hamiltonian path integral,
yes,
it's not Euclidean. Of course, we don't know how to make sense out of this Hamiltonian path integral, but it will be as well defined in Lorentzian as any other path integral.
Okay, well, what I claimed in my talk was the PU oscillator, not written the way you've written it, though, just starting with the original Hamiltonian that I presented, is not the Lorentzian path integral is not damped with the I epsilon prescription in the propagator that would lead you to negative energies and positive norms. It's just not damped. The one you described is an okay path integral. The one I looked at was not. And then what I asked was, is there any way to make it well-defined? I mean, the issue is, can I finish up with a path integral where the path integral is well-defined and therefore there are no states, there are no negative energy solutions? And the answer is yes.
But that straightforwardly breaks classical to quantum correspondence.
Okay. So now let's go to correspondence. Thank you. Now, it turns out that classical physics has a much bigger range of symmetries than we usually say. It has symplectic transformations which preserve the Poisson bracket relations, even if you go into the complex plane.
Of course.
That's right. Now, usually you don't care. Usually it's not something that's any big deal. However, for the path integral, that similarity transformation takes you into a measure for which the path integral exists. Now, you then ask, what's the corresponding quantum theory? The quantum theory, you make the similarity transformation on the operators with the same angle. And then you have a correspondence at any angle in the complex plane. You have a Poisson bracket algebra in the complex plane and a commutation algebra in the complex plane, and you can go from one to the other by canonical quantization. So you're correct that the conventional correspondence principle doesn't work. You're presupposing that you start with real variables. What I'm saying is you can have a correspondence principle at any angle in the complex plane, provided you make symplectic transformations and similarity transformations with the same angle. Now, that becomes of interest because in the particular theory I've studied, when you do that rotation, you finish up with an operator whose eigenvalues are real. So in my language, I say, I start the path integral with a pure imaginary field, not with a real field, with a pure imaginary field, rotate it into this domain in which it's real, and then I do the correspondence principle along that direction.
Sure,
and
but
I finish up.
One negative, you get two positive oscillators.
Okay.
It's the same, no?
Now, the next question is, how can I diagonalize that theory? Can I diagonalize the quantum theory? And the answer is yes. And I showed you in the talk that it diagonalizes into two decoupled oscillators. It's only a quadratic theory. I can always diagonalize it. So Can I do a screen share? And maybe I'll answer you that way.
Screenshot?
Can I do a screen share?
A screen share, yeah. Well, I thought you should be allowed to. But
You have to. I have to give you lots of money, and then maybe you'll arrange it.
But you see, I think you're a co-host, so you should be able to.
Oh, there I go. There I go. Yes, I'm still.
See, I don't have chances to get any money, so it's okay.
What happened here? Hold on. Oh, I'll do one more thing. There we are. Okay, if I don't know if you can see this. That one, yes, this one. This is a paper I wrote with Carl Bender in PhysRev D. Then I start out with this Hamiltonian. That's the one I get from the correspondence principle, exactly, from the Poisson bracket algebra. Then I made one similarity transformation, which converts one oscillator, but not both. And that gives me this Hamiltonian, which is now no longer Hermitian, but is self-adjoint because now the wave function is well defined. And now I make a second transformation, which is with this funny Q here. And then I construct a new Hamiltonian, and that one is p squared plus q squared plus x squared plus y squared. So by a sequence of similarity transformations, I am able to bring the original Hamiltonian, the one that we got from, well, I got it from using the Dirac constraints. I could diagonalize this into a normal pair of oscillators. And that's what I've done.
No, but of course, if you use complexification, for sure. But
yes,
in that case, there should be correspondence between initial data. And initial data, for these complex new variables, you would need to multiply with i's.
No, there's no, the initial.
Otherwise, canonical transformation don't work.
No. A canonical transformation does the following. You can go from a classical theory to a quantum theory, provided the Hamiltonian of the quantum theory is self-adjoint. There's no correspondence principle if it's not self-adjoint. But you don't know whether it's self-adjoint until you've solved the quantum theory and constructed the wave functions. Now, we don't usually say that because every case that we've dealt with before these higher derivative theories, the Hamiltonian was self-adjoint. It was never an issue. But in this particular case, that's not true.
But it's also self-adjoint if I have absolutely standard procedure. It just will have negative energies, unbounded from
it's self-adjoint with negative energies. So the question is, what you're asking me is this. I'll say it differently. We've agreed that the Hilbert space in which there's negative energies and the Hilbert space in which there are negative norms are different Hilbert spaces. Do we agree on that?
Negative norms, I would say that it's not a Hilbert space at all.
We'll get to that, and I'm going to make it into a proper Hilbert space in a moment.
Yeah.
So what that means is that this path integral, in principle, can describe two different quantum theories, not one. One with negative energies and the other supposedly with negative norms. However, it's one path integral. So how can it possibly describe two quantum theories? The answer is, it depends whether Z is real or pure imaginary. Both of them are legitimate because I can make a symplectic transformation on the classical fields. Now, it turns out that the one with Z real corresponds to the system that you just described, where the Hamiltonian is nicely self-adjoint. The eigenvalues of the Hamiltonian are the real numbers that you started with, but the energy is unbounded. The alternate theory is one where Z is pure imaginary. And I can define as my initial theory, a theory where one of the fields, one of the oscillators is defined with pure imaginary functions. I can do that. That's my theory. I don't like that theory, so I don't dislike it, so I make a transformation into the complex plane to make that coordinate that was pure imaginary to make it real. And at the same time, I then ask, well, if that's real, what's the Hamiltonian in the analog similarity transform theory? And the answer is in that theory itself adjoint. So you're absolutely correct. I can't describe this path integral with real Z and hope to ever get to the negative norm case. On the other hand, the negative norm case as ordinarily formulated, where you get the Dirac norm is negative, it turns out that that Dirac norm is not just negative, it's infinitely negative. And that means that you haven't yet found a Hilbert space for which that theory is well defined. And that's what Carl and I did.
Yeah, but it's very well known. If we try to find eigenvector for not annihilation operator, but for creation operator, there is no such a normalized state. It's just exactly Gaussian with plus sign.
Oh, okay. So what I did was I changed the basis from the A's and A daggers to the P's and the X's.
But
and those operators have eigenvalues.
No, of course. But I mean, at the end, it's you see what I don't understand. So physically, I don't understand very simple thing. So if we take Piles-Uhlenbeck oscillator in the very simple form of it, we know that it just corresponds to two decoupled oscillators. Classically speaking, if you do only canonical, real valued canonical transformations. So after that, we know whole dynamics of this thing, we know energy, classical, and so on. Now, if we apply to this linear system, standard quantization, we know how to do. We know how to proceed. We obtain all meaningful results exactly corresponding to classical situation.
Absolutely. I'm not in dispute with you. Now I'm saying is I'm going to give you a different theory. Two oscillators.
Sure. It's
I'm going to give you a theory, two oscillators, one of which classical, X and P are real, and the other one, X and P are pure imaginary. I'm going to look at that theory, and I'm going to ask, what quantum theory does it respond to? And that's the one here, where the Z becomes the IZ. And that theory, you look at it immediately, it's two oscillators, and they're both bounded. You see, you're presupposing from the start that the oscillator quantum operators, the P and the Q, are Hermitian operators, and that the classical P and Q are their eigenvalues. And I'm saying is, and now I'll tell you that the secret of PT, and maybe this is the answer to your question. When we write down a Hamiltonian, such as this one, we look at this, and the first thing you'll say to me is that that Hamiltonian is Hermitian. Why? Because the P's and the X's are Hermitian. Now, but when I solved the Schrödinger equation for that Hamiltonian, I found that the wave functions weren't normalizable. Now, what that means is the following. Ordinarily, the operators that appear in the Hamiltonian are Hermitian on their own eigenstates. But those eigenstates are not in the same Hilbert space as the eigenstate of the Hamiltonian. Now, usually it doesn't really matter because usually they all go together. You all work on the same Hilbert space. However, when we say that these operators are Hermitian, we have in mind a particular Hilbert space on which they act. That's not the space in which I can find the eigenstates of the Hamiltonian. So there's a mismatch between eigenstates of the operators in the Hamiltonian and the eigenstates of the Hamiltonian itself. Now,
wait. This I already don't understand. So if I have two oscillators.
Yes, here we are. Two oscillators.
I have tensor product.
Yes.
One corresponds to positive energy, another one to negative. This
negative energy.
Yes, and then there is a tensor product of them. I can multiply all of them, and this will be clearly eigenstate of this Hamiltonian with the energy which is the sum or differences or whatever.
Absolutely, I have no problem with that. What I'm saying is that this Hamiltonian has another realization in which the energy is bounded. But in the realization where the energy is bounded, the eigenstates of the operators in the Hamiltonian the operators in the Hamiltonian are not Hermitian when they act on the eigenstates of the Hamiltonian until I've made that rotation. That's the odd. In other words, it's not guaranteed. When you look at this Hamiltonian, you would tell me, oh, it's Hermitian because it's full of Hermitian operators. And I'm going to tell you, it can't be Hermitian if it's got a bounded energy because of this minus z squared term. Sure. So if it's going to have a bounded energy, it can't be Hermitian.
So, but
so then the question is, can I do something to it to show that in fact it is Hermitian?
But wait a second. So at the end, of course, when we write some formula,
yes,
right, there are some assumptions. For example, assumptions are if you write classical dynamics, that let's say your coordinates are real, or your coordinates can be complex, or your coordinates can be algebras, you know, whatever, quaternions. Of course, if we fix what the coordinates are, we know exactly how to proceed, right? Of course, if we don't fix it from the very beginning, we can get different results.
Okay.
But
I'm going to fix the coordinates from the beginning so that, where's it gone? So that this path integral exists. That's what I'm going to do. I'm going to make a demand on the coordinates to be in some domain in the complex plane for which this path integral exists.
But wait, it does exist in the representation I told you, in the standard.
Yes, but no, it doesn't, because the energy is unbounded from below.
It does.
Okay. It's not, okay. In your language, you would say the Euclidean path integral doesn't exist. It does not exist at deep Euclidean time. Okay, we're in agreement. Well, we would like a path integral to also exist at deep Euclidean time. I mean, that's the way we usually do Euclidean field theory. So you can say, all right, so you found an example with the two oscillators which are offset by a minus sign, where you can't do Euclidean field theory. Okay, I mean, that's okay, you can do that. So as far as I'm concerned, you would then dismiss this theory and say that theory can't be relevant to the real world.
But how come? If Schrödinger picture, Heisenberg picture describe it perfectly well.
Okay, that's I would say it's not relevant because the energy is unbounded. I can demonstrate that by saying that it doesn't have a Euclidean extension. But nonetheless, that's one possibility. I can tell you that this path integral has a different realization, one in which the energy is bounded. But for the energy to be bounded, and I need Z to be pure imaginary.
Yeah. No, this I understand.
That's what I've done. I mean, you can't. There are two.
Can I say something about the Euclidean path integral? Because we have.
I'm sorry. Just let me finish to Alexander. There are two realizations of the theory, and I'm discussing the other one and trying to make sense of it as a quantum theory. Alberto.
Yeah. So you were asking about the Euclidean path integral, right? So
yes,
some quantization such that the Euclidean path integral exists. We actually have a paper, Alessandro Strumi and I, where we provided this quantization. And for the Pi-Sullenberg oscillator, even the interacting Pi-Sullenberg oscillator, where the potential is a function of your Z, essentially.
Yes. Z to the 4.
Not necessarily, some function of Z. Okay. And so the trick there was was similar to your trick, but the I was put in another place. So with the Pi-Sullenberg oscillator, basically you have two canonical coordinates. One is Z, and the other one is Z dot, right?
Yes. Okay. You made the X pure imaginary.
I don't remember what your X is, but I put Z dot, the coordinate that we called Q1, that was Z dot in your notation. We promoted to a complex variable, imaginary.
Okay. Yes.
So the spectrum was purely imaginary, and in that case, we could have a well-defined Euclidean path integral.
Yes. Yes. Okay.
This was the question, as far as I understand.
Okay. Let me try to
Alexander
respond.
was asking about this.
Okay. Let me try to respond to your question. See if you can follow me. When you do the wick rotation, you go along the axis. You can either go down and then up, or you can go up and then down. Complexifying Z, you go up. Complexifying X,
But
you
what
go
is your X? I don't remember.
X is Z dot.
Ah, it's Z dot. Okay.
When you complexify one or the other, they give you different wick contours. And what you said, everything you said is correct. That you can complexify Z dot, you get one particular wick contour, and you get to a Euclidean theory. And that was the case essentially that was discussed by Hawking and Hertog. The other case is you complexify Z, and then you have to do the wick contour a slightly different way. But nonetheless, you still get to.
If you complexify Z,
yes,
you don't get a well-defined Euclidean path integral.
Not if I do along and then down in the complex T plane. I have to go up. I have to go along and then up. That's the difference. But it's okay. I'm in agreement with you. Alberto, I'm in agreement with you. I'm not interested in complexifying X and Z dot. You're correct. I've got two oscillators. What I'll finish up with is a wave function that goes like e to the minus z squared, e to the plus z squared and e to the minus x squared. So my wave function is well behaved for large real X. So I leave it like that. What you want to do is you want to flip this.
But even
that's okay. All of these things are perfectly okay.
Even with our quantization, we solve the problem of the non-normalizable wave function. So even by complexifying X and not complexifying Z, the wave function then was normalizable.
Yes. Let me say two things.
So what you want to complexify, I guess, depends on the problem you have.
Yes. Everything you've done. Everything
the
you've done.
Euclidean path integral, I think, needs to be well defined. Because,
yes, absolutely.
It is well defined in normal theories. That the path integral that it is well defined in normal theories, not the Minkowskian one. The Minkowskian one is a formal.
Yes, but the Minkowskian
path integral, which is just used to sum essentially the perturbation theory, while Euclidean path integral is something you put on the computer with lattice regularization. So it needs to be well defined.
Let me just respond to you in the following way. The wave function diverges in one coordinate and converges in the other. Therefore, you only move one of the oscillators into the complex plane. And so you can construct a theory where the oscillator...
I'm saying that there may be more than one possibilities. Your possibility and my possibility can be both viable. Maybe it depends on the...
You're absolutely correct, because you're only continuing one of the oscillators into the complex plane. That's what I was trying to say to Alexander a moment ago. If he has oscillator 1 with positive sign and oscillator 2 with negative sign, the one with the negative sign you can continue into the complex plane. So the trick here is that you only continue one of the oscillators. Now, that looks very peculiar, because if you think of X as Z dot, how can Z be complex and Z dot stay real? That's the thing that's puzzling, and that's not answerable until you realize that this is a constrained system. And that Z dot, when replaced by a second
system, it's a quantum system, so...
in
principle, there are two independent canonical variables.
It's exactly right. You would have thought
you can complexify one and not complexify the other.
Exactly, only because Z dot becomes an independent canonical variable. But that's already true in the classical theory. That it doesn't. You don't have to wait to go to the quantum theory. So Z dot and Z are independent variables. And that's why you are able to make sense of the negative norm problem. It's because the negative norm only appears in one of the terms in the propagator, the 1 over k squared minus m1 squared minus 1 over k squared plus m2 squared, it only appears in one term, not in both. Therefore, you only have to move one oscillator into the complex plane.
Yeah, actually, there are also other possibilities, because when you do the canonical transformation from, you know, z dot, like let's say q2, q1, to new canonical variables, we called it q1 prime, q2 prime. I don't know how you called it.
Yes.
You can also complexify one of these two, between q1 prime and q2 prime, and leave real the other one. So there is an infinite ways. There are many infinite. There are an infinite way, an infinite number of ways of assigning the I. Essentially, you can assign the I to z, you can assign the I to z dot, or you can assign the I to q1 prime, or the combination.
Let me try to respond to that in a slightly different way, if I can find it. That might not be easy.
So the question is then, what do you do for gravity? This is the question.
I'll come back to that in a second, but you can see what's happening here is I have omega 1 squared minus omega 2 squared. I'm working with omega 1, which is m1, greater than m2. But you could work with m2 greater than m1. And then when I call one oscillator, you call the other oscillator. That's all. I mean, you have that as an option. I mean, you see, maybe I say it this way. When I write down the theory, I haven't yet specified whether omega 1 is greater than omega 2 or omega 2 is greater than omega 1. But you can see from here, I'm working with omega 1 greater than omega 2, so that this transformation, e to the q, is a real transformation. Now, if you want to work with omega 2 greater than omega 1, you can do, and what you will call positive energy becomes negative energy, and the other one flips over. But either way, you'll only have one negative residue, not two. And that's the one. I'm in agreement with everything you've said. You see, the point I said, actually, the first thing I said in the talk is that when you write down a theory and you write down a Hamiltonian, you write down canonical commutators, you haven't yet specified the theory. You have to specify the Hilbert space on which those operators actually act. And you have to construct a Hilbert space where you have an inner product, which is positive, finite, and time independent. And until you do that, you don't have a quantum theory. Once you've done that, you can then ask, well, what was the classical theory that would canonically quantize that would get me to that theory? And the answer that you've given, and the answer that I give, is that at least either z or z dot has to be continued into the complex plane.
Or there are the other possibilities I said before, q1 prime, q2 prime. There's an infinite number of possibilities.
Absolutely.
So depending on the theory you have.
Philip, but may I interrupt you and ask you just a super stupid question? So there is a mathematical theorem which is saying that all Hilbert spaces of the same dimensionality are just isomorphic to each other. So suppose you have this PT symmetric Hilbert space or whatever Hilbert space you found there.
Yes.
Why cannot I just map it into a normal one and then see for real valued fields, for everything real valued and standard norm?
That's what I just did. This is the map. That's exactly correct.
Sure. And then you get two normal oscillators in that case, two standard one. So
yes,
this person to do this
I'm claiming that there is a Hilbert space in which there are no negative, where the inner product is not negative. I'm claiming that your theorem is the following. Any Hilbert space can be mapped into another Hilbert space. My comment is, provided it already was a Hilbert space. And for it to have been a Hilbert space, it already had to have square integrable wave functions. But once I've got square integrable wave functions, I can map it into some other Hilbert space which provided that they remain square integrable. That I can do. Now, what this does, this transformation here, gets me into the diagonal basis. That's all it does. And that's so once I'm in the diagonal basis, I can read off I can read off what the eigenstates are, and I know that they're positive definite. I know the norm is positive definite.
So, but then you see what I don't understand in that case. If I look at this formula below 41,
yes,
this is just two normal standard oscillators. Why should we care about this Pils-Uhlenbeck at all in this case?
Because that's somebody asked me, what does this have to do with gravity? That's not the Hamiltonian that you write down for fourth order gravity. That's not the one you start with. What I'm saying is that by a sequence of similarity transformations, you can bring the fourth order gravity theory to this form. That's what I'm saying.
Sure. For the price of metric being complex.
Actually, if you have fourth order gravity, you have in some gauge, you have the tensor sector, which looks pretty much like the Pils-Uhlenbeck oscillator, because you have 2 degrees of freedom with spin 2, sorry. One is the massless graviton, and the other one is the massive ghost. In the vector and scalar sectors, you just have the ghost. So that those sectors don't look like the Pils-Uhlenbeck oscillator. And they look like standard negative oscillators, like minus p squared over 2m minus 1/2 m omega squared q squared.
Okay.
But since all the components of the massive spin 2 are related by Lorentz symmetry, most probably you have to do the same quantization for all components if you want to preserve Lorentz symmetry.
Yep.
And so and that thing, so this is what I did in one of my papers about inflationary perturbations and subsequent papers.
Okay.
And you have to do the right quantization for the scalar and vector perturbations, which is, in that case, you just have one choice because it's a single harmonic oscillator, and then you have to make the same choice for the tensor sector. And so in that case, you might break this arbitrary
I have to
freedom you have in the Pils-Uhlenbeck oscillator. This is
I have to pick my words very, very carefully. I have to pick my words very, very carefully. There is still a question of the fact that when you go to the actual gravity theory, the fluctuation has 10 components, not 1. And what I'm discussing here, if I can do a different screen share, I actually had this ready, but I couldn't get to it. Sure. Okay. That just shows you the relationship between the harmonic oscillator, the diagonal basis, and the non-diagonal basis, as I mentioned. But what I didn't discuss is...
So this is e to the minus q half is the operator you put inside the indefinite norm to get the positive norm, right?
Yeah. No, I put it in to show that the norm was already positive. I didn't know whether it was positive. Let me jump back a second since you've asked, and then
you have an indefinite norm, right? Because you quantize with positive energy, so you must have some indefinite norm.
I have no, not once I'm in the proper Hilbert space. In the proper Hilbert space, the n primes are the eigenstates of the two decoupled oscillators. That's here, H prime. That's just the usual n primes, and they're positive definite. The relationship between them is that the operator that diagonalizes the Hamiltonian is e to the q. Q is not, it's not e to the iq. This is not a unitary transformation. If it were a unitary transformation, I can only transform Hermitian into Hermitian. So I'm making a non-unitary transformation, which means I'm working from a skew basis to a diagonal basis. And the relationship between the skew basis and the diagonal basis is this one. And the reason why this is significant is because Q is not unitary, it's not unitary. So the original norm is n, that's my Hamiltonian before I go to the diagonal basis. That's the norm where this m is the right eigenvector and n e to the minus q
What is not? I don't understand. What is the normal without e to the minus q? So if you do just bra.
Oh, and m, it doesn't. They're not eigenstates. You see, the left eigenstate is n e to the minus q.
No, but okay. Suppose I do bra n cat n.
I don't know.
Without e to the minus q, what do I get?
I have no idea.
Guys, I need to leave you.
Yes. Oh, okay.
It was very interesting to talk to you guys. See you.
Wait a minute.
Sorry. Do you have 2 minutes?
Okay.
Maybe. Alessandro,
you can talk. I'm not a host, I think. So therefore, it's okay.
Because I wanted to ask you something about your talk.
Alberto, I think Alex is saying that we're going to be self-hosting.
No. It's actually Alexei Koshalev who is the host.
You
wanted to ask me.
Yeah,
Sasha, thank you very much for sharing. And yes, surely we can continue discussing. No problem.
Okay. I wanted to ask Alexander a question. Yes.
Sure.
So I'm confused by your philosophy, let's say, because you said that you don't want an indefinite metric, but you want so you have to choose between indefinite metric and negative energy, and you said I choose negative energy and positive metric, and then you make the example of quadratic gravity, for derivative gravity. But actually, so as a possible application, but because it's renormalizable. But actually, in the original paper by Stelle, where he proved the renormalizability, he argued that it is only when you quantize with positive energy and indefinite metric that you get a renormalizable theory. So I mean, maybe your approach can be applied to other types of
but you see, I'm not even sure, because wouldn't it be true that Stelle argument is actually Euclidean?
I think you're wrong, Alberto. I think Stelle showed that if you quantize with an indefinite metric and a bounded energy, you're renormalizable. He didn't say that otherwise you're not. Yeah. I don't think he discussed that case.
I have the paper here.
Yeah, but if you write with an unbounded energy, it's not there's nothing you can say. It's not a theory that you can quantize and make any sense of.
So if I can share, I can show you where he
yes. Yes.
By the way, but isn't it? I would suspect that the true statement is that he was using Euclidean methods. No. And with Euclidean methods, you cannot say anything about any of this.
No. It's not Euclidean. It's Minkowskian. It's Minkowskian. Yes, because there is the I epsilon.
Yes.
I cannot share the screen.
Wait a minute.
Alberto, if I remember well, this comment by Stelle was at the end of the paper, right?
Yeah.
Yeah. So I think what he says is true if you do like power counting in Lorentzian, because in Lorentzian, if you do negative energies, you would introduce a delta, an extra delta in the propagator.
Yeah.
And this one, of course, would spoil your power counting renormalizability.
Yeah.
But I think if you start from Euclidean, I mean, if you do renormalizability in Euclidean, power counting in Euclidean, everything should be still fine. So in this sense, I think.
Well, but look, if you
Alberto, I made you co-host if you want to share.
Oh, okay.
No, I've got it.
By the way, Huang Wu also wanted to say something.
Yeah. I've got the paper. If you
want. Here's the paper.
Okay, good. There's the I epsilon.
So you have two choices. One is negative norm, okay, and the other one is negative energy, which is choice of Alessandro, say. And it says that power counting requirements leads us to adopt an indefinite metric at the end.
Sure. But you see, this I epsilon is true only, I mean, because you're doing Lorentzian, right? You need the I epsilon.
But
this was Lorentzian.
But then you're saying that the Lorentzian is not correct. But at least perturbatively it should be correct.
By the way, but how does he start?
No, I'm saying if you want to prove renormalizability,
I looked for a long
Euclidean,
time.
you wouldn't bother about that, right?
Sorry, don't speak at the same time.
Sorry, Alex, please.
So at the beginning, can you show me beginning of this paper? Because I suspected that he was actually doing.
This is in the appendix.
Yeah, but the major calculations are probably done in kind of Euclidean, no? I would suspect.
But this is the original paper where he proved the renormalizability.
Yeah.
No, it doesn't mention Euclidean. I think it doesn't specify really Euclidean.
Maybe it's just pre-assumed, because I looked at this paper quite a long time ago.
I think the argument is correct, and
sure.
I don't find loopholes.
Can you go down? Wait a second.
So I'm not saying that. I mean, maybe your approach is interesting for other things because you were.
I know he's writing what he's using as a signature. That's true.
Oh, what happened if negative?
Everything is Minkowskian. Everything is Minkowskian. I think.
Right.
I mean, he can't discuss the existence of massive states as poles of the propagator if he's Euclidean.
It's not Euclidean, it's Minkowskian.
Yeah, it's not.
It's like we are having question from Juan.
But I think that, I mean, if you suppose you start in Euclidean, Alberto, you
wait. Can you show path integral? Can you show the path integral? I think it's I. Yes, that's.
Yeah, there is I.
I don't remember where the path integral is.
It's above. It just was a bit above. Yes, okay. It's here. Yeah, it's all actually Lorentzian. That's
true. Yeah, it's Lorentzian. Yes.
Yes.
No, but Alberto, do you agree that if you start in Euclidean, I mean, you have renormalizability, and then if you want to go to Minkowski, you may have maybe, I don't know, you have to choose some prescription
how is it possible that something doesn't work in Lorentzian and works in Euclidean?
I mean, in general, it's possible. I mean, you never
because the Wick contour contributes.
Yeah, for instance, depends not always you can Wick rotate in both ways, right? It's not always equivalent.
As long as you do perturbation theory, I would say is equivalent.
For instance, if you take Wick theories
with non-perturbative stuff, if you do non-perturbative stuff, you need Euclidean path integral.
No, but even if you take, for instance, now, I don't know if you take, for instance, this Wick theory with 6 poles. If you start from Minkowski, you go to Euclidean, or you do the opposite, you don't get the same result.
Sorry, which theory?
If you take, for instance, theories with extra poles, like the Wick theories with 6 poles, in that case, you would get, if you start from Minkowski, you go to Euclidean, or from Euclidean to Minkowski. I mean, depending on the prescription, you can have different results. Okay, so it depends also very much.
Anyway, if you claim this, then you have to redo the proof that he did, because he did it in Lorentzian. So now we're saying if you do, you start from Euclidean, then you can prove the same. So now you have to publish another paper where you say, look, if I do Euclidean, I can have a renormalizable theory with negative energy and positive norm.
Perhaps I can comment.
I don't know any proof of this. So
let me just make proof of Euclidean renormalizability of renormalizability.
He didn't prove what you said. So this is a non-trivial statement. Maybe it's true.
I mean, for instance, I don't know. I think the group of Anselmi, Marco Piva, they work with a different prescription, which is this Fakion. And even in the case,
okay. If you do another thing, but okay, that is another thing. That is another thing. But this is not what Alexander was saying. Alexander was saying, look, I can take negative energy, positive enough, and the theory, as far as I understand, he said still is renormalizable.
No. Look, what I was saying.
In Anselmi's theory, you have
just motivating what I was studying, and as you understand,
sorry, you were motivating. You were motivating, yes,
right.
But you were kind of assuming that this was true because you use static gravity. So,
but you see, so the point is, if you take norms which are negative, of course, it all comes from Gupta-Broadler quantization. But there, it's a fictitious linear space which has nothing to do with Hilbert space. It has nothing to do with probability conservations and so on. This breaks, you see, negative energies are okay because at the end, the whole energy of closed universe is 0, right? We know that the negative even though bounded, but negative energies in a single atom.
But this is another discussion. Now you're saying in which case
No, I mean just look that
want to be, in which case you want to be, but this is another discussion. The discussion
no,
is
look,
in which case you have a renormalizable theory.
That's a different story, because to be honest, you see, I don't remember. Last time I looked at this paper was long time ago, and I kind of had in mind that he was probably proving it by power counting and saying like it's all Euclidean as it is usually done. Okay, of course Euclidean path integral for gravity does not exist, and so actually is Lorentzian path integral, right? So formally speaking, this 3 point
for Einstein gravity, you mean? For Einstein gravity?
Yeah. It's not, but I mean, even not for Einstein gravity, for whatever gravity, right? Because there is operation ordering problem, and there is also this problem with these guys. I mean, like, if you write it with negative norm states, it's not a Hilbert space. If it's not a Hilbert space, what are we talking about? We don't have probability, we don't have Schrödinger equation, we don't have anything.
Alex, I completely agree with you, but that does not mean that I can't find a different Hilbert space where the theory makes sense and the energy is bounded.
Sure, but then the metric is complex.
No, it's not complex. Yeah. No,
like
no.
look at like in your example with
I start out with pure imaginary, and I say that theory is not sensible, and then I make a symplectic transformation to a real metric, and then I have a well-defined path integral. No, you see, it's because I don't. You see, if I started with real and made a complex transformation, then of course I'd finish up with complex. But I go the other way. I start with complex and make a similarity transformation to real. So the observables are the reals.
Right. Then it's the question, what for? I mean, like there, you know, like instead of Pais-Uhlenbeck, you were actually secretly considering just two normal oscillators. That's the truth.
I'm claiming that that's what the Pais-Uhlenbeck theory is. It's just, you just have to do a lot of work to diagonalize it to find that out.
No, but you see,
you can't find it out without going into the complex plane.
Sure, of course, you can find, look, in that case, the simplest question, if you can go to complex place, why don't you just complexify both of these?
Because then I don't get a well-defined theory.
Sure, but I mean, like,
I can't. That's my point. My point you showed. I have the difference of two oscillators, one positive energy, one negative. If I complexify both, I finish up with one negative and one positive. So I'm back where I started.
But look, the point is that this complexification, right?
Yes.
One thing is to rotate a contour in an integral. Another thing is to change it from the very beginning in which field, algebraic field, you are working in.
What I'm doing is I'm trying to find a domain for the path integral measure for which the path integral exists.
But you mean Euclidean path integral, please?
No, I mean Minkowski.
No, Minkowski would exist perfectly well for these two decoupled oscillators.
Okay, I've given you another. I've given you in the complex plane, there is a second domain for the path integral measure for which the path integral exists.
Sure, but it has nothing to do with the original system you started with.
What it is, I just write down a theory and I write down a measure, and I ask under what conditions can I find a measure for which the path integral is well defined and the energy is bounded from below.
Yeah, let's pursue that issue. So what classical theory do you get in the end?
Yes.
Okay.
It cannot be a higher derivative local metric-based theory because those things have indefinite energies. What theory do you get? What classical theory do you get from all of this math?
Okay, I start out with a path integral with a pure imaginary field. I make a similarity transformation and I finish up with a real field. I ask, then the path integral exists, it's well defined, and if it's well defined, there's no problem with the energy. And then I ask, what is the quantum theory that would correspond to that path integral?
Wait,
Philip. Wait. And
why don't you answer the question, which is, what is the classical theory that you get? Is it a metric-based invariant field theory? And if so, which one?
I finish up.
It can't be that one. That one has indefinite energies. Which one is it?
No, I know.
There isn't any, and therefore it isn't a metric-based invariant theory of gravity, and that ought to worry you.
No, Richard, the fourth order theory has two totally different Hilbert spaces, one with negative energy and one where the issue is negative norm.
You know, you're right about that. That's true.
Good. Now, negative
norm is not a Hilbert space.
And by the way, the negative norm version of it corresponds to a metric that would have been imaginary. So I would say nonsense, but that's what the negative norm theory corresponds to. Right. And my question is, I'll let you do all the math that you do. Give me the end. You've done all the math. You've got a theory that you say is wonderful theory. What does it correspond to? Is it a metric-based theory of gravity?
Yes, absolutely. Because I then make...
What's its action?
The action is the action that I showed you.
It can't possibly be that action because that action has negative energy. This is a classical theory, no quantum mysticism going on. It's a completely classical theory, and that theory certainly has negative energies. What is the theory that you get?
The action that I start with is an action which is a classical action with a pure imaginary metric. The action that I finish up with is an action with a real metric. Now,
okay, so what is it? Whoa. I'm asking just a simple question. Write down the field equations, write down the action. It cannot be the quadratic gravity theory because that theory doesn't have the properties you state. What is it?
It's a quadratic gravity theory, which is similarity transformed.
No, wait. Let's shape it even easier.
The quadratic gravity theory with a real metric moving in a real space-time will not have positive energies. What is the theory that you get?
The space-time is real. The fields can be complex, but they are functions of
okay. So length and distance can be complex numbers, right?
X, Y, Z, and T.
Doesn't that worry you?
No, of course it doesn't, because I can.
Okay, well, it worries the shit out of me.
Oh, I can't do much about that. Okay, two things. One is first of all, I'm saying until I find a Hilbert space, a quantum theory that is sensible, and the answer is it's the one where that complex G mu nu, that complex classical field, is symplectically transformed into a real field in a domain where the path integral exists and the quantum theory exists. Now, if I take a Christoffel symbol, if I take a Levi-Civita connection, I have a lower G mu nu and a contravariant G mu nu. If I replace the G mu nu lower, the covariant by I times G mu nu, and the contravariant by minus I times G mu nu, that leaves the connection invariant. The connection admits...
It changes distances. Distances are just dx mu, dx nu, G mu nu.
No, I'm sorry, Richard. That is not correct. You write a distance. You write a ds squared is equal to G mu, dx mu. I understand that.
Well, yes.
You don't have any connection to the propagation of particles until you have solved the propagator in that theory. And what you will find, and it's very straightforward. Well, you write down the action. You write down an action for the geometry, for the Riemann tensor in whatever combination you want. You then take a field like Maxwell. You let it propagate in that geometry. You look at the normal to the wavefront, and you will find that the normal to the wavefront is geodesic. You then define distance by measuring along the geodesic. Now we do something else. We introduce a line element ds squared whose variation gave that geodesic. However, that line element can be multiplied by a constant and you'll still get the same geodesic. And that's the geodesics that you measure. That's how you measure distance. The distance is determined by integrating along the geodesic, not by looking at ds.
But you're multiplying your words. Just a minute ago, were you going to change the contravariant and covariant metrics by multiplying by an I, right? And if you do that, The integral.
I don't change the geodesic. I don't change the geodesic.
Wait. So Philip, if I take Riemann tensor, okay,
yes,
and I go into local flat frame,
yes,
I kill all Christoffels. I don't care about Christoffels. I am around the point. I only will have second derivatives of the covariant metric, and that's it. After that, I will look at my geodesic deviation, and I will know whether this thing is complex or not.
Yes, but the Riemann tensor is built out of the connection.
Sure. But there is one particular representation with lower indices. This thing is measurable, and this thing is measurable by two particles. And
if you want me to Alex, you want me to get the distance between 2 points. At point A.
No points. Geodesic deviation. I will take geodesic deviation. Two particles. I will put them there in point.
I can't make the geometry flat at two different places at once.
So what?
I can't make the geometry flat at two different places at once.
No. You are in local Einstein elevator, and locally there is a reference frame in which you can kill in this neighborhood. You kill your Christoffels. And the only thing what survives are second derivatives of the metric. And the second derivatives of the covariant metric, they will be there.
Yes, that's absolutely correct.
Sure, yes. But this covariant metric, if you multiply it with I, you will see it.
But some other place, if I have Mr. Einstein in a second elevator, killing the Christoffels in elevator 1 does not get rid of them in elevator 2.
No.
And then I want to know what's the distance between the two elevators.
Look, that's how we measure Riemann tensor. Two particles infinitely close to each other.
Yes.
Right? Because geodesic deviations, these congruences of geodesics and so on, is for infinitely small distances. So no way I will not see this eye there. I will.
No, but geodesics are you can integrate them over any distance you want. Look,
geodesic deviation. It's relative acceleration between these two particles. What measure? What we care about?
Let me state it differently. Where do geodesics come from in physics?
No. Look,
you've got to first tell me where does geodesic come from? I'm going to give you the answer.
No, look, I think classical example.
Let me give you the answer first.
Sure, no, but I know how we get geodesics. You see, that's not
I'm telling you that you don't get a geodesic by varying the line element. What you do when you vary the line element is you demonstrate that the geodesic is covariant. But it doesn't mean that the particle knows anything about the line element. So let's state it this way. Long before GR, people knew that light travels in straight lines. What that meant was that the normal to the wavefront was a straight line.
Sure.
With GR, what comes new is that the normal to the wavefront is a geodesic because the wavefront's in curve space. That's the geodesic.
Sure, but we know
the energy of the light wave in a curve space is transported along the geodesic. Nowhere did I ever write down the line element.
See, that's the point. If you take
because the line element is not part of the Maxwell equations. I can solve the Maxwell equations in a curve space and show that the normal to the wavefront is a geodesic without ever writing down ds squared.
Look, it's a question of different question, right? It's a question of how you measure distance. And
I measure distance along a geodesic.
That's right, but there is a metric there.
Oh, of course. I didn't say there wasn't a metric because I'm discussing the propagator in a curve space with a normal to the wavefront, which is a geodesic. I've got a metric.
No. Look, there is a metric.
The geodesic equation is not sensitive to the sign of the metric or to a phase of the metric.
Equation not, but the length.
Add a force term. Just add a force term, something other than gravity, and then it is.
No, you have
add the Lorentz force.
Yes, but then you've got
to a charged particle. Then it doesn't move along geodesics anymore. It certainly is sensitive to it.
Now, what I've written in one of my papers is that it's possible to check the phase of the metric in an interference experiment with electromagnetism. That's correct.
I see. So you're really arguing that the metric might be complex, right?
I'm arguing that if you made a complex obviously, if you have to rewrite the Maxwell equations in the curve space with the complex metric in order to get the Lorentz force appearing in the geodesic equation.
Well, let's just be clear. That's a yes or no question. Are you arguing that the metric might be complex as an observational statement? Is that a correct statement or is that a misstatement?
I'm not saying that the metric is complex. I'm saying is that the metric can be brought to a, maybe I'll state it this way. If
you should be a politician, Philip.
Okay, bless you. No,
sorry guys, I need to go. It's fun talking to you, but I need to go.
Okay. The coupling of electromagnetism to gravity is conformal invariant. Therefore, I can change the phase of the metric, but at the same time, I change the phase of the vector potential, and I do not change the properties of a massless particle.
Okay, but we have other things than electricity and magnetism to study gravity with. For example, our bodies.
Okay, now you're going into a whole different question. And that is, now you've got to look at a massive particle propagating in a curve space. And again, the normal to the propagating propagator.
It could be massless, just not conformally invariant. There are massless, not conformally invariant particles.
Okay. Now
the inflaton, for example.
Now I've got to go a lot further. Okay. If you follow what I'm doing to the end, then you work with a purely conformal invariant theory. My talk today and lots of things I've done are how do you make second plus fourth?
Okay, whoa, let's pause that just for a moment. Do you admit then that this is all nonsense if you try and apply it to r plus c squared or r plus r squared?
No, I did not say that. But what you asked me was a different question.
But you just a minute ago, I thought I heard you, maybe I misheard you. You said that you've got to do this in the context of the conformally invariant theory. Is that what you said or not?
Talking about mass generation. You asked me about massive particles and what
why do we have to have mass generation at all? I mean, if we're talking about a classical theory, there just are masses, right?
You don't have a classical theory with a mass if the mass is created by dynamics in the quantum theory. The whole notion of you can write down a classical theory with a mass is convenient, but is not correct. Because if we believe everything we believe from Weinberg-Salam, mass comes from the vacuum. Therefore, you have to go and write down a theory with no mass in the action. But what I'm doing is, since you asked me how do I really deal with mass, and the answer is I deal with mass through the vacuum. Therefore, I need a theory with no mass scales. Now, obviously, the second plus fourth has a mass scale, but that mass scale doesn't come from the fourth. That mass scale came from the second. That's the thing that I am against in principle because of conformal gravity, which doesn't allow a mass scale. However, you can ask the question, if I have a mass scale for the gravity and I have a fourth order theory, an R squared term as well, is that theory sensible? And the answer is yes. Now you ask me, if I bring in another particle, a matter field with a mass, can I add that mass term into the Lagrangian? I say no, that mass has to come from spontaneous breakdown. And that's the difference. So I'm allowing...
Okay, so what you're doing then, by your admission, if I heard correctly, doesn't make any sense unless it's a purely conformally invariant theory. Is that a correct statement?
No, not at all. No, I'm saying that mass is dynamical, independent of whether or not the gravity...
You will not allow any bare masses. So for example, the theory of quantum electrodynamics with the bare fermion mass, you would not allow that.
It is zero, yes, absolutely. And that's, I can explain
a suggestion here.
Yes, I can explain how that works. Right,
okay, I think we're going to just have to agree to disagree then, Philip.
There's nothing to disagree about. Weinberg-Salam is telling you the mass is dynamical. It's not telling you anything else. There is no...
Yeah, but you're telling me that the theory of gravity doesn't make any sense if I use quantum electrodynamics and I just I find that very difficult to
in
accept.
SU1, there is no Burr mass to the electron.
If
No.
I may interrupt, I think it is a good time to stop it here and
Okay.
Yes, I suggest to move it for tomorrow. And in this case, I'm indeed the host, and I will stop it if I press a button. But I have a tradition to stop around midnight, maybe, which is for me the case.
Okay.
Okay.
Richard, thank you very much for your questions.
Well, it's fun talking with you, Philip. I think we're not going to agree, but we both want to
Tomorrow
get the answer.
we definitely can continue. There is no question. Richard, after your talk, there will be a lot of time for extra discussion.
Okay.
Well, I'm not going to talk on higher derivatives, but I'm happy to discuss with anybody who wants to talk.
Yeah,
So-
but discussion is free, so.
Richard,
Okay.
you have the most intriguing title of the conference. Reminiscence.
Yeah.
Yes, I mean that's
With
true.
apologies to the famous French novelist.
I love the title. I'm looking forward to it.
Okay. Hope you all enjoy it.
Yeah.
See you all tomorrow.
Good.
See you tomorrow. Bye-bye.
Bye-bye. See you tomorrow.
Yes. Bye-bye.
Bye-bye. Bye-bye, Philip. Thanks for the discussion.
Yep.